All right, let's see here. Hello everyone, welcome to today's FPGA development live stream. Checking to see if what the delay is like. So, I guess I'll just go ahead and get cracking, and we'll see how this goes. All right, let me think here. The plan for today is to do a couple different things. The main goal is to try to get basically a prototype version of the Corundum datapath implemented that can then be used going forward to act as a basis for the next generation version of Corundum. So the idea is to build basically a prototype, which we can then sort of ship of Theseus it into something that's actually going to be useful in the long run. So, let me see here. I got a couple different things planned before I get into the actual coding portion. First, I want to provide a little bit of background, both some non-technical background and some technical background, and then we'll get into the actual coding portion of it. Oh, I see. I'm going to be watching the chat periodically. I see we have somebody from South Africa. Well, that's very cool. That it's 9 a.m. or 9 p.m. I'm assuming 9 p.m. So, yeah. Well, thanks for taking the time to tune in. All right. So let me go ahead and get into some of the non-technical stuff that I wanted to discuss just as background. So if you're tuning in to the recording afterwards, hopefully I'll remember to put some timestamps down below so you can skip ahead. Otherwise, if you're watching this live, I guess you'll just have to wait a couple minutes before we get to the good stuff. Let me see here. So there's basically two main things I want to discuss first. The first thing is why I'm going through the whole process of rewriting Corundum as opposed to continuing to build on the existing code base. The second thing is some of the lessons that I learned working on the legacy version of Corundum. And then after that, we'll get into the actual coding. So yeah, also, if you have any questions or comments and you're watching live, go ahead and pop that in the chat and I'll get back to you as soon as I can. All right, so for the first bit of background, why am I going through this whole rigmarole of rewriting everything? Really, what it boils down to is that I've come to the realization that the existing legacy version of Corundum is completely dead. It has no future whatsoever, and it's took me a while to come to that realization, but basically, over the past 5 years that the project has been available, we've run the experiment, and that's the inescapable conclusion. A project like Corundum is very big, complicated code base, and to really do it justice, you need, many people working on it full time, right? It's not a project for one person for nights and weekends. You're not going to have an effective project. And what we realized is that with Corundum being available under the permissive MIT BSD licenses, it's subject to the tragedy of the commons. So, this thing has been available to whoever, not just the research community, but also, companies that are using it in revenue-generating roles. And nobody has ever bothered to reach out to the people behind the project and saying, hey, we use this, we'd like to make sure it continues to exist, so, here's some financial support for you. That hasn't happened over 5 years, so, okay, I have to figure out what to do next now that the grants at UCSD that have been paying my salary have come to an end. So, basically, if the project is going to be self-sustaining, it has to have a way of actually bringing in revenue, and probably to the tune of several $100,000s a year realistically, in order to pay the salaries of potentially multiple people that would be working on it. And you just simply can't do that under like a permissive license. at least for something as niche as Corundum, which is, it's like a niche of a niche, right? It runs on FPGAs, and you really only need something like this in a very narrow range of circumstances. So yeah, it's not like something like Mr, which targets gamers, and you can potentially run something like that on donations. Corundum, not so much. So the only option really is to be able to charge licensing fees to companies that are using it, and the only way to do that is either to take it completely private, which I don't really want to do, or to change the license to something more restrictive that will actually encourage companies to help support the project. So that being said, that's probably the main reason for doing the rewrite, but there's a couple of ancillary reasons as well, right? If we do a rewrite, we also have the opportunity to change the language to something more modern. So I've had a few people ask about, hey, why didn't you use System Verilog for this? Well, now we have the opportunity to do a rewrite into System Verilog. I've also had some people ask about why you're doing a rewrite in System Verilog as opposed to like Spinal HDL or Chisel or VHDL or whatever. Well, I don't really use the alternative HDLs because it causes a lot of complexity with the tools. Like, how do you do placement constraints? How do you do timing constraints when you have a mass of generated Verilog? So those are not great. And then something like VHDL, it's one, it would take time to come up to speed with the language, and two, it's a more complicated process to take some of the existing code and port it over. So I guess the point is that it's not a complete rewrite. A lot of the libraries are more just a direct port, and then the data path itself is going to be pretty much completely rebuilt. Another factor as well is that there's a number of significant architectural changes that I'm planning on making, and a rewrite gives you the opportunity to make all those changes without having to worry about legacy constraints. So if we have to make some significant changes to how the driver works, for example, I don't need to worry about how people are currently using it. You start with a relatively clean slate, then that makes some of this a lot simpler. Let's see. I think that was all the reasons. Yeah, or all the main ones anyway. All right, so moving on to the slightly more technical reasons, or the slightly more technical background. So when I've been working on Corundum, I know one thing I've mentioned a few times is, hey, wouldn't it be great to take this design, or take the driver and upstream it into the Linux kernel, and have a DPTK driver and things like that. One thing that I realized is that the driver in its current form isn't really set up for that. If you wanted to put it into Linux or into DPTK, it would create kind of a logistical nightmare. And the problem is, in some sense, not really a technical one, but it's more that, I don't control Linux, I don't control DPTK. When you put a driver upstream into Linux kernel or into DPTK, then you start running into versioning issues, right? I can't ensure that somebody is running a compatible version of the driver with given instance of the hardware, right? So if you have a complicated interface between the two, like a big register space, then it really causes trouble, because if you're going to change the design of the hardware significantly, you probably need to make significant changes to the register space. And if you can't change the driver because it's included in the LTS version of Linux or something, then that's a significant problem. So one of the things that I want to do is rebuild that interface between the driver and the hardware, such that you could use to really decouple that interface. So you can use an old version of the driver with the new hardware, or a new version of the driver with the old hardware, and things will mostly just work. Obviously, you'll have to have some sort of negotiation process, but you can't do this sort of thing with a register space. So that's one of the things that needs to change, is that the register space doesn't need to completely go away, but it needs to mostly go away. Let's see. I think there was one other thing that I was going to mention as well. I mean, that's probably the main thing that that's a little bit counterintuitive, is that it's harder to change the software than it is to change the hardware. I mean, usually if you're talking about spinning a chip, that's totally the other way around. You can use the software to do all sorts of reworking and workarounds and things like that that you can't do in the hardware. Oh, right. That's another related thing. Another thing that I've been talking about as well, even with the legacy version, is removing all of the board-dependent code from the driver. And yeah, obviously, if you're going to put the driver in the Linux kernel or whatever, and somebody releases a new board, they don't want to have to make a pull request against Linux just so their board works. So it's vitally important for all of the board-specific stuff to be pushed onto the FPGA. And most likely that means we're going to be adding, potentially multiple soft cores to the FPGA design to deal with this sort of thing. But yeah, the specifics on that, we can get into it some other time. Yeah, and then the other thing, I guess that's kind of ties into this as well, is that, oh right, yeah, I'm actually planning on making a couple of different variants of the Corundum design that target different optimization points. So I've talked about this at the developer meetings before, where I'm planning on doing a Corundum Lite, which sort of matches the capabilities of the current legacy version of Corundum. And then I'm planning on doing kind of a step up and a step down. So Corundum NG would support higher rates, and Corundum Lite would be super size optimized. So if you wanted to run at like a gigabit per second on an SoC, then Corundum Micro would be a good option for that. And because these designs could have, well, they will have significantly different internal construction, we'll really need to take that mapping layer into effect to make everything work. Yeah. So that's kind of one of the big things, is this sort of architectural reworking. Oh, and then I also need to rebuild the whole descriptor subsystem to support more complicated descriptor formats. And this is extremely important if you want to do something like RDMA or TSO or whatever, where you need to connect potentially quite a few memory pages to each operation that the hardware is going to be carrying out. So with the old version, the descriptors are all fixed size. You can actually change the size on a per queue basis, but not on a per descriptor basis. So the idea with the new design is that you'll actually be able to change it on a per descriptor basis. So, and potentially it'll support things like inline payload data and things like that. So getting all of the details figured this out is probably going to be a longer term thing, but the rewrite gives an opportunity to mess with all this stuff. And I guess I should also say that the rewrite, by using system verilog, should also reduce some of the opportunity for errors, because I've definitely made mistakes when connecting or making big complex connections between modules and adding a typo or messing up some little thing, and it can be really annoying to debug. But if you use system verilog interfaces, it can sort of eliminate maybe not all of those errors, but a lot of those errors. It's kind of the same reason that people use something like Rust, which while in some cases it might be a little bit more difficult to write a program in, the compiler doesn't allow you to make certain mistakes in terms of memory management. So in some sense, that can make things easier to debug, because you don't need to worry about a particular class of bugs. I guess it's a couple of comments here to take a look at. In dealing with version dependencies in software drivers and FPGAs at work, it doesn't scale well. Yeah, that's the big thing, right? It's if you design things properly from the get-go, then you can kind of get ahead of some of these problems. But yeah, it's definitely a potential problem if you can't guarantee that the hardware and the software are the same version, which is kind of a requirement for the existing legacy version of Corundum. All right, then the other comment here is you could try to put the board-specific stuff in the soft processor. Yeah, that's exactly the plan. In fact, I guess I can just talk about this real quick. The idea that I have in mind is actually to add potentially 3 soft processors, one of them to handle the board-specific stuff, one of them to handle managing the data path, and then a potentially third one for like real-time time synchronization stuff. And by having 3 separate soft cores, it means you can manage the firmware versions for all those separately. So like you can update the datapath management firmware separately from the board level firmware, the board management firmware. And that's quite important because you don't necessarily want to be editing the board management firmware all the time, because that needs to be tested on each specific board, versus the datapath management firmware would just be tied to the datapath. And then these would be optional. If you don't have any board specific stuff, then you can leave that core out. Yeah, so that's kind of the idea. But it's going to take some time to get all of the details hammered out and such for that to work. But yeah, the idea for today is to do a really stripped down implementation of the datapath. I mean, I know I mentioned it's probably going to be like Corundum Micro, but realistically it's going to be more like somewhere in between Corundum Micro and Corundum Lite, because the idea is that I'm not going to do any optimizations at all, right? It's not going to be optimized for size. It's not going to be optimized for performance. And with that sort of a setup, I mean, that kind of falls somewhere in the middle, but it should be, hopefully, a more straightforward implementation. All right, so I think that takes care of most of the background here. So I'm just going to take a look at this setup that I have really quick, and then we'll get to work on the actual implementation. All right, so what I have here is this little computer that I put together a while ago, and this is completely overkill for what we're doing today, but you know, it's what I have available at the moment, and there are some nice features of this unit that makes it a little bit easier to deal with. So the motherboard in here is a super micro motherboard. I can't remember the exact part number, but it's one of their, I think, X13 series boards in this, you know, very small enclosure. It's not a micro ITX or whatever, but it's like a mini ATX or something. It has a Xeon what, 6430 CPU here, so it's pretty beefy, and I think it has got a lot of RAM. I think it's got 256 gigs of DDR5. So yeah, in this economy, that's worth quite a bit. Yeah, I don't need that much memory necessarily, but it's important with these server CPUs, especially for doing high performance networking stuff, is to populate lots of DIMM slots, so you get lots of memory bandwidth. So I think in the initial version of this that I put together, I put smaller memory modules in there, but then one of the memory modules was bad, and I wasn't able to find a replacement of the same size on short notice, so I put in a different set. Let's see. The motherboard itself has 2 PCIe Gen 5x16 slots. So we've got a Mellanox NIC down here. This is just a 100 gig NIC. And then I've got an FPGA board here. We're not going to be using this FPGA board today, but it's here. And then over here, the motherboard has 2 sets of MCIO connectors. And these are really convenient because I can plug an FPGA board in basically on the desk and have, you know, much better access to it, and, you know, run it outside of the computer case and still get the full 16 lanes. And these are decently long cables, so you get, you know, a fair amount of space to play around if you need it. So not much else to say about this, aside from, you know, this has been a very nice unit to take to conferences and whatnot because it's very compact. All right, let me see if I can stand this up and get a little bit more space to work here. Flip side, this thing is rather heavy. And the other thing, this particular case, while it's nice and compact, it's really annoying to get into because there's a lot of screws, and you literally have to take it completely apart to do anything. So I wouldn't necessarily recommend it unless you need something really small. I guess that's the trade-off, right? The full-size tower, you get lots of room. But yeah, with this one, if you need something high density, that's what you get. All right, so for today, we're going to be using one of these ex-Alibaba FPGA boards. This has a, oh, the fan that I put in here stopped working. Happened. Okay, that's not great. I don't think that'll be a major issue. These use the Kintex UltraScale Plus XCKU 3P FPGAs, and you can get them on eBay for a pretty good deal. So they're not necessarily the best board you can get, but they're pretty good value. I think these I managed to pick up for around 140 bucks each. I've heard that if you get them directly from China, they are a heck of a lot cheaper than that. But, you know, there's logistical challenges potentially of ordering direct from China. So we'll see if maybe there's a possibility of doing some sort of a group buy. If you're interested, you can pop onto the Corundum Zulip, and maybe we can figure something out. These boards do not have USB JTAG on them, so, and they don't even have the standard Xilinx JTAG header, so you have to use a flying lead cable to use these boards. And I am using one of the Xilinx, you know, legit DLC10 cables with the original breakout setup here for the flying leads. I think this board will work just fine with one of the knockoff cables, but it's like, if you can get these cables for like 40 bucks versus the knockoff ones are also about 40 bucks, like, you might as well try to score one of the legit ones. And I have this in a little, you know, external frame here which can hold card. Unfortunately, this only has a short bracket, and the card only, this frame only takes full height cards, so it's kind of flopping around a little bit. But you can see how the MCIO cables power come in here to power the card. Oh, I'm looking at this. Maybe I do need to figure out this fan. What is going on with this? Why did this fan stop? In fact, this card may have overheated, which is not helpful. Okay. I was not planning on having to debug this sort of thing today. What is going on with this fan? Yeah, the unfortunate thing about these cards is that if you don't have sufficient airflow, they can overheat. This is a 12-volt fan. Why did that stop spinning? I think I have some more fans lying around. Give me a second. Let me see if I can get an alternative setup for this. Did some rearranging of stuff, and whenever you do that, then looking around for things can sometimes take longer than expected. All right, let me see. All right, actually, before I hook that up, let me just see if this fan spins. Okay, that's working. All right, let me get this thing reconnected here. Then I'll have to reboot this computer for this to work. One thing I will mention as well, as a bit of an aside, is that the motherboard in here seems to be pretty well behaved in terms of PCI Express. Some motherboards are quite annoying about how they, you know, rescan the bus if devices disappear randomly during operation or are not present when you do the initial boot. But this one seems to be pretty good. If the card doesn't show up, or if it's not present right away, it will do a good job of rescanning and picking it up later. So, all right, that fan is now running. Plug this back in here. Okay, now I'm getting the light. That's good. All right, cool. And then I'll have to reboot this thing to get it to show up, but I'll do that in a bit. All right, so that's it in terms of the setup. Let's see. The next thing is to get into the actual coding here. So the plan actually is not to immediately jump into Corundum. I need to go ahead and take a look at all of the interfaces around the edge and make sure all that's working first. So I got to test the Macs, and I got to test the PCI Express interface. And this will also serve as basically putting together the top level design for Corundum, which has, you know, all of the necessary interfaces. So I need to put that together, and then I'm also going to put together a very simple device driver that basically tests the register space on this and does some, you know, test read and write operations effectively. And then we'll work on the data path on the card, the some simulation code to test that data path, and also we'll take the very basic driver and extend it with, you know, the components needed to act as a network device. So that's the plan. Let's go ahead and get into it. All right, let me switch to, here we go. Okay. Okay. Oh, I got another question here. What motivates me to write all these modules on GitHub for all of these boards? Well, that's a good question. So I guess all of this stuff kind of initially started out as a hobby project and partially just, you know, messing around and learning how to do stuff. But now that, you know, Corundum seems to have a bit of a life of its own, it seems like that there's people that are interested in using this stuff. So if we have example designs for various boards, then people can take that and build on top of it and such. So now for supporting lots, I guess there's a bit of a difference between, you know, the core code and all of the board level example designs. I guess with the core code, there's probably a few reasons for that. At least initially it was more like, you know, I wrote it for my own purposes, so we'll put it out there and see if anybody else finds it useful. But yeah, now that I need to actually find a way to, you know, make this, you know, monetize it in some way, then it actually seems to have worked out pretty well, where making all these modules available has kind of created some, it's got my name out there, right? So now I can potentially capitalize on that and say, well, hey, if you want to use this in a commercial environment, you know, you can pay a reasonable licensing fee, and then, you know, you have all the code available, and you've been able to mess around with it and look at the code and see what the quality is like. Unlike what you get from a lot of companies where you basically can't see the code at all, or you don't see anything until you've already signed a bunch of NDAs and paid a bunch of money and things like that. So from a transparency perspective, it's potentially useful. And then I've also been doing a lot of you know, research over the past few years as a PhD student and postdoc and whatnot. And, you know, if you have code available that you can build on top of, that's incredibly useful. So by releasing Corundum, you know, to the world as opposed to keeping it internal, that's definitely facilitated some research, and there's, you know, a fair number of papers that cite Corundum. So that's always pretty cool. Hopefully that answers your question. Let's see. And somebody else is saying that the motherboard PCIe identifying capability, I think it's called hot plug. I'm not using hot plug. So there's a difference between hot plug and just having a motherboard firmware that doesn't completely suck, because a lot of machines have very weird habits when it comes to managing the PCIe bus. So they will, for example, remember when a slot has a you know, didn't have a device in it, didn't enumerate, and then they won't check that slot again until certain conditions are met. So in some cases, in the good cases, it will check on a cold boot, which causes some problems, but not the end of the world. In some cases, they'll actually remember, and you have to physically remove the card, do a cold reboot, plug the card back in, do a cold reboot, and then it will work. So yeah, and none of this has anything to do with hot plug. Hot plug is about being able to plug in the device while the machine is running and being able to use it. So in that case, it's about making sure that the resources that that card is going to require are already allocated and ready to go. Because the problem with PCI Express is you basically have to allocate everything in a depth-first pattern. And if you don't do that properly, or once you've done that and you try to add something, you're screwed unless you've basically reserved space for it ahead of time. So if you want to do hot plug, something along the lines has to reserve PCIe bus numbers and a certain amount of address space, such that when you plug a device in later, it can be assigned inside of that hole. So some motherboards support that. It seems to be pretty rare. It seems like, honestly, every motherboard should be able to do that, because I think it's just a firmware thing. But I guess, you know, it costs money to verify that that actually works properly, so most boards don't turn it on. Yeah, there's another comment here. I've always made sure that the FPGA boots first and to keep the configuration and bar space identical during reconfigurations. Yeah, that's very important. If you don't do that, then you're in trouble. Somebody else says, I don't feel like I'd be doing this stuff unless somebody was paying me. Yeah, I mean, that's definitely valid. I mean, the thing is, a lot of this stuff, at least initially, has been, you know, for me, just kind of a hobby, sort of like, hey, can we build this cool thing? And then I was getting paid as a grad student. Not very much, but I was getting paid. So, you know. But yeah, obviously, long term, it's not sustainable to, you know, not get paid for this stuff. So that's kind of the idea with Corundum is, hey, can we get to a point where, you know, companies that are using it would actually be interested in paying to support it and ensure that it continues to exist in the long run. So, anyway, let's see here. Let's go ahead and get started. Since we've been derailed with some questions here, I'm trying to remember what the next step is going to be here. All right, so I've gone ahead. Well, so I don't know if you turned into the streams before, but previously I was using the Sublime text editor, and I recently switched over to Zed, and I'm still, you know, getting things figured out a little bit here and there. There's definitely a number of things that Sublime does that Zed doesn't do that take a bit of getting used to. Anyway, but this seems to be doing what it's supposed to do at the moment, so that's good. All right. So I've gone ahead and created a folder for Corundum, and what I need to do in here is to start creating some. I'm just going to create a design in here. You just open up a terminal here. I know there are terminals built into this, but sometimes I just like having a separate window for whatever. All right, so let me go ahead into, and I'm going to create an example design for the board that we're using here, right? All right. And I'm going to make a copy of, let me see here. I have an Ethernet example for this board. I guess I should have just copied that instead of, yeah, all right. So I'm going to copy it. Where am I? I got to go up another one. All right. And we'll do that like so. Oops. All right. All right, so here's one slight annoyance about Zed. It doesn't always properly rescan stuff. So if I rename that, will it show up? No. All right, gotta go up one more. Really? That didn't work? Well, this is kind of annoying. All right, let me I will just do that, and then I can drag and drop the files over here. Let's see. Maybe it'll figure itself out at some point. All right, so the first thing we need to take a look at is the XDC file here, because the Ethernet one, it only has the Ethernet related stuff in there. I need to turn on all the PCIe related signals. One thing I'll mention as well is that I have seen XDC files for this card floating around, but it seems like a lot of them have some issues. So for example, on this particular chip, most of the I/O is LVCMOS 3.3, but most of the designs, or most of the XDC files I've seen set that to something else. So I don't know why, but as far as I can tell, that's how things are wired up on the board. There's no level translators anywhere on the board. It's a very simple board design. But yeah. All right. So let's see that, like I said, there's not much on this board, right? So we've got 100 megahertz system clock that's provided to the FPGA. There's a handful of LEDs. Some of these are on the board. I think all of these are. All these on the board? I think all these are on the board. With the SFP LEDs, those are actually visible through the back panel. Maybe there's another one on the back panel as well. This one might be on the back panel as well. I would need to double check on the actual board. There's a reset button, but I don't think the button is actually installed in most cases, but it is hooked up to that pin. There's a couple of GPIO pins that are not fully connected, but they are accessible on the board if you do some poking around. And then there's two SFP28 ports. So here's the high-speed connections for that with the reference clock. It's a fixed 156 megahertz reference clock. And then we have some control signals here and the I2C signals. And I think the TX disable pins are tied on the board. I've not been able to find a connection to those on the FPGA. Maybe they're connected somehow, but I have not been able to figure that out. Let's see here. I2C interface. Oh, I guess some of these lines should actually be deleted. So RS, TX disable. Yeah, those pins are not there. That can go away. That's the I2C connections. Okay, that seems reasonable. There's also two different I2C interfaces on here. I think they're going to two different EPROMs. I gotta double check on that though. And then obviously PCIe. And that's it. There's no memory. There's not much else on here. Well, actually, I guess there's a QSPI, but that's on, you know, the dedicated configuration pins. All right. So let's take a look then at the HDL for this. Right. So for the top level, we'll have to add the PCIe pins here, and this one basically just has all of the standard boilerplate that you need. So I like to put in an MMCM to take whatever the input clock is and convert it to 125 megahertz. There's, I guess, not really any reason to do that necessarily, but having the MMCM means that if I need to add some other clock frequency or change it, you know, it's pretty easy to do that. And then there's some reset synchronization stuff, and then the core logic. There's really not much here. And then for the core logic itself, in this case, we're just looping the max back. So this is basically just a Mac and Phi logic, and that's about it. And with the, you know, newer incarnations of the wrapper logic that I've put together, we don't actually need to mess around with the transceiver wizard at all for setting things up. So if you've watched some of the previous videos that I've done, like talking about porting Corundum, where we have to go into the transceiver wizard and assign pins and things like that, that's not necessary with the new setup, because I basically, the way I have things set up is I turn off the external I/O pins, or the external I/O constraints, and then let's see, I turn off the external I/O constraints, and then everything just flows from the pins. Somebody's saying the font size is small. All right, let me see if I can adjust that. Is there? I do. Nope, that's not working. All right, let me see about that. Open settings file, there we go. And let me see if I make this. That should be a little bit better, probably. All right, we'll see how that works. Okay. What was I saying about the wrappers? Right, so with the current generation of the wrappers, it basically turns off all of the internal placement constraints. So all you need to do is drop it down and wire it up, and you're good to go. You don't need to go change any settings in Vivado. So here's the SFP plus pins, the LED pins, the reset, the clock and reset connections, and then we have the core logic here, right? So we've got the clock connections from the SFPs, the status outputs from the PHYs, those are put on the LEDs, and then I have some logic here just to blink the heartbeat LED, just as an indication that the clock is actually running, so that's useful. And then we get into the actual logic for the Macs. So we have a little bit of clock related stuff. We need the iBuff DS GTE4 to bring in the clock itself, and then to get a copy of that in the fabric, we use a buff GGT. So that provides a clock that's basically being used to gate the reset. And then I have AXI stream interfaces for the TX data. Well, so I got TX RX, TX completion, and the SFP, the statistics output. Do I always assume one ref clock is driving the entire quad? No sharing with other interfaces using the other QPLL. I've done sharing with PCIe before, because on the Korea K26 system on module that you only get one quad. So I'm trying to remember how I have things set up. Well, let's just take a look at the transceiver wrapper itself. But it should be possible to use them in that particular mode, because I've done it before. I'm not sure if these wrappers have been fully updated yet. Yeah, okay, so it actually does have two ref clock inputs here for the two different internal PLLs. I'm trying to remember if you can drive these on, from different inputs, or yeah, I should go take a look at that and make sure things are set up properly. But you should be able to do that. I would just need to remind myself on the... Oh, right. So I think the Vivado tools are smart enough to kind of change the PLL clocking configuration and such, depending on, what's required for the actual input pins. So I think this one is for... I don't like their naming here, right? I think this is for QPLL 0 input. No, this is input 0 for QPLL 0. This is input 0 for QPLL 1. And I think if one of these has to go in through input 1 or something, based on, how the pins are connected on the PCB, hooking it up to the wrong pin here is not really a problem, as long as you're not messing around with the the input clock selection at runtime, right? If that's fixed, then the tools can figure it out. So I think I was able to use this exact setup to use one of the QPLLs for PCIe. So the Ethernet code owned the entire common block, and then the PCIe block was connected to some of the common signals. And there were a couple of additional connections required for that to work. So you'll see I have the PCIe rate in connections and the reset in connections, and I think those need to be driven by the PCIe block for that to work. So I haven't really extensively messed around with this, but yeah, you should be able to share it. Although obviously, you got to be careful about how you do that to make sure everything works properly. All right. So getting back to where I was, I have the AXI stream interfaces defined here. And this is the nice thing about System Verilog, right? Because each interface contains all of the, width settings and whatnot. So I don't need to pass in like 10 different parameters and, name everything appropriately. Okay, so that's all of the kind of top level logic, and then we have the actual wrapper here. And this one, you got a bunch of different parameters that you can set. This is not even setting all of them. There's, I think, a lot more GT parameters that I just omitted here because they're all defaults. In fact, I could even omit these probably. Then the settings down here are for the Mac and Phi logic inside. So there's quite a bit of configurability here. One thing that's relatively new is the low latency configuration here. So if you put it, well, let's see, there's low latency and there's also the data width. So the data width, you can pick 32 bits or 64 bits for the internal data width. And then the low latency configuration, it determines, in the low latency configuration, it will use the synchronous gearbox. And it'll put the transceiver in buffer bypass. If you put it in the normal latency mode, then it will run it with the asynchronous gearbox. And that will shave off a handful of nanoseconds, and also make the latency a bit more consistent. So if you're doing time synchronization stuff, then it's definitely useful to put it in the low latency mode. All right. So in terms of the actual Mac instance here, you've got the kind of top level free running clocks. There's an APB interface for transceiver control. Actually, did I define that? Yeah, I guess I defined it up here. I don't actually drive that with anything right now, but this one internally, it drives the transceiver DRP interfaces, as well as some additional control registers for controlling a bunch of other pins on the transceivers. And then we have the common connections here for the reference clock inputs. There's also the power grid signal, which is, what do you need to do with that? Oh, that one's driving this buff G. So, let's see. And then the rest of these are not really used unless you're doing the QPLL sharing. So yeah, serial data connections are here. And then the Mac clocks. So this is, well, clock and reset, right? So you can, there's reset inputs if you want to reset the channel, reset outputs for the downstream logic, and then the clock connections. And there's also an input for the PTP sample clock, which I will probably be revisiting that at some point, because that'll be related to the internal time synchronization. Let's see, and then we have the transmit interface. So this has the transmit data input and the transmit completion output. Then the receive data, same thing, that's just the receive data output. PTP clock connections, they're not used here. Link level flow control, priority flow control, all these other control lines are just kind of tied off for now. The statistics interface, is this actually, I don't think that's being used, right? I have that connected. This is one of the slight annoyances of System Verilog, is that you can't just leave an interface port disconnected. You have to connect it, even if you're not using it for anything. So in this case, I'm not actually doing anything with the statistics outputs, but they have to be connected here. Status. Most of these status signals are, I think, represented by the statistics setup. So unless you need to do something with one of these signals, you can usually just leave them disconnected. RX status is useful to put that on a light or something. So that one's connected. FIFO drop, this is an input to the statistics stuff. So that one needs to be at least tied off if it's not being used. And then down here we have all the configuration. So you can set the max packet length, interframe gap, turn the transmit on and off, and receive on and off, set the receive packet size. And then there's a bunch of stuff related to either the MAC control layer or the LFC and PFC that sits on top of that. So let's see. Then down below that we have the FIFO instances that are used to loop the channels back to themselves. So this one just kind of turns it into a loopback, right? We take the RX coming in, the TX going out, and there you go. Everything else is not connected. All right, so this setup right here will act like a loopback, and we can test this with a network tester and verify that it works. The other thing that I need is the PCIe interface. So actually, I guess one other thing I should show is how you actually use the this thing in the make file. So this is the top level file for the Ethernet MAC wrapper, right? So for this module, and I'm using .f files for this. I have a snippet in the make file which basically converts that .f file back into a list of, source code files. But this just makes things a lot easier because you can go through and, edit the .f file, and it basically edits all the projects that depend on it. I'm not sure actually how standard these .f files are. I think some tools might be able to handle them directly, but it's just a couple lines of make file or Python or whatever to expand this out. So it's a pretty convenient setup. But yeah, so that one pulls in the HDL, and then you also have to add an IP TCL file, and this one basically just gets sourced by Vivado when creating the project. And this one is for GTY transceivers running at 25G with the 156.25 megahertz reference clock. Pretty straightforward. So there's actually a whole list of these. If I just go into, where did I put that? Here we go. So there's a whole list of these TCL files, and really the only differences are the transceiver channel, right? GTH versus GTY, and then the configured link rate and the reference clock, right? So we've got GTH and GTY. These are for 10G, so the 32-bit configuration, and these are for 25G, so the 64-bit configuration. So these are all, well, let's see. So these are for GTH, these are for GTY, these are for 10G, these are for 25G, and then we've got the different reference clock configurations. Somebody asking, have I considered using FuseSock instead of a makefile build? I don't even know what FuseSock does. I don't know how it works. And I don't really like adding external dependencies unless I got a really good reason to. So, yeah, I've never looked into it, basically. And this just works great for what I do. The makefiles are very simple, very straightforward, very easy to understand. For example, right, this is, let's see, yeah, so this is the code that you need right here to handle these F files, for example. It's just, 5 lines of code, and that's it, right? This is the entire makefile here, right? How long is this? It's 150 lines, right? 150 lines that's shared across everything. And then for this project here, all of this is in terms of, handling the JTAG stuff. So this is only like, 40 lines. And FuseSock is what, some massive Python project. So if it does something unexpected, like I have no idea how to debug that and figure out what's going on. So there's something to be said for keeping things simple. And these makefiles, I think, are about as simple as you can possibly make things. Yeah. So, if there's a significant advantage to using FuseSock, then I guess I might consider it. But, I don't even know what it does exactly. So it's not something I've looked into. It would probably be a tough sell. Let's see. Right, so I have this. The next step now is to bring in the PCIe code, bring in the PCIe core. So I'm going to create a folder here for the TCL script for that, and now I need to copy that over. So I have created a couple of just very rough example designs for PCI Express. So we can copy some code out of here to get up and running more quickly. And a lot of this stuff was like copied from the Verilog PCIe and Corundum stuff in the first place. So there's not really anything special here. Right, so this is what we need to create the actual PCIe IP core. This configures a lot of the internal settings. So what I think I'm actually going to do is remove all of the bars that we don't need here. We'll just have one bar. Then I think I will, actually, I guess I should probably check. I want to use MSI initially because MSIX adds some additional complexity. And if we're actually going to be using interrupts, it's going to be a lot easier to do that with MSI instead of MSIX, at least in the short term. Long term, obviously, it makes a lot more sense to use MSI, or to use MSIX. Let me see here. So I'll go under that new directory I just created, and all right, PCI 4 Uscale +0. Okay, cool. So there is the TCL script that we need. It's configured for 8x8. RC straddle, I'm going to make that false. I don't think the current core that I have is going to be set up for handling that. Got all of this. Subsystem ID, subsystem vendor ID, that's fine. I'm going to delete all of the bars that I don't need. I'm going to delete all the MSIX stuff. And I may need to take a look at the MSI configuration. There's vendor ID, mode selection, GT selection. I think this is all fine. Oh, I'm going to change the device ID to, I'll make it C001. Okay. All right. So then what we do is we add that to the make file here. And this is pretty straightforward. I can just do a plus equals, and then that's a IP and PCIe 4. All right, now what I'm going to do is I'm going to go check the configuration of that in Vivado. We'll build this thing for 10G initially. Make sure it's all cleaned and ready to go. I'm not going to do the full build, but I'm just going to create the create the project file and import all the IP, so I can check the configuration of this and make sure that MSI is all set up correctly. All right. So while we're waiting for that, let's go ahead and add some of the other stuff that we're going to need here. Okay, so for PCIe, we need top-level ports here, right? We need the RX and TX connections and the ref clock. So we'll take that and we'll go ahead and, where should I put this? I'll put it at the bottom. Sure, why not? Yeah, so here's one thing that really annoys me about Z, right? This has got to be some sort of a bug. When I paste it in, it changes the indentation level, even though it's the same indentation level as this. So that's bug number one. If I shift tab that, look at what the heck it did with this comment. Like, what the hell? That's got to be a bug. So it's annoying fixing that all the time. I guess I should check to see if anybody's reported that, because it's kind of annoying. All right, so I'm going to go ahead and copy all of the PCI Express related code that I have in here for now. And this one is basically just setting up some parameters. And then it's got the AXI stream interfaces for CQ, CC, RQ, RC, right? All the stuff you need. It's got sequence number connections, yada yada yada. It's got the PCIe core has the iBuff DSGT4 external, so you need to instantiate that, and then you have the actual core. And then the streaming interfaces get passed into the core instance here. So most of this stuff, oh, I guess I'm going to have to go clean this up a little bit probably in terms of MSI versus MSIX. All right, so I will need to make a few more edits to this, but we'll go ahead and copy this over for now. All right, so let's see here. There's a plugin that does automatic SP formatting. Yeah, I don't know. Sometimes these formatting plugins are really annoying. If you have one idea about how you want a particular block to be formatted, and then the formatter just goes in and rewrites it, that's annoying. I've been quite annoyed actually by the Python formatter that Z uses by default, so I turned it off. Maybe I'll revisit that at some point. All right, so I'm gonna make sure straddling is turned off. I think that's parameter is not even used by anything right now, but okay. What else do I need to do? This stuff all looks good. We got all of that. Right, I need to check on the connections for MSI and MSIX. So, okay, this has gone ahead and made the product file, so I'll go ahead and open that up. Yeah, because I think all of these MSIX signals need to go away and get replaced with something else. So this thing really needs to figure out how to rescan this hierarchy correctly. Yeah, Z is nice, but it definitely has some bugs. Let's see here. So this is going to go under FPGA.gen. Oops. Do that. Okay, let me go into... Oh, this hasn't generated the core yet, has it? Okay, I see. I think that's the case anyway, right? Wait a minute. Why am I not seeing that PCIe file? I added it here. Oh, this is a 25G one. Hee hee. All right, let me open the correct file then, and we'll try that again. I go FPGA 10G and config.tcl and makefile. All right. So I just need to copy that line over here. All right, let me try this one more time. Okay, so we'll close out of Vivado. And I gotta go rerun this. Oops. Oh, there we go. All right, where was I? Need to copy. I need to make some adjustments to this, so we'll leave that there for now. Then we have the core logic, and for the core logic, let's see, what did we do here? So this one I just implemented. Oh, I put a an AXI Lite RAM. Okay, that's right. That's nice and simple. So the very stupid example design I put together just for kind of doing a sanity check on the PCIe side. I have the top level, PCIe clock and reset signals and the 4 AXI stream channels. So I'm going to go ahead and add that. Again, I'll put that at the bottom. There we go. All right, so I think I copied and pasted that in a way that Zed was happy with for some reason. So, okay, go figure. All right, so this has the same heartbeat code. And then we get down to, we have an AXI Lite interface for bar 0. And then we have the AXI Lite master interface here, which takes in the CQ and CC connections to the PCI Express IP core. And CQ and CC stand for completer request and completer completion. So we're in the completer role. When a request comes in from something external, we get handed that request on the CQ interface. This module then has to perform the corresponding AXI Lite operation and then issue a, potentially issue completion data on the CC interface. So writes are posted, so there's no completion. Reads are non-posted, so there is a completion. And there's, writes are not always posted. Memory writes are posted. IO and configuration writes are non-posted, and there is a completion for those. But we're only using memory operations for now, so that doesn't really matter. All right, and these signals I will need to revisit at some point, but that's a different story. All right, so that is the PCIe to AXI Lite bridge, and then over here we have just an AXI Lite RAM. So as you can see, it's just 2 lines to make that connection, and I don't need to pass any of these other settings in terms of the data width and the address width and whatnot. Well, there is an address width here because this determines how big the RAM actually is. So if you have a wider interface here for whatever reason, you don't have to implement that entire thing as an internal memory. So it's like in this case, I guess the address width is set to 16, but I think the bar size is 24 bits, right? So something like that. So yeah, I'm going to go ahead and, well, so I put the top level code in here, right? Okay, now I need to copy this stuff. And we'll roll with this for the time being, then we'll circle back around later on in a few minutes once we've tested all the interfaces, so we can try to get the driver put together for this test design. All right, so I've created the project. Let me open that up and we'll look at the MSI settings real quick. All right, let me see. Is Vivado opening itself up here? I guess it's taking its time. Okay, there we go. And let me also check to see if why does Vivado keep putting itself on top? Okay, so this one did pull it in, and we have those XML files that it created. All right, so let me take a look at this file, or the settings for this, and I need to potentially make some adjustments to the MSI settings. Thought I double clicked on that. Vivado, what are you doing? Yeah, recustomize. There we go. All right. Being slow today. All right. So frame straddle, that's turned off. Let me take a look at MSI and MSIX here. All right. So MSI, that's enabled. You might as well enable that, and we'll set this to 32 vectors. All right. Let's see. I think that's everything that I need here. The rest of this stuff is whatever. Okay. All right. I'm not in a hurry to upgrade to a new Vivado version. Yeah, so I'm actually running on an old version on purpose, just to make sure I'm supporting a wide range of Vivado versions. So yeah, at some point I'm definitely going to have to put a newer version on here. All right, so that looks pretty good. I'm going to go ahead and hit OK, I think. Yeah. Why is the core clock at 500 megahertz? I don't know why that is. That's interesting. So by 8 and 256 and 8 gigabit transfers per second. Yeah, all that looks fine. So, okay. We'll hit OK on that. Okay, so I'm going to go background here because what I'm interested in is the TCL that it ran, right? It runs a set property to change a couple of different settings. I'm going to skip the generation for now. So I'm going to go ahead and copy these settings, and I'm going to go back to the TCL script that I have here. So MSI enabled, yes, and then we can put those in like so. All right, there we go. So now we have all the settings here. Yeah. Newer Vivado versions sometimes bring weird bugs that break perfectly legal HDL. This is also true, yeah. You never know what you're going to get when you upgrade to a new version. Not only, you know, synthesis bugs, but also potentially things like IP core bugs and such. So, what are you going to do? Now, fortunately, I'm not using a lot of Vivado IP, but yeah. Okay, let me see here. So that's that. Now I need to do a couple things. One, I need to go ahead and add all these files to this design here, and I'll need to rerun the build again. But all right, so I think we got that already, and then I need, I think, all of this, right? The AXI stream, AXI Lite, AXI Lite RAM, AXI Lite master. Okay, we'll start with that. Okay, we'll go in here, and I'll just put these at the bottom, right? So AXI Lite, AXI stream. I probably don't need that one because I think that's already getting pulled in. and the AXI light stuff. Okay, great. Okay, so that's 4. And I'm about to make the exact same mistake that I already made just a minute ago, where I need to do this for both the 10 gig and the 25 gig versions. Okay, great. So let me go ahead and close Vivado for now. And I'm going to do a, oh, actually I did want to regenerate those files. Anyway, I'm going to, I'll just kick off a build. It'll fail, but it will generate those cores. Yeah, I'll just run make. All right. So what I'm interested in now is, the top level file for the IP. So when Vivado does its IP build, it's going to create a couple of files that are, let's see, it creates the files for the actual IP, which you can look at, and then it also creates a an instantiation template. And I need to check that one to figure out the MSI related signals. So, because I think all of these MSIX signals need to go away, and then I need to add some additional stuff for MSI. So that will take a minute maybe to get back to that point. We'll see. Yeah. So now, for those of you not aware, MSI versus MSIX, you know, what's the difference? So the main difference is just in terms of how the interrupt vectors are managed. MSI is managed entirely through the configuration space. MSIX, it has a structure in the configuration space, but all of the addresses for the interrupts, right, the vectors themselves, have to be stored in one of the PCIe bars. So if you want to use MSIX, you have to add some additional logic that sits in one of the bars and can store all of that. And you actually have to manually issue, memory writes to trigger the MSIX requests. Well, I guess on some devices you have to manually generate PCIe writes. I think on the Xilinx ones they do have. Well, I think that's what we're looking at here. Is let me see. It's address data int. Yeah, so you can provide the address and the data value, and then the int line is just kind of a, kind of a start the process signal that will trigger the generation of an MSIX interrupt on the host. For MSI, well, okay, so with MSIX, you can put the vectors wherever you want because you can set those to whatever values you want. For MSI, I'm trying to remember how it works. I think it's all a single address, but then different data values get written to that address. So some systems, will handle that a little bit differently. I'm not sure if there's systems that like only support one versus the other. I'm not sure if that's the case. I think it's relatively common for devices to support both MSI and MSIX. But yeah, from the standpoint of the PCIe core, it's a little bit easier to use MSI because basically the core handles everything, and you just tell the core to fire off 0, channel 1, whatever. For MSIX, you actually have to keep track of the addresses in the data. See if this is made. All right, Vivado is it's created some folders. All right, not done yet. All right, we'll give that a couple more minutes. Okay. Well, I guess while we're waiting for this, what I can start doing is putting together some of the, top level RTL that's going to be needed for Corundum. So let me think about this for a second here. So the idea is to have kind of a set of nested files, and the innermost one will be the core logic, and then the wrappers will add additional interface stuff. So the core logic will have basically just the data path and the register interface and whatnot, and then we'll wrap that with the with another module which will bring in the PCI Express DMA engines and such. So let me see here. Oh, is this all right? It finally went ahead and right, where are the files? Naturally generate that? I thought it would have generated that. Oh, maybe because it's not actually using it. All right. Let me go ahead and cancel that. I'll open up Vivado, and we'll manually trigger that so I can fix up the port list. Kind of important. How many times do we have to reopen Vivado here? Well, whatever. It is what it is. So, of all you guys using the new version of Vivado, are there any potential pitfalls to be aware of? I mean, obviously, there's always a potential for adding bugs. I've heard that they added a dark mode, possibly. Maybe I misheard on that. All right, let me go ahead and generate output products here. I did hear that one of the 2025 versions of Vivados breaks something related to system Verilog interfaces. So, yeah, I definitely need to test that at some point and figure out what the deal is, because that could be a pretty significant problem. All right, let's see. Going back into PCIe. All right, there we go. I think this did finally generate the files that I need here. All right, so we get several different components. We got the XML file, we got the XDC constraints, we got folders with a bunch of other stuff. But the one that I'm interested in is this VEO file, which is a, what do they call it? It's an instantiation template. There we go. Oh, here we go. It's the instantiation template. Yeah. So this has all the different signals and information about their configuration. So let's see here. I guess this is all the interrupt related signals, just like that. And I think that's what I need here. So I'm going to go ahead and comment out all of this for the moment, and I'll go ahead and paste those in here. All right, so I have these signals which are tied off, and then this is all in relation to MSI. So let me double check on all of these things. So we got interrupt MSI enable, MM enable. Okay, so most of these are outputs. So we'll set the outputs aside for now. The main ones we need to look at are the inputs. So we've got MSI select, MSI int, MSI pending status, MSI pending status data enable, MSI pending status function number, and then we got ATTR, TPH present, TPH type, TPH ST tag, MSI function number. All right, so let me try to distill down what all this is. I think MSI select, I was going to say that's to select the function, right? If you have multiple PCIe functions, but there's also a function number down here. So I may need to double check what that is. MSI int, these are for actually triggering the MSI channels, right? You give a pulse on one of these bits to fire off an MSI. MSI pending status. How does this one work? Right, I think this one just gets passed through to the PCIe configuration space. So from the software, you want to check to see if there's an interrupt pending, for example, before you enable interrupts. So this one feeds a register in the configuration space that can be read. Data enable, I think, is in terms of latching this value into the register. And then function number, I believe this also corresponds with this MSI select here. So this one is for actually issuing the MSI, and then this one is part of this updating the pending status. So because you get multiple functions, you pick the function here, you put the status for that function here, then you pulse this. It's something like that. And then these are status outputs, MSI sent, MSI fail. So you'll get feedback from the core. And then these values are going to affect what actually gets placed in the TLP that gets sent. So ATTR, TPH present, TPH type, ST tag, all of these are fields in the TLP. And then the function number is confusing me because I thought that would be determined with this, but I may need to look at the manual to double check what needs to be done there. All right. Anyway, I'm going to go ahead and copy all of these for now, and I'm going to comment out all this MSIX stuff, and I'll put that here, and we're going to go ahead and, all right, so I need all of these. We'll do that, and that, okay, cool. And I'll go ahead and clean this up a little bit. Don't need a bunch of additional white space. Gotta make everything look nice. Okay, so let's see, those are the MSI signals, and then I have them, they're all connected over here. All right, great. So that is the first step. And at this point, do I have all the pieces in place to test this? Maybe. Let's go ahead and give it a shot. Auto complaining about anything. Now that I've saved the files, I'm seeing here's the AXI Lightmaster, here's the RAM, here's the SFP instance here. That looks reasonable. We got the PCI Express core here. Why does it say it's running synth design? Maybe it got canceled in a weird way. Cancel that, and then we'll go ahead and make an attempt to generate a bit stream here. Right, so we can see this is set up for the board, right? XDKU3P. Okay, that looks reasonable. All right, so while that's running, let me see, thought I had another, okay. I need to go look up an example driver to take a look at here, so we're not totally shooting in the dark. All right, so put that away, and we're looking at this guy over here. All right, that looks like what I need. Okay, let me check a look. Oops, Otto is not happy about something. What's new? Oh, that's important. I forgot to add the connections in FPGA.sv for the actual interfaces. So I need to go locate that file again. That would be here, all the way at the bottom. There we go. Perfect. Okay, so we'll copy that. Then I will go ahead and paste that in here. And we'll see how that works. What, only 624? All right, so yeah, I guess that was the only issue here. All right, let me go ahead and hit this again. I mean, it'd be one thing if it was warnings only, but actually, where are these warnings coming from? So here's the funny thing, right? These are all from the out of context module runs. So that's 672 warnings from all of the GT Wizard and PCIe cores. Not even from my code, it's from Vivato's code. Great. Yeah, so there's not much I can do about those, right? I mean, what are any of these things here? Unused top level parameter. Really? Oh, wait, but why is it complaining about that here? That doesn't make any sense. Oh, I see. So these are, is this some sort of a Vivado problem then? Because these are set at the project level. So why is it trying to apply them to the IP core builds here? Right? So they're set here, right? 1, 2, 3, and then they're not used in the core. So I'm just trying to figure out, okay, if they were used in the core, for example, it seems like that could be a problem. I don't know. Not gonna think too much about it. RX data in is unconnected. Right, because you only use half of the pins. Or not even half of the pins. Yeah. Oh, are those the only warnings? That's interesting. Yeah, I guess they can be suppressed, but it's like, it's is it worth the effort to go through and suppress all that? 101 critical warnings. Uh-oh. Unknown option ICT. Uh-oh. Oh. Okay, that needs to be fixed. Big management. What is this complaining about now? Unconnected pin. Big management address. Is that, let me just see here. Is this just because I haven't connected these things yet? Yeah, I guess so. Alright. So we're just going to have to ignore those for the time being. And all of these are going to have to be tied off at some point. Or pass through. So, alright. Critical warnings, you always got to at least take a peek at, just to see what sort of thing it's complaining about. Okay, so I think that's probably going to be complaining about that pin later. So I'm going to go ahead and reset the run. And we'll rerun that. Okay. It takes a few tries to get this to work. So in the meantime, I'm going to let this run over here, and we'll start taking a look at the driver. So I'm sure this is something that people are interested in, is how do you make a PCI Express device driver? So we're going to create one from scratch, and then we're going to extend it and make it a proper network device driver. So I'm going to go ahead for now and just create a modules directory here. And then we'll go ahead and create a test driver in here. So what am I going to do? I'll just start with the, and then we can work on that from there. I also need a makefile to build it. That's kind of important. All right. Go up to that directory I just created. Yeah, some of the stuff I'm gonna have to clean up later in terms of the exact directories and such, but you know, one step at a time. All right. Just check on Vivado. How are we doing? No errors yet. All right, so what do we need for a module? So the thing with, actually, let me create the makefile really quick here. So this one, let me go ahead and copy this over from the, oops, that didn't work. All right, something funky is going on here. All right, so what do I need in this thing to actually work properly here? I need that. It'll take a minute to transfer this over. All right, install. Oops. Okay, and then I also need to set the KDIR. Lib modules. Then I do. Okay, is that everything that I need? No, there's more. Okay, I need to do objm. I think I do test mod.o. Alright, so the idea with this thing is it's going to tie into the kernel's build system. So that's what this command is for, is that it's going to run in the current directory. We're going to build the module in the current directory, but it has to run this inside of the kernel's source directory. Yeah, so that's what this is. It takes the current running kernel and says, okay, we're going to build that, or we're going to build for that, and we're going to run, you know, make modules, or make all modules. So we're going to make the modules, and then we'll be ready to run that. So let me see. We need to build this on that other computer. Where did I? Okay, there we go. One moment here. Actually, all right. So that probably needs a minute to figure itself out. But what we're going to do is get set up to build this on this development machine that I have here, because that's where the card is going to be installed. Okay. So I think this is what we need for the make-file. I'm not 100% sure at this point. Let me actually see if I can do a I run make here, what happens? Okay, well, it complained because, why did it complain? Missing module license. Oh, yeah, okay. So it did try to build it, but it failed because we're missing required stuff. So let's go ahead and take a look at that and try to put in all of the required components. All right, so we have the module here, and we need to go ahead and add a bunch of stuff here. So I think we need include Linux module.h, and then we need to set, what does it say we needed? We need module license and module description at least. Oh, all right, Vivado failed on something. We got bitstream generation failure with some critical warnings. So what happened? Unconstrained logical ports, but why did that happen? Not set lock property of ports. So what is the conflict? Oh, okay, I see. Okay, I think I may need to change something about the PCIe core configuration, because I think this is putting things in places where they're not supposed to be. Let me see if I can figure out what happened here. This is the first time I've tried building the design with both the PCIe core and the Ethernet Max, so it's in some sense not surprising that it's complaining about something. Alright, so we're going to take a look at the pinout that Vivado actually used. So we can go into FPGA.runs, and I go into implementation, and there should be an FPGA, where is this, IO placed. Alright. And so this put the PCIe pin, so if we say look at TXN3, that put this on quad 225. TXN3, I mean, that looks correct. But I've had this happen before, where if you've accidentally tried to place two different cores on the same pins, Vivado can do weird things where initially it will report some sort of placement constraint problem, and then it will move one of the cores. So I think what might be happening is that the PCIe core configuration is trying to put this in a different location. What am I looking at here? Hang on a second. Okay, so what I suspect I need to do is change the core location, the GT quad here, right? So this says 227, and actually that could be the problem, because in the XDC file, yeah, this is using 224 and 225. Yeah, so we have a constraints problem where the core here for some reason was set to 227. And if you're only using the PCIe core, it figures it out. If you're using both of them, then it complains. Actually, let me just see if I turn off the GT quad selection. Okay, so the default is 227. All right, but that's not what we want. So let me go ahead, open this up again. Let me change this to 225. I hit OK, and I will need to update the TCL script for that. Let me see here what I need to edit over here. Okay, I'm going to skip that for now. Go to TCL 225, right. GTY quad. What's that? Oh, so there's a master GT setting. I guess that's not even in here, is it? Alright, so I gotta copy the whole setting over. Cool. I don't think I need that one either. Okay. Alright, so let's go ahead and I'm just going to resource that file. Actually, I can't source the file at the moment. I need to remove this first. Or, yeah, I'm just going to make sure that we're doing this correctly. So I'm going to go ahead and, well, no, here's what I'm going to do. I'm going to close Vivado, and I'm just going to do a clean build of the project. And we'll see what that does. Yeah, all right. Let's see what that does. So the problem was the configuration, or I think the problem was the configuration of the PCIe IP core itself. This is just one of the issues sometimes of dealing with these wizard-generated cores, is they have internal constraints. And basically what happened in this case is that you get the core applying one set of location constraints and the project XDC file applying a basically a conflicting set of constraints. And then Vivado gets very confused. All right, so we'll let that run and see what happens. At any rate, let's take a look at the module. So I need to create a... There's a whole framework that Linux uses for building these modules. So these are macros, and I'm not sure exactly what happens in the background, but my understanding is that these end up in well, they're either used by some of the other code that gets built into the module as boilerplate, and or they end up in additional sections. A kernel module in Linux is just a shared object file, basically, and it has some additional information in it that's used to determine whether it can be loaded for a particular kernel version and such. So we need a couple of these directives, right? This is complaining about module license and module description. So I'll just put GPL for now. So we've got those two. And then we need the core of the actual module itself. So for those of you who've written, normal C programs, you'll know that there is like a main method that you need to call at some point, or well, not that you need to call, but that the operating system calls when you run the program, and then everything that you do is in the main method. Drivers are a totally different ball game, because your driver gets loaded into the operating system, and then you basically want to spend as little time in your driver as possible. So the operating system will call into your driver under certain circumstances. And what you need to do is register the entry points with the driver. So there are a couple of entry points that are defined here. These are basically static definitions here. Oops. And these are responsible for the module loading and unloading process. So these definitions are going to be used by the shared object or by the kernel for locating these functions. Let's see here. And I'm going to try to use the kernel's coding style here. Oh, well, all right, I need to mess around with Z to figure out how to do some of this stuff properly. One thing that I've noticed about Z is that it doesn't have very much like per file and per project configuration stuff, which is slightly annoying, but what are you going to do? All right, so these are the entry points for setting up and tearing down the module. And what we can do in here is I think we can call like a print K. Let's see, what is the funny thing is I never really call print K directly. So, or should we even bother with that? Nah, I'm not even going to bother with that. We're going to go ahead and go straight to creating a PCI Express driver. So init is called when you load the module. Exit is called when the operating system attempts to unload it. So we're going to use these to register the PCI Express driver with the operating system. When you've registered the driver, then the operating system will sometime later, when it scans the bus and looks at all the devices, it will then attempt to attach that driver to a matching device. So let me go ahead and explain exactly how you do that. So first we need to create a structure to define the driver, right? So we have set extract PCI driver, something like that. And then what we're going to do is we're going to set the name. See, how did I have that defined here? All right. I'm just going to call it, for now, I'm going to call it that. And then we need a couple other pieces of information here. So I need to create an ID table, right? And then there's going to be a couple of entry points here. In particular, we need probe and we need remove. All right. And then we're going to go over all these here. Okay, so the ID, so this is defining the, well, probe and remove are entry points. Name is just a string defining the name. And then ID table, this is how the Linux PCI subsystem will determine which driver to attach. Every driver, well, the nice thing about PCI Express is that it has the configuration space, which exposes, device IDs and vendor IDs and that sort of thing. So we can create a, so every device, it needs to match, or every driver is matched to the device based on those IDs. And that is the same for every single device. So instead of having each driver do its own filtering, it gets handled by the kernel in kind of a standardized way. So what you do is you define a structure that has the IDs that you want in it. And then the kernel will go through and do the matching. Let me double check on Vivado here. How are we doing? It's still running. All right, hasn't failed yet. Okay. So the structure that you need to define looks like this, and then it ends with a 0. And then we have PCI device, and then you specify what did I set? Was that C001? Yeah, all right, so we'll see about that. Okay, perfect. I'm gonna put a comma here, and then we're good to go. What is this complaining about? All right, whatever. That doesn't matter. Oh, I may need to import some additional stuff, perhaps. Do I need to import something PCI related? I don't know. Well, we'll see. If it complains, then we'll fix it. But, oh, I probably need that. Okay. But I think this is a starting point for the driver. All right, so the next thing I need to do then is to implement the probe and remove methods. So let me take a look at what those need to look like really quick here. All right. All right, so this is what the kernel calls when it is trying to attach the driver. So, oops. Let's see here. Oh, so I'll call that pdev, and then select PCI device ID entry. Okay. All right. And then we need one more for the remove operation. Where is that? All right, so we do that, and then I need to put both of these over here, right? There's your probe, and there is your remove. Okay. Now what we can do is print some information here in terms of yeah, all right, so dev info, I need to do pdev dev, and then we can see this in the messages, kernel messages output. I think that's all we need here. Okay. And then the last thing we need to do now is to register the actual PCIe device drivers. So we can do return PCIe register driver, and then I need to provide this thing here. Okay, and then similarly to unregister it, we do the same thing here. So PCIe unregistered driver. Okay. I think that's everything that's needed here. Let me see if this builds. Okay, so something is very unhappy, probably because I have forgotten to do something. Oh, actually, so yeah, I probably need to include some additional stuff because the file that I'm looking at here includes some other header file which probably pulls in a bunch of things. Yeah, so I think you're right about having to pull in PCI and probably other things. Third inside parameter list. What happened? Alright, so I think I need to include kernel.h and PCI.h. Let's see what that does. Okay, that was a lot better. No return statement. Okay, that's fine. Test. Oh, this should not be int, this should be void. Hey, there we go. So I was just missing a couple of those includes. Alright, so that went ahead and built the module. Now it's not going to do me much good to do an insmod here. What I need to do is do an insmod on the other machine. Let's take a look at what Vado is doing in the meantime. Okay, so it has completed the first pass of routing. That's good. We'll see if it actually builds the whole thing this time or if it blows up at some point. All right. Something is not working in terms of my file synchronization setup right now, but that's okay. I'll just have to rsync this. Let's see here. All right, let me see now. Okay, so this is running on the other machine. Actually, I'm going to do one more thing here. Actually, now that I think about this, this might be kind of pointless until we actually until we actually have the card properly enumerated over there. So this is the D-message output on that machine. So I'll just leave that up for now. And I guess there's not much I can do with this until we have the design from Vivado. So right now it's doing the bitstream generation right now. So that's... Did it fail before or after that step previously? It may have failed during bitstream generation at DRC, so we'll see. All right, let's take a look at what's on this thing. Oy, there's a lot of stuff. So there's a couple of specific devices to look at here. We can see Ethernet controller. This is the Mellanox NIC that's installed. That's the other FPGA. And this one, I think, is the default configuration of the whatever firmware is loaded on that by default on the the Alibaba card. So let me just take a look at using LSPCI. I need to do sudo. I can look just at that card. Okay. And the main thing to look at here is the link status. It's up at 8x8, so that's good. And by default, it has 2 memory regions. This is 2K, and this one's 512 meg. So actually, okay, this went ahead and generated the output files here, so it didn't fail that time around. Let me see. If I do make-n, that looks good. Do make program. I hope this works. I think I have everything plugged in. We got the JTAG cable plugged in. I got a green light on there, so that's good. All right, that's that'll figure itself out in a minute. Okay, now it's talking to it. Yeah, I can see the device. Okay, it's programming it. All right, so now I need to reset this thing. Well, not yet, but very soon. Oops. I need the PCIe ID here. Now, for those of you not aware, these IDs are the bus device and function numbers. So in this case, it's bus BE device 0 function 0. And I see. It copies things when I select it, which is actually kind of annoying. Okay, so that's gone ahead and finished that. So let's see. So it should be programmed. It should be ready to go now. Let's see what happens if I reset the device. Hey, there we go. We can see it. It was detected. There's the vendor ID and device ID that we set. Type 0, class, whatever, PCIe endpoint. And here's the bar 0. And it was assigned. All right, so that's perfect. So I can take a look at this again. And we got, well, it's not an Exablaze device, but whatever. That's, I think I copied the PCIe configuration file from one of the Exanics and didn't change the subsystem ID. Okay, well, whatever. I'll deal with that at some point. Okay, and we can see over here, MSI, right? Count 1 of 32, maskable, 64-bit. This has not been configured yet by anything, so it just reads as all zeros. And we have region 0, right? We have 16 megabytes of address space, and there is an address assigned, so potentially this should be usable. And if we look at capabilities, we can see it is up at 8x8. So there we go. We do have the PCIe link working. Now, what I'm going to try doing here is let's rebuild this module, because I SSH'd it or rsynced it over here. So testmod.ko. All right, so we're going to insmod that. Ah, crap. Oh, wait, never mind. That's fine. Yeah. I thought I have to turn off signature verification, but actually, no, this is fine. So we can see that it detected the device, and we see our, we see that it probed, right? This thing ran. So it was able to successfully attach to the device. And now we can go ahead and run rmmod, and we can get rid of it, right? Rmmod, it's removed, right? So, great. It's not really doing very much, but there you go. That's a start, right? This is the general framework that you need for making a PCI Express device driver. Now, obviously, it doesn't do anything yet, but we got to start somewhere, right? We can connect to the device. Okay, so the next thing to do is to map the bar, and then we can actually access it. So in this case, the bar is just viewing this little memory that we've added. So what we need to do now is, I need to remember how to do this properly, but the idea is to set up the mapping for the bar so we can actually access it. And I think there's a couple other calls that need to be made as well. So let me take a look at this other. I'm at the moment I'm looking at the legacy Corundum device driver to remember what needs to be done for everything to work. So we have the probe here, and then let me see here. This is all just printing information. Oh, all right, this is useful. So I'm going to do PCIe print link status dev. All right, so that will print some useful information about the link. All right. This driver is a little bit more complex than I thought, perhaps, because this calls. Maybe I need to look at a different. Here I am trying to get creative, and now I'm not exactly shooting myself in the foot, but okay. So this one was doing what? All right, I need to look at a different file here. This one, the problem with the legacy Corundum driver is that it uses devlink, which adds a bunch of additional stuff on top. So let me pull up a simpler driver that I will look at instead. Oh, I didn't want that one. I wanted oh, that folder. All right, cool. Okay, this one should be more straightforward here. All right, where was this thing? Okay, so what we need to do is create a structure. All right. It's very common in device drivers to have a like a private data structure that you can use to put information in for use later. So I'm going to go ahead and create this thing, test dev. All right. And then this is going to be, I'm going to put the PCI Express device here and the device reference, because those are quite commonly used. Okay, and then I will do void iomem. I'll put the bar here. Okay, there's the bar size. And I think that's everything that I need for now. We'll see about that. And then what I need to do is, okay. I just got to remember what all needs to be done and in what order. So what I do now is sure. This is going to be, well, I shouldn't alias the name. Yeah, okay. All right, we'll do that. Devm. We have to allocate space for our structure. And the cool thing about this devm kzalloc is that the kernel keeps track of the allocation for you, so you don't have to remember to free it yourself. All right, so we'll do that, and then I need gfp kernel. Okay, great. And then I also need to define this td thing here. All right, we do that, and then if this didn't work, right, if we're gonna fail. All right, there we go. And then we can go ahead and set some of the parameters here, right? So this is pdev, and then td dev equals, let's see here. Okay, great. So now that we have that, then we can take the next steps of actually enabling the device and such. So let's see here. I need to do all right, so I'm going to go ahead and create a return value here, int ret, and then at the bottom we return ret, I think. All right, so what we need to do now is ret equals PCI enable device. Oh, mem, there we go. All right, and bottom we're going to return 0, but if this fails, in the kernel you have to do a lot of error checking. So we got to check to make sure this worked. If it failed, then we do dev error. Oops, dev error, and this is going to be dev comma failed to enable device. All right, and in that case, then we do go to fail enable device, and that goes down here. All right, so that enables the device. Do I need to do anything else? That let me make sure that's correct. Okay, cool. And then we need to do, similarly, when we remove it, we need to do PCI disable device. Yeah, okay, cool. So we do that, and then we need to do PCI set master. All right, I apparently have a visitor. Houston, are you gonna come here? There we go. All right. Let me see. Let me turn on the cat cam. Boom. There we go. Okay. Great. Houston, you want to be here? You gotta be not disruptive. Okay. Okay. Great. All right. So we do the disable device here, and we also need to do clear master. PCI clear master. Dev, and then I'm also potentially going to need to do these here, depending on whether other stuff fails. So this is kind of a standard format for writing drivers, where if something fails, you need to do local cleanup here, and then you also need to do basically the same cleanup when the device is removed. I actually don't know if there's maybe a better way of specifying this, because the lines here are going to be basically the same as the lines here. So yeah, I don't know what to do about that necessarily, but this works well enough. All right. Where was I? Right, so we do set master, and then I need to do request regions as well. I'm actually not sure off the top of my head exactly what requesting regions does. I think it's something to do with how the kernel is managing the bar space and a few other things. But yeah, so all right, so with set master and also with enable device, this is going to be twiddling devices or twiddling bits in the configuration space on the device, both to enable the memory space so the bars work, and then set master, it enables the device to perform DMA operations. All right, so let's see. Ret equals PCI request regions, dev, and then we need to put the driver name. I need to create a macro for that. That would be useful. If ret, oops. All right, then I do dev error dev. All right, do that, and then we do go to fail regions. Right. Okay, and this is going to be over here. Okay, and then I need to check what we need to do to release those regions. All right, just PCI release regions. All right, cool. So there's quite a bit of boilerplate code you need for this to work. Okay, because we haven't even mapped the bars yet. Okay. So we've enabled the device, we've set the master, we've requested the regions, then we need to map the bars. Let me check on the correct way to do that. All right, so for this, we're going to use the PCI IO remap bar call. All right, Houston wants to run off. Cool, let me turn that off. Okay, cool. We're going to call a couple different things here. So I'm doing two things. I'm going to map the regions, and I'm also going to save some information about the size of the region. So you see I have bar and I have bar len. All right, so PD bar len, this goes to PCI resource len, pdev, comma 0, so we want the first bar, and then we want to map it. So let's go and print that information out. Dev, and then this is going to be, oh, actually, I guess I have a, oh, no, I don't have a dev reference here. All right, cool. Let me just create that real quick. Struct device dev equals pdev. Oops, I want to do pdev dev. All right, now I can use dev instead of that, and also here. All right, great. So dev info, I'm going to say bar size %LLU, and then I can put td bar len, and that should be, when we run it, that should print out 16 megabytes basically. All right, and now td bar, that's going to be set to PCI IO remap bar pdev 0. Right, we're mapping the first bar. So this will get us an address that we can actually use, because we can't directly access the physical address space from the card. Oh, hey, we have another cat dropping by. Let me turn the cat cam back on. Boom, there we go. That gonna work? All right, here's Maji. Not actually taking a nap at the moment. How you doing? All right, but he's just passing through. Okay, great. Turn it off again. Okay, so this is how you turn the physical address of the bar that's configured into the device into an address that we can actually use in the driver. All right, so we do that, and then if this fails, let me see here. If not td bar, that means it failed. So we do ret equals mem, and then we do dev error. Failed to map bar 0. All right, cool. And then we go to fail map bars. Okay, cool. Let me see here. So this is going to be fail map bars, and then what I can do here is if td bar, yeah, then I can do PCIe unmap dev. Okay, cool. And then I need to do this down here as well, right? So again, Z is indenting that wrong. That's annoying. Okay. So I think I have most of the stuff in place. I guess I also need to enable interrupts potentially. Let me see here. That done. Okay, there we go. So allocate interrupt vectors and then set up interrupt. Okay. Well, I'm not going to set up the interrupt yet, but I will go ahead and do all of the initialization for that. So that's mapping the bars, and then to set up the interrupts, we do ret equals PCI alloc IRQ vectors. This one will allocate either MSI or MSIX depending on what's available. Let's see here. Okay, and then this one will go to fail IRQ. Okay, and then over here I have fail IRQ. Oops, I need a colon, and then down here we also need to do the same thing. Well, not so much the same thing, but we need to free the IRQs here. So PCI free IRQ vectors. And I need to do that down here. Oh, I need to do that there. Okay, great. So let's see what happens if I try running that driver. So let me go ahead and rsync that. Okay, that's rsynced over there. Now I'm going to go ahead and do a build. Oh, dang it. I should have tried that earlier. All right, let me see. Test mod PCI probe. Oh, I need a semicolon here. All right, let me try that again. For some reason, this thing is not accepting my my password, or rather, it's not accepting the what am I trying to say here? It's not accepting my public key, so I got to keep typing my password. It's kind of annoying. I got to sort that out at some point. Okay, that is complaining about this. So what I need to do here for the proper removal is to get the private data. So we're going to do, I guess I might as well copy both of these lines down here for now. And then that means we can just use dev instead of this. And then this is going to be set to PCI get drv data pdev. Okay, so that returns the rsync it again. That returns the structure that we previously allocated. Okay, there we go. And then I do that. And that worked. Okay, great. So let's see what happens if I insmod that. Oh wait, I've been building this locally, haven't I? Where did I put that other? Did I close that window? What happened? Okay, I don't know what happened. So let's go ahead and, oops, I need to do that. Build it. There we go. And now I can insmod it. And there you go. We can see it called probe. It printed out the information about the PCI Express link, right? We're going at, about 64 gigabits per second, 8x8 link. It enables the device, and there's the bar size. And this should work if I RM mod it. Oh, crap. Okay. What did I do this time? So something obviously didn't work correctly. What did I screw up here? So we did PCI free IRQ vectors, yes. IO unmap, yes. Release regions, yes. Clear master, yes. Disable device, yes. Okay, that all looks reasonable. Allocate IRQ vectors. And I don't think that failed, right? It printed the bar size, so... Yeah, PCI device removed, driver detached, bus removed driver, unregistered driver. Where specifically did this crash? Kernel null pointer dereference. Yeah, it's just unclear exactly what line triggered this. Exited with IRQs disabled. Yeah, so it crashed in PCI device remove. Okay, that's great. But which line was it that was the problem? Did it print remove? Yes, it did. Okay, so we're good to that point. I wonder if maybe... Well, no, but it wouldn't be... I'm just thinking if it's this IO unmap, if something was null at this point, that could be a problem, but this one was checked. This one has to be not null for that to work. And then the rest of these, I think, are all correct. Let me see here. PCI IO unmap. Yeah, so that should be correct. Uh-oh. Okay, so PCI plus 30 test mod. Yeah, this is not really giving much information aside from it failed in that call somewhere, but not specifically which line was it that was the problem. Yeah, and that's also interesting. It's not indicating anything other than PCI device remove. So it's not like it failed in, well, alright, so driver detached, PCI device remove, but where is my call coming from? The ampersand before... No, this is fine. And the reason this is fine is because dev is embedded in pdev. So you need the ampersand, otherwise it won't compile. If dev was a pointer, then that would be fine. So dev is fine, but maybe the problem is pdev. No, it wouldn't be pdev, because that's... Is it possible that td is, for some reason, null? I don't know why that would be the case. Oh, unless I need to set something and I didn't do that. I've been looking at like 2 different drivers, so it's possible that I've missed something important here. Alright, I suspect that might be what happened. Yep, I missed exactly 1 line here. So yeah, the problem at this point is that TD is null because I never set the driver data. Yeah, so this is... I was going to put that right here. PCI set DRV data, and that's pdev and TD. Alright, cool. Now I need to reboot this machine because it's hosed. So, did I have my my hard reset script on here? Yes. For those of you wondering, here is how you hard reboot a machine, even if you know it's going to hang during reboot. Let's see. That should work, hopefully. I'll have to give it a minute. Yeah, so it's definitely crashed now. It's definitely down now. This little script here has come in very handy. Whenever I, totally screw up a driver and crash the machine, but it's still working well enough to run a command via SSH, this is what you can do to basically push the reset button, because it will automatically, like, instantly trigger a reboot. It doesn't do any, kernel, anything to clean things up, shut things down. But, at that point, once you've made the kernel panic, there's really not much other choice you have. And maybe there's an easier way to do this. I don't know. But this works well enough. Alright, well, we'll wait for that to reboot. And this, again, is why you don't do PCIe or really any driver development on your local workstation. Because you never know what you're going to screw up, and then you'll have to reboot the whole shebang. So yeah, if I was doing this on my workstation, that would screw up the stream and everything, so that's not great. Alright, so there's that. Alright, now I need to do, what was the command? Tilde dot, there we go. So log back in there. Okay. There we go. Oh, the kernel was corrupted or uncleanly shut down. I wonder why. Alright, let me go ahead and rsync this again. Okay, there we go. And now I can do make. Oh. Alright, we insmod it. Okay, and now, is it going to crash this time? I hope not. Hey, there we go. Perfect. Okay. Yeah. Alright, so Tobias says, yeah, it's the alt sysrec magic. Well, I shouldn't run that on this keyboard because that would reboot the wrong computer, but yeah. Actually, do I even have a sysrec key on here? I don't think I do, so I couldn't even do that on... I couldn't do that on here. The keyboard that I usually use on these other machines, let me check. Yeah, I don't see a sysrec key on here either. Interesting how these old keys kind of disappear after a while. Although I don't know, maybe it'll be replaced by the Microsoft Copilot key or something, right? What are you gonna do? Okay, so at this point we've mapped the bar. Now we need to do a test read and write. Okay, so let me take a look here. The way you do that in Linux is you do IO read 32 and IO write 32. So what we can do is let me copy this for a second here. I'll do dev info, do a write to bar 0, and then I will do IO write 32. We'll do a 32-bit write, and this is going to be okay, so we do the value, and it's what and then where. So we can do, right, something like that, and then I can do td bar. Yep. Okay. And then we can do a read. Happens Z being annoying. Okay, then I can read from bar 0 here. So read from bar 0, we can do that. We can do IO read 32, and this is going to be again another dev info. Actually, I guess I can do U32 value equals that, and then I can print that. I think that will work. Just make sure it builds first before I SSH it. Okay, that does build, so we'll try that. All right, so now I will rebuild it, then can insmod it, and there we go, right? We read the value that we expected from bar 0. So that means the PCI Express interface is in fact operational. All right, so we've confirmed that. Somebody said that we could use devmem. Yeah, we can absolutely use that for testing, but the point here is that we're going to be doing everything in the kernel anyway, so it makes sense just to test the basics you need for the driver. Yes, I could have used devmem and saved a bunch of time here, but we're going to need these, you know, building blocks for making the NIC design as well. So, you know, one step at a time. Okay, so we've tested PCI Express interface. Now let's test the Ethernet interfaces on these things. And for these, I'm going to use my my network tester. So, me a second. For my microphone is happy here. All right. Go ahead and switch now to the camera view here. And where did I put my network tester? Okay, there it is. And I configured this for 10G, I think, right? Okay. This will take a minute to boot up. These are a little noisy, unfortunately. Hopefully it's not too bad. Keep that card over. Okay. All right, and now I will get a cable. We'll hook that up to one of the ports here. All right. And this is going to go to port 1 on this guy. All right, I guess that'll take a minute to boot up. But yeah, this setup will allow us to test the loopback and make sure that the MAC and PHY logic is working correctly on the NIC. Little fan here, that's still running, so that's good. Yeah, I don't know what happened to that other fan. Just randomly decided to die. I don't know what happened. Anyway, whatever. Yeah, downside about these Viavi units, they are, well, the software in here is like all written in Java, and it takes ages to do anything. All right. And this is probably going to load a couple of 100G tests, which will take a minute, and then I'll have to switch it, but step at a time. Come on. I guess it needs some more coffee. Well, we'll just let that run for now. When that's ready to go, we'll switch back to it and take a look at it. Kind of annoying. All right. We'll switch back to this for now. When the tester is ready, then we'll go ahead and test the Ethernet side. So we've got the PCI Express side working. Ethernet side, we'll figure that out in a minute. Okay, that's now initializing the whatever test I had loaded up before. So in a minute, we'll get that set up for operation at 10 gig and give that a quick test. All right, so that's the basic driver for PCI Express. Now, to do Ethernet, in terms of interfacing with the operating system, what we need to do is register what's called a network device, or a net device. And this is done basically after you have the PCI Express device set up. Then you can go in and register the net device. And the net device is another set of entry points that you have to declare that interfaces with the operating system in terms of being able to transmit network packets. And for reception, I'm going to have to refresh my memory a little bit on how all this works. But the idea with that is that there are operating system APIs that you can use to hand packets off to the network stack for reception. So you'll have to register an interrupt handler and whatnot in order to be able to take advantage of that. All right. So while we're waiting for this tester to set up, I guess there's some other infrastructure code that I can start putting into place, so we're ready to get cracking on the NIC design. Let's see here. What did I need to do? Right. So for right now, I don't have any. All right. So I don't need that. And I don't need that. And which one is this? This one is, oh, that's the current one. Yeah, okay, great. That's not doing me any good. I can get rid of that. It helps to try and clear out stuff that doesn't need to be open. All right, so here's the IO placed. That's, yeah. So if you'll notice, Vivado eventually placed this on the correct pin, but it failed previously due to the constraint problem. So, well, rather, it still placed it on the correct pin despite the constraint problem, but there was some other error that it created. Right, I guess it unplaced the SFP sites because of that error, and then subsequently failed. Great. Oh, and Tobias is saying that devmem is not always enabled. Yeah, I actually don't think I've ever used devmem personally. Actually, there's another tool that you can use. So I think devmem is something that's disabled on a lot of devices, although people like using it on Zinc devices because it's very simple. But there is another little utility you can get. It's not it's not part of the kernel. It's a separate little utility that will allow you to poke at like PCIe device bars. And that one, it basically just does nmap from user space. Yeah, so I've used that a couple times myself. I can't remember what it's called at the moment. All right, let me take a look at the network tester. Actually, I need to step out for a couple of seconds here. I will be back in like 2 minutes. Okay, all right. Let me go ahead and get this thing set up here. Oh wait, it seems to be already set up properly, perhaps. We are getting our... Oh, never mind. Something else. What is this complaining about? Okay, so this is on port 1, and I want to go ahead and switch this over to 10 gig layer 2 traffic. All right. Like I said, this thing takes a couple minutes to figure itself out. Now the card is giving me a little light indicating that that link is up. So that's a start. This just needs to finish loading the software here. Okay. So there we go. Link is up. So I can go over to actions and turn on the traffic, and there we go. So this is with 512 byte frames, and we can make it minimum length, right? 64 byte frames. Takes a second. There you go. Full line rate, minimum length frames, no problem. This can go up to jumbo, I think, right? If I put that on jumbo, do 9,000. There you go, jumbo 9,000 byte frames. That works just fine as well. So Ethernet side is working. So that's one port. Let me check the other port. Make sure that's good. Hit the restart button. It looks good. And there you go. So both ports are doing what they're supposed to do. I'll switch this as well back to minimum size frames. And you'll notice here, I don't know if this is readable on the display. On this little bit. Okay. Get a slightly better view of the network tester. You you can see that with minimum length frames, the L2 throughput is significantly reduced because of all of the headers that need to be sent. So yeah, it's saturating the link, but that's the throughput you get with the payloads. It's a lot less. Yeah, so I think what Tobias is saying is that if devmem is disabled, then devmem doesn't exist, so you can't use that technique. So the problem, I think, with devmem is that it just gives you such low-level access to the system that it's, you know, partially a security concern and partially just dangerous. If you poke the wrong thing, it can cause a lot of trouble. So on a lot of systems, the devmem thing is disabled. It just doesn't exist. I guess I can check on these and see. But maybe not a bad idea. Anyway, there's not a lot else to do with this network tester, so I'm going to go ahead and get this packed up for now. And then we can take a look at the making this thing actually work like a NIC. I'll take a quick look at see if devmem exists on these computers here. So let me turn off this network tester. This thing is really loud. It's quite annoying. Okay. Yeah, put that away. Okay, great. Let's look back over to this guy. Okay. Oh, this is in some weird order. Okay, there we go. All right, so if I could do ls dev, is there a mem in here? Oh, there is a mem. Interesting. I actually have not tried poking around at that. Is dev mem actually a Yeah, there's also a dev mem. Oops. If I can click on the right thing, there's also a dev mem on my computer as well. I'm just wondering if I've never actually tried using that before. My understanding is that either it's kind of neutered or it's not fully usable. I'll have to take a look at that. Yeah. So, well, this is both on Ubuntu. So, hang on a second. Actually, both of these machines are running Arch Linux. So, Arch at least has it turned on. I'm trying to think if there's an Ubuntu machine that I can poke at. Yeah, I don't have any devmem utility installed. If you know what the package is, I can try installing it, and we'll see. But I don't know what the package is. Let me take a look here. Let's see. Oh, I guess maybe it's just in the Arch user repository. All right, so I'm going to install it, and we'll take a look. All right. Okay, so what did we see from... Actually, so two things I need to do. One, I need to make sure the driver is not loaded, just to make sure we don't have any problems there. It is loaded. So sudo rmmod test mod. Okay, there we go. It's removed. Okay. Now I need to take a look at LSPCI, right? Yeah, okay. Oh, this shows up as a memory controller because I didn't change the class code. Anyway. Okay, so this is showing up with, yeah, so this, you can see this is now configured the interrupts, right? So we have the address set to FEE00418 data 0. So that would correspond to the interrupt controller on the device. All right, so let's take this address. Oh. Oh, do I need to actually put a 0x in front of this? No, that's, saying the device needs to be loaded. All right, well, I'll try it. Yeah, it's been reserved by the drivers, so you can't poke at it. Let me see here. This bus PCI devices. What was that? BEE. So it is enabled, but devmem is still reading all Fs. Why would it be reading all Fs? I don't know. Go figure. It's never as simple as you think it's going to be, right? But it seems to be at least sort of functional. So, yeah, I thought it was just disabled by default on most operating systems now, but I guess it's enabled on Arch anyway. Presumably they have some level of filtering on here, so like when the driver reserves the regions, I guess then devmem can't use it. There's another utility. What was it called? Let me see if I have that. Did I like download it somewhere? Oh. Oops. Yeah, I'm not sure where the I think there's like a PCI mem utility as well. I thought I had a copy of it on one of these machines, but I don't know where it is. Yeah, whatever. We know it's going to work from the driver, so yeah. Well, we'll just roll with that for now, right? Okay. Great. So, well, that was interesting. You learn something new every day, right? I didn't even know that the devmem thing existed on these hosts because I thought it was just disabled by default. Well, that'll be something to investigate some other time. Yeah. All right. So the next thing then is to see if we can get ping working on this thing, right? All right. So before I do that, I'm going to give a little bit of a background here. Let me go ahead and switch over to that, and let me get a piece of paper. Oh, that out of the way. This out of the way as well. I can put this guy over here. Okay, let me see. I need a piece of paper and something to write with. Okay, cool. So the next thing that we need to do is to build the actual NIC data path, right? We have the PCI Express interface working. We have the Ethernet MAX working. Now the question is we need to get data from the host networking stack over to the NIC. And we need to implement the return path as well, right? So question is then, how does a NIC work, right? Especially if you want one that has a, some reasonable level of performance. So on the host side, right, we're going to have the system memory. And then we're going to have a PCI Express link that goes to the hardware, right? So we got the memory here, we got the hardware over here, and this is PCIe. And the question is, if we have a little packet that's sitting in memory, right? We have some packet. How do we get that packet from the host over to the card? There's probably multiple different ways you could go about doing this, but the most important thing is we want to make this as efficient as we possibly can. And to understand how to do this properly, we have to know a little bit more about the system architecture. So like I said, the host is connected to the hardware, the NIC hardware, over PCI Express. And what does that mean exactly, right? Can't we just send this thing over PCI Express? Well, unfortunately, PCI Express is a very low-level protocol in terms of how it interacts with the operating system and with the host CPU. You can't simply open a socket and send arbitrary data over PCI Express like you can with Ethernet. And the reason for that is basically the abstraction of PCI Express is that it's about memory access. So in the system, you have your global address space. Part of that address space is going to correspond to DRAM. Part of that address space is going to be mapped to I/O devices. So if you perform a read or write access on a portion of the address space that's routed to the PCI Express root port, then that operation will get translated into a PCI Express TLP, which will get sent over the link to the device on the other end. So if we want to send data to the NIC, we have to do that in the form of a memory write. But the problem is that the CPU, it can only access memory in increments of its word size, right? So if you have like a 64-bit CPU, you can perform a 64-bit load or 64-bit store, and then that will go out over PCI Express. But PCI Express is a packet switch protocol, right? So when you issue a 64-bit load or 64-bit store, it's going to get wrapped into a packet. So there's going to be some number of bytes of headers and other overhead associated with that operation. So if I have an 8-byte read, for example, or an 8-byte write, let me think here. So PCI Express is going to add between 12 and 16 bytes of headers. And then there's another 8 bytes of like physical layer overhead on top of that. So it's something like 24 bytes for every single operation that you perform that you have to pay in overhead. So if you want to say have the CPU copy this packet to the NIC 8 bytes at a time, that's going to be terrible. Now, obviously, there are other CPU instructions. For example, there's like SSE and AVX and that sort of thing where you can perform larger operations. But this doesn't really solve the problem completely for multiple reasons. And another thing to think about as well is that you don't want to be wasting CPU time touching every single byte of the packet. It would be much better if the NIC could just read the packet at its own leisure. So yeah, having the CPU read this and write it to the NIC, not a great idea. So instead, what we want to do is use something called DMA, where we have the NIC read the packet directly out of system memory. Now, I guess one other just quick note on terminologies. MMIO is specifically the CPU reaching out to hardware and performing a memory read or memory write. DMA is the hardware reaching out into system memory and performing a read or write. And then you also have peer-to-peer DMA, which is a piece of hardware communicating with another piece of hardware via DMA. All of these look exactly the same on the actual PCI Express bus. The only difference is, the entities involved in the operation. Now, there is like I/O space and configuration space and whatnot in PCI Express, but configuration space is really only used during like device initialization. You don't really use it after that point. I/O space is not really used these days. So the only thing we're interested in is the memory space and performing memory operations. And I/O space is, my understanding, is basically just memory space. It's just a different address space. So but there's generally a very limited amount of it. So for the most part, we're just going to be doing memory operations. All right. So getting back to the problem here, right? We need to get this packet data from host memory over to the NIC. And we want to do that by having the NIC reach out via DMA and reading this. So for that to work, the NIC needs to know where this is located. It needs to have a pointer. So we have to somehow get a pointer to the packet into the NIC and a length. So we could do that by writing those into registers, right? We can have a register for the length. We can have a register for the base address of the packet. And while this would work, there are some problems. And one of them is that you have to have some sort of a flow control mechanism, right? Like, is the NIC only going to work on one packet at a time? And we update those registers, and then the NIC works on that packet, and then when it's done, then we'll write another packet. That's really going to limit the throughput. And additionally, if you were going to, say, have the CPU just go crazy and writing packets into the NIC, you're eventually going to fill up whatever resources the NIC has to keep track of that. So you have to have some kind of a, handshaking mechanism between the two to make sure that the CPU is not going faster than the NIC, right? Because the NIC on the other side, you have the actual Ethernet link here, right? And this one is only going to run at some speed. So the NIC can't send data any faster than the link. So you have to have some mechanism to make sure that you're not, exceeding what the actual link can do here and causing backups somewhere. So how do we get this information then from the host to the NIC? Well, if we can't write it via registers, what about writing it out into memory, right? If we have another memory region here where we can write, the address and the length, and we can inform the NIC about the location of this memory region, then the NIC can go read this at its leisure, right? And it can work on, one operation at a time. CPU can just queue up a bunch of stuff, and then the NIC can chew on it and send stuff out, and there's no problem, right? So this is called a ring buffer, or a queue, or a descriptor ring. There's a bunch of different terms for it. In order to build this, you need everything, both the driver and the NIC, to know about this memory location, and you have to have a producer and a consumer pointer pointing into this here, right? So how do we use this, right? What we need to do is write a piece of information into this buffer, and that piece of information we call a descriptor because it's describing an operation. So the driver will write it in here, and it will update the producer pointer, and then it can write another descriptor and update the producer pointer, so on and so forth. And it can do that until the producer pointer matches the consumer pointer, at which point it's full. Okay, so let's say the driver writes some entries into the queue. How does the NIC know about these pointers, right? Because the NIC also has to know about the producer and the consumer pointers. Well, we have to use MMIO somewhere. And generally what we will do is write the producer pointer into a register on the NIC. And then, now that the NIC knows about the new producer pointer, it can advance its consumer pointer and read entries out of the queue. And that works, but that works until the queue is full, and then the driver somehow needs to know about the consumer pointer, and the progress that the NIC is making on, sending the data. So, okay, how do we do that? Well, let's separate this into a couple different pieces, right? Obviously, we need to know about this consumer pointer somehow. But another thing that we need to do is that when the operation is complete and the packet is sent, then we need to be able to free up this buffer for use by the operating system for something else. We can't just leave this allocated forever. So we need to know when the operation completes. So to do that, we set up another little buffer in host memory. And again, we need to know the base address, and we need the producer and consumer pointers into this. When the NIC completes sending a packet, it can then write a completion record into this queue. And then the driver can read that completion record and go, okay, this operation has completed, so we can then free this element, right? We can free this packet and reuse that memory for something else. Additionally, once we've seen the operation complete here, we know that the consumer pointer has advanced here. So we actually don't need to know directly about this consumer pointer because we can infer based on the operations that we know have completed. Okay, but somehow the hardware then has to tell the software about the updated producer pointer. So how do we do that? Well, you might think interrupts, right? We can fire off an interrupt from the NIC to the host and tell it that something has happened. I mean, that's certainly important, and that we can tell the host that something has happened, and it can run code to try to handle that situation. But an interrupt doesn't carry any arguments, right? You're not sending any data. It's just an event that something happened, and then it's up to the driver to handle that. So how do we know what happened, right? How do we know what entries in the queue here are valid and which ones aren't? Well, this is where we use a technique that a whole bunch of different devices use. It's something called a phase tag. And the idea is that every entry in this queue, we reserve 1 bit somewhere in that entry to use as something called a phase tag. When we allocate this block, we initially zero it out. The whole thing, we write zeros over the whole thing. So all of these phase tags start out as 0. Now, when the NIC writes a completion into the ring, we set that phase tag bit to a 1. Then the host, all it has to do is read the completion and go, oh, the phase tag bit is set. We have a valid entry. We can process it. And we don't need any other communication between the two. And the first pass through, we set all the bits, right? So we set 1, we set 1, we set the next one, we set the next one, so on and so forth. At that point, they're all set. When we wrap the pointers around, then we clear the bits out. We clear it out the second pass, and then we set them the third pass, we clear them the fourth pass, so on and so forth. And with this method, we don't actually have to have explicit communication about the exact pointer value. We just need to look at these phase tag bits. And you might be wondering, okay, well, how does the NIC driver know about the consumer pointer? Well, the NIC is only ever going to write a completion in response to some sort of request. So as long as the driver doesn't issue more requests than it has space in the queue, we don't need to know about that pointer because we're never going to overflow it. And I mean, even if it did run into a situation where the queue is full, like what is the hardware supposed to do in that case? Besides, stop the queue and raise an error. So that is kind of the high level for how this works, right? The driver will get a packet from the operating system. It will take a pointer to that packet, and the length of that packet will write that into the transmit descriptor ring in the format of a descriptor. The NIC will then read that information, send the packet, and write a completion into the completion ring. Oh, sorry, I missed a step. Right, the driver writes out the descriptor. It then writes via MMIO the updated producer pointer to the NIC. The NIC then reads the descriptor, carries out the operation, writes the completion into the completion ring, along with the phase tag bit, fires off an interrupt. The host then looks at the descriptor, or looks at the completion, realizes that the phase tag bit indicates that it is a valid entry. It processes the completion, frees the packet, and advances the consumer pointers on both of these effectively. And then when more packets need to be sent, then you repeat the process. Okay, great. That works for transmit. What about receive? Receive is exactly the same. It's just a question of which direction is the data flowing. For receive, it's simple. The driver has to allocate a bunch of empty buffers and then write into the receive ring pointers to those buffers. And then from that point, as packets show up, the NIC will pull those descriptors, write the packet data into the buffers, generate completions, and then at this point, the driver, instead of freeing those, will hand those off to the operating system for processing. And this is not just NICs do this. Pretty much any high-performance device will do something very similar. If you're doing something like with RDMA or Rocky, you know, the send queue, receive queue, completion queues, they work just like this. And also with like NVMe devices, you use a submission queue to submit operations to the hardware, and then a completion queue to get the responses back, all doing exactly the same thing. So plan for today is to take this and implement a very stripped down, simplified version of this in the HDL, and then write a driver and some Python code for testing this to make sure that it works properly. Well, we'll test it with the Python code, and then with the driver code, hopefully it'll work well enough to actually be able to do something simple like run ping. That's the plan. Let's see if we can make it work. And I see we're getting a little bit distracted here in terms of the devmem thing. I see, okay. Okay, so it sounds like the kernel has a strict devmem setting. So depending on the configuration of that, it determines what you can access through devmem. So it's not like the devmem thing just completely goes away, but its behavior changes. Yeah, IOMMU. Well, so the thing is, IOMMU is more in terms of DMA operations from hardware, right? So IOMMU can prevent, you know, a NIC or some other device from accessing system memory. But in terms of the CPU accessing stuff, that would just be the normal MMU. Yeah. Anyway. I'm getting all tangled up with some of these wires here. Okay. Okay. So the next step here then is to start working on the core data path. And I just went over how the NIC needs to work, kind of at a high level. So the question is now, can we render that reasonably in HDL and make it work? So this is probably going to be the tricky part. So yeah, okay, so this was, all right, that was the module code. Let me see here. Now I need to start creating some additional files. So for the time being, I'm just going to create everything in this RTL directory here. And then later on, I can go ahead and figure out how to arrange things more nicely. So one step at a time, right? Okay, so what do we need? What do we need? So I'm going to go ahead and create, let's see, I'm going to create a file for the core logic for Corundum Micro. And then I'm going to create, well, actually, I guess, for now, I'm not going to use the PCIe file, but I am going to use the PCIe UltraScale one. And we'll roll with that for now. Okay, so go ahead and, oh, and that doing something annoying. All right. Didn't want to do that. I just wanted to open them up normally. There we go. Okay. Got to drop it in exactly the right spot for this to work. All right. What do we need here? I'm just going to copy this for now here. Okay, so there's a couple different things that we need, right? Just clear out all of this stuff for now. That'll be the core logic for Corundum Micro, right? And well, all right, so I have the PCIe stuff here for now. So I'm gonna get rid of this one for now. I'm gonna put PCIe UltraScale here. All right, so there's the PCIe connections. Now I need Ethernet connections, right? So what do we need for that? We need AXI stream input and output. Let me see here. Right, so AXI stream input and output. I'll just go ahead and copy this for now. Okay. So we have RX and TX. So max TX clock, and this is going to be source, and there's also going to be a TX completion. Okay. How did I have that labeled on the Mac? Check on that real quick. Mac wrapper. Okay, TX CPL. All right, cool. Okay, and then yeah, for now I'm just gonna leave it 1, and then this can be that. Okay, that's better. Then later on I can rework that. So this is going to be RX, and RX is going to be a sync. Okay, cool. So we got that. That looks reasonable. And I'll fix the PCIe one in a sec here. We got the Ethernet connections here. Okay, nice. And I got to fix all the indentation and whatnot, but you know, one step at a time. All right. So this is going to be core PCIe US, and the idea with the PCIe one is it's going to wrap the core logic here, and then we're going to add the PCI Express related logic on top of this here. Yeah, and I'll have to add all of the associated parameters and such a bit later once we get some stuff a little bit figured out a little bit better. All right, so what do we need here? I have the AXI Light Master. This is going to go over here, right? So we're adding the AXI interface logic on top of this. Actually, and I need one more thing. I also need the bar configuration here. All right. And then these things can be specified as parameters. Well, it's got to be specified somewhere, right? Go ahead and grab that. This here. All right, so the address width and the data width, there we go. So we have bar 0. Instead of calling it bar 0, I'm going to call this the control bar. Okay. There we go. So we got the PCIe clock and reset. We got the CQ and CC. This provides the AXI Light control bar here. Then for this, I'm going to call this just clock and reset, and then this needs to be AXI. There's a number of things that I need here, right? So I'm going to need AXI Light, and I'm also going to need connections to the DMA engine. So yeah, one step at a time here. I'll go under AXI, RTL. Let me take a look at the AXI Light. Doesn't really make that much difference. I just need something AXI Light. Okay, there we go. So yeah. So I guess what I'm going to do here actually is I'm going to take the clock and reset. I'm going to move those up to the top. Ethernet, I'm going to leave that at the bottom. Then I'm going to go ahead and add, let's see here, PCIe Lite control register interface here. Right, so one thing that I mentioned before is that I want to rebuild the basically the management interface between the hardware and the software. I'm not going to do that initially. First pass, I'm going to use a very basic register interface just to keep things simple. Once that's kind of working, then we'll revisit the control register interface and see what we can do there. Right. Well, it's not so much the control register interface. We'll revisit the kind of management subsystem. And the idea is to use basically commands that are similar to descriptors plus queues to transfer those to and from the hardware. That's the plan. That's the plan. Okay, so I got that, and then I'm going to go ahead and make these connections here as well. So I got Ethernet, and then here goes Z, screwing up things again. So these go away, and then I'm going to have the PCIe clock and reset here, right? PCIe clock and PCIe reset. Okay, cool. And the control register interface, that's going to be this is AXIL. Okay. There's a question, do we know if root can access devmem even if config strict devmem is enabled and a driver didn't reserve the regions? Well, you can test it, right? My guess is that something is not going to work. Either the driver won't work if it doesn't reserve the regions. But yeah, I guess you can try it and see what happens, right? Also, I don't know exactly what the reserve regions thing does and if there's any additional semantics on top of that. Like maybe there's a way to request regions in a, less restrictive manner. I don't know. Probably not. All right, so that's the PCIe interface for ultrascale. And I will go ahead and add a parameter for the control bar here. All right, so we'll copy that and we'll use that over here, and the data width, we'll fix that at 32. All right, great. Okay, so the idea here is that this should give us the basic register interface through to the core here. So what I can do for the time being is copy and paste this little RAM, and we can use that to do a quick test of this thing. We'll have clock and reset, and then the AXI Lite control interface here. All right, great. So that's looking a little bit better here. I don't think, well, I'm not going to add any parameters yet. That will be necessary at some point. Okay, cool. All right, so the other thing I need to do as well is to start creating some .f files for these. So I can go ahead and put all the files in here. So we have the top level here, and then this is going to be core.f, and then I need to start adding the PCI Express related stuff. So let me see here. What did we add previously? This is how did I do this before? Yeah, okay, it's gonna be something along those lines. Okay, cool. But this is going to be PCIe, and then let's see. So this is going to be pulling in AXI Lite, AXI RAM. Okay, cool. So I'll just pull that in for now. Okay, great. Okay. I Lite IF, that's, oh, I guess this can go under this one here. I just copy that. It's going to be .sv. Okay, and I have the AXI Lite interface, AXI Lite RAM. Okay, great. So I just do that. Okay, great. Okay, so the next thing that I should do then is to try to set up some test code for this, just so we can start poking with the logic and make sure it's doing something useful. Let me also go ahead and I will make a copy of this and put this in FPGA core and replace, I guess, most of this stuff, right? I will do this. Corundum micro PCIe US, right? So we have the bar 0 aperture set to 24. PCIe, that should be right. So that's just going to be basically a direct pass through from the top level. I guess I copy these from the top level, right? So that should be no problem then. Okay, great. There's that, and then the Ethernet. Actually, that's a good point. I might as well just go ahead and add a ports parameter on this. So I have a parameter here. All right, so parameter ports, I'll call it 2 by default, and then these are all going to be parameterized based off of that. All right, so we got that, and we got that, ports. All right, great. Okay, and then we can go ahead and add okay, that looks pretty good. And then over here, that one's fine. And then I can go over here, and these will just be a direct pass through. Oh, this is RX, so I do that. And then I do the same thing on TX. All right, cool. Got to get everything all hooked up. That's very important. Okay, and then this is going to be TX and TX, TX, and TX completion. Okay, and then this port count here, right? Ports 2. Okay, cool. So we got PCI Express connection, we got the Ethernet connection. Get rid of, I think we can get rid of all this, right? Yeah, okay, great. Okay, so that's that. And now what I can do is go over to, well, let's see, for now, we'll go ahead and do that, and then I can get rid of that. Okay, great. Okay, that's looking more reasonable. Now what I need to do is create a test bench here. I don't think I have a, I don't have a test yet for this. All right. That's the modules directory. All right, so I'll go over here. Oh, I see. I'm looking at a different directory here. All right, FPGA EB. There we go. All right, that is what we need here. Okay, so I'm looking at the FPGA core here. Here's a test bench for that. All right, great. So we have the top level test here, and I need to add okay, so we've added that, and let's go ahead and see if this does anything useful if I try to build it, right? My guess is this is going to blow up somehow, but we'll see. Yeah, that was very unhappy about something. I think I have some syntax errors. FPGA core 398. Oh, I need an instance name. There we go. And I think I need to do that as well. That's fine, but I need to do it here. Okay, great. Still unhappy about something. All right, syntax error, FPGA core. What did I screw up? Oh, and I need to get rid of all these too. I just pass it straight through. Okay. Alright. What is it unhappy with now? PCIe US. And what did I do this time? Oh. Okay, I see. These are all completely wrong. Okay, there's that, and then I gotta do the same thing here. Okay. You can start to see where the system Verilog is quite nice, because to do the same thing in Verilog would require a lot of lines of code to make all of these interface connections. All right. Oh, another missing comma. Great. We'll get this eventually. Maybe. All right. Corundum micro core.sv line 21. That's unhappy about that. Oh. Yet another comma. All right. Now, what is it complaining about? Oh, it couldn't find the AXI stream interface. Really? That doesn't make any sense. FPGA core. This is line 67. I suspect this is just Verilator being unhappy about something, but I'm not sure exactly what the problem is. Because this file should be in the list somewhere. It says parent instance's interface is not found. Yeah, it's kind of annoying because Verilator is supposed to be pretty good at reporting errors, but it's certainly not unheard of for tools to do weird things when you have particular errors. Yeah, so this has a null source. BR1 should be in here somewhere, right? Yeah, here's the AXI stream interface. So something else is causing it to get tripped up, but I'm not sure exactly what. All right, next thing to try, I'm just going to comment stuff out piece by piece, and we'll see if this decides to start working at some point. All right, so I'm just going to keep commenting stuff out here. So if I comment this out as well, see what that does. Comment both of these out, or all of these out. Why not? Everything. The annoying thing is I just ran into this very similar problem recently where it couldn't, or it was complaining about not being able to find an interface, and the cause of the problem was something completely unrelated. But I can't remember what it was. All right, let me just see if I go back to this guy and I comment out that. Oops. Comment out that. What happens? That's interesting. So I've commented out basically all the new code, and it's still unhappy about this particular file. Oh, I think I know what happened. All right, yeah, this is just, hang on a second. I need to, okay, I see. Yeah, I see exactly what's going on here. This is basically, the problem is that you can't put system Verilog interfaces at the top level, and in a lot of these designs, I basically need to create a system Verilog top level, which I don't currently have. So let me go ahead and, or a system Verilog top level for the test bench. All right, so I've created that. Now let me think here. I'm going to go ahead and, I guess I don't have one for Ethernet, and I haven't created any test benches for the PCIe stuff yet, or have I? Oh no, I have. Oh, perfect. Okay, so I'll just copy that. All right, so test FPGA core.sv. All right, so that gets the PCIe side of things. And let me think here. So I've got the, all right, so I've got all the top level stuff for now. I just need to add the Ethernet, or what do I need for the Ethernet side? Actually, I guess I don't need to add very much because that's kind of buried, at least as far as the top level is concerned. So I have all the SFP plus connections here, which I can transfer over, but all of these are basically just going to be tied off. except for the ref clock. So I'm going to start with all of the... And let me think about this here. Well, alright, so I'll just do this for now. RX, that's blank. These are going to be this. Okay, that looks good. These are... Deal with those. Ref clock out, that's an out. This thing is screwing up again. Indentation. All of these I'm gonna tie off. Well, actually no. Okay, so copy that. These guys will be passed through like so. And let's see, so I do that. All right. Cool, that's that. Ref clock, I need to go ahead and find those as well. All right, great. Okay, that's looking more reasonable because I have the PCI Express connections now. Okay. Now I need to change this to the correct file, right? Yeah, okay. So I need to change this to bring in the top level. How do I do this in the other ones? Okay, yeah, here we go. I'll probably need to copy some stuff from here anyway, so. Oh, I guess I need the make file, and then I'll clean up the Python later. All right, so CocoaTV top level, and then that, and then the top level. All right, so I'll set all four. Well, no, I'll just set all of these lines like that. Okay, cool. It was this one. There we go. That one I think will work. Hope. All right. Making progress little by little. All right, so it's missing the 125 megahertz connections and the LED connections and a couple of other things. All right, great. Let me take a look at, yeah, I guess I just need all of this. Okay. So I take that, I go over here, same thing, I go ahead and paste this in here, and all of this just becomes, logic. And then I need to make those same connections over here. Yeah, I think the test bench code that I was looking at was copied from a different board. All right. All right, so then I get rid of this, and maybe that will work. Okay. All right, so then I need to remove some stuff from, well, all right, what do I need to do here? Sim vendor family. All right, so that's not passed through at the top level. So let me see here. I have, yeah, these guys. And I'm going to go ahead, go over to FPGA core. Do I need this? Yeah, okay. Oh, it is here. All right. And then I need to go ahead and add this here as well. Okay, and then these are going to get passed through down here. Actually, I don't need the combined Mac PCS well, whatever, I'll deal with that later. All right. Oh, I missed a comma yet again. All this thing with the commas really makes you appreciate languages where if you have an extra comma at the end of a list, it's fine. Makes a lot of sense to do it that way. Okay, slowly getting this piece together here. So we've got all the PCI Express related settings. That looks good. We've got the Ethernet related settings. That's all getting passed through. We've got the 4 main interfaces here for PCI Express. And now what we need to do is connect to a lot of that stuff in the test bench here. So it will take a little bit longer to get all of the, core pieces in place for this to run. But once that's done, then I think we'll be pretty good to go. Yeah, I'll have to clean this up later as well. All right. Yeah, Verilator takes a while to compile the Mac modules that I have. All right, so what else do I need to do now? I need to start looking at adding some of the PCI Express DMA engines as well, because I don't have those in here yet. That's going to be under, not under PCIe, but under DMA. So we need the DMA interface for PCIe UltraScale. All right, so I'm going to go ahead and add that here as well. Okay, so this one built and then it crashed, which is fine because we need to go down a few levels to get to the Mac. All right, let's see if we can get that to run. Well, in a second here. Well, all right, let's not get too far ahead of ourselves. Okay, so we're talking about .sfp Mac instance. All right, so well, I got to go through UUT, right? .uut. Oh, and then the Mac instance is right there, isn't it? Yeah, all right, that's probably all I need to do then. See if that works. Didn't need to rebuild anything. Okay, this test will not complete because I broke the loopback, but that did bring up the Macs. All right, so what I can do now is open that up in the waveform viewer. Let's try Surfer and see if this is any good. I usually use GTK Wave, but Surfer is kind of the new kid on the block, and I think it definitely has potential. All right, so let's take a look at RX0. I'll go ahead and add that, and yep, we have some data going through here. So there you go. All right, now we need to bring up the PCI Express interface and whatnot, but that's a good starting point. And you can see here, you see how the valid line is behaving a little bit funny in a few spots. That's because of the low latency configuration. There are stall cycles that get inserted periodically, and sometimes they end up in kind of funny spots. But yeah, okay, that looks pretty good. Now the next step is all of the PCIe infrastructure. So that's that. Let's see, PCIe, what do I need for that? I put together a rough test design over here. Okay, so I'm just using the UltraScale PCIe models directly. So I need to pull in this. I have Ethernet, I have PCIe. All right, that looks pretty good. And then I need to go over here and I'm going to go ahead and add all of this PCIe stuff. All right, so this one is, okay, that looks good. I'll go ahead and select all of this. Okay, so this is the PCI Express device model and the root complex model from the PCI Express simulation framework that I have over on GitHub, the CocoaTB extension for PCI Express. Go ahead and plug that in up here, and then the Ethernet will be down here. And I probably need a slightly better mechanism for doing all this setup work, but one step at a time. Okay, I also need AXI stream. And I think there was an option, there we go, there's the AXI stream. Go ahead and pull that in as well. Okay, so we have AXI, Ethernet, and PCI Express. And let me see, I'll go ahead and clear that out there. And let me see what the test cases need to do here. Okay, I think I need to rework some of this stuff because I don't actually need to run Mac test. Yeah, I'm going to go ahead and just move this up for now. Well, let's see, init. Okay, yeah, I'm just going to remove all this for now and then put the Mac stuff in there. Okay. All right, so this is going to be looking at SFP sources 0. Okay, so think SFP sinks and then SFP sources, right? Okay, that looks good. So multiple small packets, it'll send that, and then, all right. And then I also need to initialize the PCIe subsystem, I think. Let me take a look here. Yeah, okay, so this does a bunch of setup stuff. So I'm going to run actually this exact same code here. And I will go ahead back over here and init. Go ahead and run this stuff first here. Okay, so I do alloc region, get absolute address, find device. I'm just going to pull up bar 0. It's going to be bar 0. Okay, bar 0. So this is going to attempt to access bar 0. Okay, great. Dev is coming from there. All right, do we need a timer? Yeah, I should import that as well. Great. Need a timer under CocoaTB triggers. All right, let's see if that works. Oh, I need to fix one of these files here. This should be under PMA, not PCIe. All right, so this failed. Why did it fail? AXIL, oh, contains no object named AXIL bar 0. All right, where is that print coming from? That is 370. Oh wait, that's something else here. Okay, that's 269. Okay, I see. So this is looking at the bar 0 address width. Well, I'm just going to set this to 24 for now. The to-do for handling this later. Here's what I'm going to do. Duplicate that, make this 24 bits, and then we'll do that. All right. But that was at least a somewhat promising start. Oh, actually, let me take a look. How is this configured in terms of MSI? So I want to enable MSI here. True. MSI X. False. MSI count 32. All right. That's probably closer to what we want. Okay. So this failed. Untype. No attribute bar window. Uh-oh. What happened? I don't think the PCIe bus was actually enumerated. Where is that done? RC, make port connect. Okay, no. Here we go. This is part of the init routine here. Alright, let's try this. Wait for falling edge, PCIe reset. Okay, gotcha. So I'm going to go ahead. Sometimes takes a little while to get some of these components sorted out properly. Alright, so we do all that to reset all that, and then go ahead, tab that in. Alright. So this is looking at PCIe reset and then enable device set master. Okay, that looks good, and I need to go and add falling edge as well here. Okay. All of this just to get the core PCI Express test bench components working. What happened? Oh, I have a typo. I see. That is this thing being unhappy. Let's try that. Alright, I'm actually going to do this differently here then. Think about this for a second. So the 125 megahertz. I guess I can just do this first. The problem with falling edge, if it's already low, it's not going to fall. Alright, so that did something. There we go. So that actually worked. So we have the PCI Express model working, and for those of you that haven't really looked at the PCI Express simulation framework before, let's just go over a little bit about what's going on and all this stuff that I just did. Because a lot of stuff that I copied and pasted from other test benches. So in general, there's two different things that were created here. The first one is the root complex model. The second one is a simulation model for the UltraScale Plus PCIe device hard IP core. And then these two modules get connected together here. So I create a port on the root complex and I connect that up to the PCI Express device. And then I also add a bar on the UltraScale PCI Express device. And then later on, during this init routine, I call rc.enumerate to enumerate the bus. And then I can do find device to get a reference to the device. And then I can do enable device and set master to get everything set up for the test to do stuff. So in this case, we can find the device again, and then we can look at the bar, and we can write to it and read from it. And this one is doing byte-based operations, but you can do, well, for this one you can do arbitrary size, but there are wrappers to do like D-word operations as well. So when you when you call the enumerate function here, this triggers a whole bunch of stuff to take place in the test bench. So if we look at the log, when we start out, it prints a bunch of stuff, including, it's like, here's the hard IP model being created. Here's the, or hang on a second. Yeah, okay, here's the root complex model being created, and then here's the PCI Express UltraScale Plus model being created. And this has all of the internal parameters here for the link speed, link width, etc. for all of this stuff. You can see we've enabled the PF0 MSI, disabled MSIX, that sort of thing. It picks up a PCIe ID here. I think that is spurious because it hasn't actually started the enumeration process yet. Well, actually, so this is the root port, so no, maybe that's actually correct. And then we have stuff here for the base R, the max for the serializers. And then finally we get down here, prints out, this is actually coming from the simulator, the address configuration for an APB interconnect block. This is inside of the Mac wrappers. And then down here, we actually hit the bus enumeration part. So root complex, it's enumerating bus 0, device 1. Then this is going through the process that you need to enumerate all the devices on the bus. So the way this works is, why is it bus 0, device 1? It seems like it should be starting with device number 0. Anyway, oh no, okay, no, this is enumerating stuff on the root complex. So I'm actually not 100% sure what the proper way is of enumerating components associated with the root complex itself. But in this case, because all of the root ports, they get device numbers, 1, 2, 3, 4, 5 underneath the root complex. This starts out at device 1. So this will poke it via the config space and read a few registers, finds a function, realizes that it's a PCIe bridge based on the class code, and then it does some internal initialization here. So I think this is looking at the bars. No, this is looking at the bridge control registers. Then it walks the capabilities, and it finds a couple of different PCIe capabilities. And then it enables extended tags. I guess it doesn't really do much else at this point. But then it looks at the other devices, and there's nothing for device 2, nothing for device 3, 4, 5, 6, 7, 8, so on and so forth. So all of these get, I believe these should all result in unsupported request operations or responses. Not 100% sure about that exactly, but you get these warnings because it failed to route the TLP because there's nothing there, right? And then it goes down here, it scans the bridge, right? So this is the root complex, or not the root, this is the root port that the device is connected to. So it scans that, it assigns PCIe bus number 1 to that. Or no, never mind. This is scanning the devices downstream of this component. So it tries to access bus 1, device 0. I think it actually, does it assign, I can't remember the exact sequence here, but bus 1 is the next bus number that's available. So it uses that one and it attempts to enumerate devices behind bus number 1. And at this point, that bus number is captured by the UltraScale Plus PCIe core, and you can see the bus number changes here, and then it continues to enumerate it. It reads the device ID and whatnot, and then it let's see, it enumerates the function. It realizes that there's a bar, and then how does this work? M bar 0, 32-bit, maybe that should be 64-bit. Anyway, I think this process here is part of initializing the bars. 5, 6, 7, 8, 9, C. Yeah, I can't remember. Oh, okay, I see. So this 4, this is looking at the first bar. Okay, so it's identified the first bar, it identifies the size and such. It's a 32-bit bar, and that's the size of the bar. And then that can be assigned. So it looks at all the other bars, doesn't find anything, walks capabilities, yada, yada, yada. At some point, it's actually going to go allocate it. Okay, so it configures the function. Here it is. It's allocated the bar. It writes that address to the bar. And then doesn't do anything with the I/O. Well, I guess this is now poking at the switch at the root port. So it configures the registers in the root port. At that point, the enumeration is done. That's the LSPCI style output that you get, right? So this is, below the root, you get, or I guess at the root, it's bus number 0 and 1. At bus number 0, we have device 1, that's the root port. Underneath that, bus number 1, we have the device at device 0, function 0. Relatively straightforward. And then, let's see, at some point, all right, so we call enable device. So now we're getting down here. We call enable device, we call set master. So enable device, boom, enable bus mastering, boom. And then that also gets done. That gets done at the root port and at the PCI Express hard IP core level. So these are both kind of recursive things to turn everything on and set everything up. Yeah. So this is, it's await dev dot, So that should be handled by the driver internally. Actually, I'm not sure. It's interesting how it enables the device and then enables bus mastering on the root port, and then enables the device and enables bus mastering on the ultrascale core. I would need to double check the code to see what it's doing there. That doesn't seem quite what I remember, but I could be mistaken about that. Right, and then at this point I do a test memory write, right? So it goes down here to do test memory write to bar 0. And what is this? We create some test data. We write that to address 0 of the bar 0. There's the data. And then we do a read. Same thing. We read address 0 of bar 0. We want the same length. We get that. We print it out. Okay, cool. So what do we see here? Well, the I guess I don't have all the debugging stuff turned on, but the root complex model will generate a TLP and send it to the PCIe hard IP core. And then what we're seeing here is the ultrascale format frame. So we can see here's the data that we wanted to write, right? It's the same thing. And then we have the byte enables, etc. The core handles that, and then we do a test memory read. List. All right, this is another thing that I need to look into probably at some point. That will need to be fixed. Okay, wait op.join. All right, well, that's something to take care of at a later date and fix that. Anyway, we do test read. It issues the read, and one of these is the address. I'm not 100% sure which one is which. This might be the address and length or something. Because I think this first one indicates what the operation is. But it's both C. So, all right, I would need to consult the documentation. I can't remember exactly what this is referring to. I think this is the address down here, though. Anyway, yeah, because it's probably 1F. No, but this should have been writing to the same thing. I'm not sure. But this would be the this would encode the necessary operation for the read, right? And then this is the completion carrying the read data. So that'll be the completion. And then over here we have the read data that's being returned. So that's pretty straightforward. I guess maybe this 1F, the tag, because I see the 1F over here too. And there's no tag here. The tag would be 0. C, yeah. Well, what was the address that was assigned to the bar? Allocation C, all zeros. So this might actually be the address on this side. I'm not entirely sure. Yeah, this is probably the type, right? Because 801, 001. Anyway, whatever. That is the gist of how a write and then a read takes place with the core. And so the idea is that this is going to be sent down CQ, and this will be returned on the CC interface. And that will be handled by the AXI Lite master module here. So that this request, right, this will come in CQ. This will perform the operation on the AXI Lite control interface here, and then you'll have the response going back out on the CC carrying the read data. All right, and let me just take a look now if I can reload Surfer here. Let me see if we can pick that up. Actually, let me hit a refresh here. Oh, this is being slow. Why is this being so slow? That's interesting. Okay. It's this is another problem that I run into occasionally, is that the files are not always closed out properly. So yeah, this file annoyingly cannot be opened right now. All right, well, we'll take a look at that in a bit. Yeah, we'll have to see about that. I don't know if that's a Verilator bug or something else, but yeah, that's a relatively common problem, to have issues with opening files that that were not quite closed properly coming out of the simulation. All right, so let me see here. The next step is to actually start putting together the core data path for this thing. Now that I have all the framework in place, I can start working on that. So, oh, I guess I need to hook up the DMA engine. All right, let's do that real quick. I'll get that squared away. All right, so the DMA engine. Let me see here. This is under DMA RTL. We're looking at the DMA IF PCIe US. I should have one down here I can copy. DMA IF PCIe US. All right, there we go. Perfect. And yeah, this one has a lot of code associated with it, so this will take a second to get everything all set up. So you have read descriptors, you have write descriptors, you have the DMA RAM, and then we have a bunch of additional control signals. All right, go ahead and copy all of this so we can get started with that. This is just being pulled out of the test bench for the DMA interface module. So we have the AXI Lite master module here, and then I'll go ahead and add the DMA interface module here. All right, so statistics. Yeah, I'll just leave this stuff kind of wired up the way it is at the moment. All right, so RQ and RC, those are getting passed in. Clock and reset, we have those as well. So this is getting passed through as a PCIe clock. All right, so PCIe clock and reset. M-axis PCIe. All right. There's the PCIe connections there. Sequence number, input, transmit flow control, read descriptor, write descriptor, RAM interface, configuration. So the configuration stuff, this is going to have to come from one level up, right? So this configuration, I'm going to pull that, and that's going to go, going to have to go up here. What happened? Okay, there we go. That's better. Okay. So read enable, write enable. Well, I guess not necessarily all of this will have to go up to the next level here. I think read enable, write enable, that's a different story. X tag enable.
Well, actually, okay, here's what I'm going to do. Instead of doing that, I'm going to go to one level up, and I need to, oops, not that one. I need to go to FPGA core here. And in this case, actually not even FPGA, I need to go over to FPGA.v. Alright, so in this case, I need to add a bunch of this configuration related stuff. So sequence numbers, actually I guess I need pretty much everything. Interrupts, error status. Alright, so we're going to start just with all of this. Alright, so I go down here now to here. This is the annoyance about working with PCIe cores occasionally, is you need a lot of connections to make everything work. So that's that, and then I need RQ sequence number. Let me go ahead and get this added over here as well. It's all going to be, oh, it's not all inputs, is it? Oof. Mostly inputs. Those are inputs. All of these are inputs. MSIX, I will forget about that for now. MSI. Alright, I'm just going to fix the directions later. But that's all inputs. Well, it's not all inputs, but we'll start with that for now. And similarly, we have all this as well. So all of these signals are necessary for the DMA engine to work properly, because we have, well, I guess not just a DMA engine, but among multiple things, right? So this is the sequence numbers that track the movement of TLPs through the transmit pipe. We've got configuration settings here for the max payload and read request size. RCB relates to the read completion boundary on the host. It can either be 64 bytes or 128 bytes. So it's important to know that gets past the DMA engine. These configuration management ports are related to reading additional information out of the core. These are flow control related ports that returns information about flow control credits. So these are all inputs to the core. It's used to determine when information can be sent. It's actually an output, now that I'm looking at it. Yeah, that's important, because these are multiplexed. And then these are for interrupts, right? MSI, and I guess I removed the MSIX stuff, but yeah. So that's important for being able to send and receive, well, not really receive interrupts, but receive status about the interrupts that we're sending. All right, so that's that. And I can go ahead and transfer that through to here, right? We got all those same signals here. And this is going to get passed through. All of this gets passed through here. So all of those complaints from Vivado about things not being connected, well, we're now connecting a bunch of stuff. So that'll be good. All of this stuff gets connected. Boom. Okay, and I need to add this last one down here as well. Okay. All right, so that's that. And that is going to get it down into 4. And then I can copy this again to pass it through into the... Oh, actually, I guess I also need to add some of this stuff to the test bench, because we have the PCI Express connection here as well. Actually, let me rejigger this to line up a little bit better with what we got. All right, there's PCIe. Oops. Yeah, all right. Okay, there we go. And then I need to add all of these as logic as well, somewhere. I guess down below this. They all need to be connected. All right, so all of this. Okay. Great. So these are not inputs or outputs. These are just wires. Or no, this is going to be logic. Okay, that looks good. RQ sequence number width. Is that a parameter? I guess not. All right. Well, I'll add that. I think it's 6. Okay, and then I gotta add another one here. Passing all these parameters through can get a little bit monotonous. Okay. And this also needs to get passed through here, right? So I'm going to do another one here, .rq width, RQ sequence number width. Okay, great. So that passes it down through to the core here. All right. Now it's time to start getting all this stuff hooked up to the core again here. And there's more stuff I need to pass through going down as well. So we have sequence numbers. That's fine. We have those. Oh, do I need to add that too? Or do I already have that? Actually, no. Oh, I guess these need to start being connected through to the actual core. All right. So these guys, that gets connected through as all of these. Or no, I didn't want to do that. I wanted to copy these here. Okay, there we go. All right. So I'll go down here and these get passed in there. All right, so that's the sequence number connections. The flow control connections are next. I need to take a look at how I've done that elsewhere. I'm not sure the correct way of doing that at the moment. Read and write descriptor, we have the DMA RAM. All right, so I need to add connections for that to the core here. Let me see here. So this is going to be DMA. All right, so that's DMA, and then this is going to be consisting of a handful of different things where I'm going to go, let me just see here, PCIe DMA interface module, right, this one. And this has a bunch of connections here. So we have the read and write descriptor connections. All right, so go up to 4 again. Okay, great. Almost did what it was supposed to do, but not quite. Okay. Then I have the read and write descriptors and the, well, I guess I can get rid of this here. I don't really need all of these separate things here. So we've got the read and write descriptors for DMA. Call it DMA, read and write, everything. Okay, great. And then I need to connect all of these through to the DMA engine. Okay, great. Where was that? Okay, great. That looks like that, and then okay, so this is going to be this is going to be DMA read descriptor, DMA write descriptor, a read descriptor, DMA write descriptor, DMA RAM. All right, that looks good. And then I go down here and I can remove all of these extra annotations at the end here. All right, very cool. The read descriptor, write descriptor, DMA RAM. Okay, so these connections are how the core logic is going to talk to the DMA engine. So the read descriptor and the write descriptor ports, these carry basically the source and destination addresses to everything. The way you can think of the DMA engine is that it's basically doing a memcopy operation. So you have to provide a source address and a destination address and a length, and then the DMA module takes care of the actual operation. And then the DMA RAM, these are the connections between the DMA engine and internal scratchpad RAMs, where the data will be stored while it's being operated on. All right, so that's looking reasonable so far. Now I need to finish hooking up. What else do I need to hook up? So the interrupt stuff doesn't go to the DMA engine. That doesn't go to the DMA engine. These do. All right, so read enable, I'll just tie it high. Write enable, I'll just tie it high. All right, so max payload. Where does this go here? Max payload size, max read request size, requester ID EN is 0, requester ID is 0, RCB status is RCB status. So the only thing I need is X tag, and I think that one has to be read from somewhere else. I'm just gonna set that to 0 for now, and mark this as a to-do for later. Okay, so I think that's most of it. Status, guess I have all of these connected, just pulled out for now. Yeah, okay, so I'll just leave those alone for the time being. Okay, great. Now the next thing I need to do is there's a bunch of DMA related parameters that get set in. I think I copied these out of here, right? So there's a bunch of parameters. Let me just grab all of these for now, and then I will take a quick peek at getting these cleaned up here. Okay, so PCIe data width, I guess all of these can go away because a lot of these are coming in via, right, all the AXI stream stuff is all coming in already. RQ sequence number width, that needs to be moved to the top. Does it? Yeah, it does, because we have top level parameters here, or top level ports. I'll do that. That goes away then. Sequence number enable. All right, so we can move that to the top level, I guess. Well, yeah, okay. RAM cell width. I think I already. Do I already have that? No, I don't have that yet. Okay, cool. Cell width. RAM address width. Where does RAM address width come from? I guess that's not defined yet right now. All right. RAM segs, that also needs to be defined somewhere. Oh boy. All right, so a bunch of these. I guess I need to interchange this block here. All right, cool. So sequence number enable. I'm just going to make all of these local params for now, and then that can all be cleaned up later if necessary. Sequence number enable, yep, RAM cell width, I'll make that 2. RAM address width, I guess I'll make it 16 for now. That looks fine. Actually, I'm just going to set it to 2 for now. Tag count, I'm going to make that 64. Immediate. Actually, I don't think I need that for now, so I'll turn that off. Immediate width would be 32, but that's not going to be used. Len width 20 is probably fine. Tag width, yeah, that may need to be expanded, but we'll do that for now. That looks good. Read FC enable. Okay. I think that's everything. I'm definitely going to put a big to-do on here to fix those things. But this is looking like a decent starting point anyway. Alright, now I got to figure out these guys. I think the way that was done previously is that these are just driven by a couple of the top level signals. Let me see here. RTL. I'm gonna look up some of the Corundum code and see how this was done there, because it does have a similar set of connections for bringing in some of these signals. Yeah, okay. So the FC cell pin. Okay, that one is going straight through to the PCIe IF. All right. Well, I don't have that, so I need to take a look at that module. Let's see. PCIe RTL. Yeah. PCIe DMA IF. What is this? No, PCIe IF for ultrascale. PCIe US IF. There we go. All right. So what are we doing with this thing here? That is okay. Got it. So that just needs to be tied off. All right. Let's see here. So this is. So this one, that just needs to be tied off. All right. So I assign. Okay. So I do that. And then what happens with all these guys here? Okay. That's an output. Great. And then that goes to, I guess I should take a look at the, where is this? Where is this? PCIe Core US again. So those signals come in, they go through the interface, and then I'm going to use a subset of them in the actual DMA engine. So which one is it? Or at least I think they need to be used in the DMA engine. Maybe they don't. What is going on here? That doesn't make sense. They should be used somewhere. DMA IF PCIe. That is statistics. RAM interface. Oh, right. It's because they would be handled deeper in the logic. I think it's actually handled by, yeah, the DMA interface block instead. Okay. Well, it should be clear which one needs to be connected where. So there's NPH, PH, and PD. NPH, PH, and PD. All right. So that's coming from here. And these are the signals. So we have NPH. Yep. Okay. And PH. Yep. And PD. Yeah. So this is. So what are these things? These are flow control credits that the hard IP core is indicating are available. So NPH is for non-posted header credits, which is basically the number of non-posted requests that you can issue. PH is the posted header credits, or the number of, write requests you can issue. And PD is the posted data credits that refers to the amount of data that you can request. Well, the amount of data that you can send in terms of oh, hang on a second. I'm getting things mixed up here. Okay, non-posted header request. This is the number of read requests that you can issue. PH is the posted header request, which is the number of write requests that you can issue, and among other things, but mainly write requests. And then PD is the amount of data that you can send in those write requests in units of flow control credits, which I can't remember exactly how many bytes that is per credit, but it's a handful, like 16 bytes or something per flow control credit. All right. So the PCIe DMA engine needs to use this information internally to, not screw everything up. Okay, so this is actually looking pretty reasonable now in terms of this connection. So I have this connected through to I have DMA connections here, and I have close this. All right, close that. All right. Oh, I see. Yeah, so I have those connected here. I'm not doing anything with them, but they are there. All right, so let's see if this builds or if this blows up in my face here. All right, I got to get this infrastructure in place first. Oh, RAM data width 155 in over here. Where was this? 155. PCIe data width. All right. I guess I just need to make some of this stuff. That is going to be coming from where is that? This one. Okay. Great. Pin not found. All right. DMA read desk request in Corundum micro PCIe US.sv. That's looking towards this. DMA read desk request. I mean, isn't this what we want? What happened? So this is line 377 in this guy. So this is core, Corundum micro core, DMA read scripter request. I haven't saved this file. That would explain a few things. Let's try that again. Okay, great. So there's a couple of these things that are unhappy that I'm going to have to take a look at here. Okay. All right, so one of these is a problem, minor problem in the DMA engine itself. All right, so this is PCIe. This is going to be the read DMA line 1000. I just have to cast that to the correct number of bits. Okay, there we go. That'll fix one problem. Oh, there's another one actually. 1231. 1231. All right, so this is PCIe tag width again. All right, so I got to cast that to the correct width. All right, and then finally, Corundum micro PCIe US. This one we need to take the 128-bit RCB status here, and I will just set that to 0. All right, great. I'm just going to pull out the first bit. Okay, so that's now building. Now I also need to go ahead and make a few connections on this side here. Or actually, no, sorry, not that file. All right, so I need to make this connection, this set of connections. Configuration management. I'll leave that one alone for now. Need to do this one. Yes. All right. I mean, those are the main ones. I think I will also need to do MSI at some point. Might as well do these as well while I'm looking at it. Okay, cool. Okay, great. So that is like that. That is like that. These I need. All right. All right, so this is going to take a couple minutes to rebuild the design, and this is just basically a test to see if it compiles for now. The next thing that we need to do once the DMA engine is more or less in place is to start working on the core data path more directly. And it's looking like I need to get a quieter chair too. This is squeakier than I was expecting. Anyway, all right, so that the Verilator build passed and then this crashed. Okay. So I need to fix some names, I think. Or actually, maybe what the problem is that there's some stuff missing from here. Okay, PCIe RQ sequence number 0. All right. It's important to get the naming right, you know? Oh, there's no underscore there. All right, cool. So I will do that, and hopefully this will work. Oh, I think this is just VLD, right? Yep. Okay. Oh, that's follow the same names. I should have just copied and pasted that. Classic. Hey, there we go. All right. So this went ahead and ran, and there we go. All right, great. Cool. So that is a decent start. Now I need to go start actually working on the data path itself. So, what do we need to do here? The first thing we need to do is we need to create a block of memory to store the packet that we want to send. And I'm going to go ahead and set this up for both transmission and reception. Let's see here. So I'm actually going to go ahead and comment everything out for this point. Okay. Got to start simple. All right, so I'm going to start with this just to make sure we're good. All right, so clear that, sync out. All right, so what we're going to do here is we're going to set up for both receive and for transmit. That's quite important because that's the only way we're going to be able to test this thing and make sure it works. All right, so what do we need to do for transmit and for receive? We need to allocate several different blocks of memory. And to do that, we need to do that through the PCI Express root complex. So let me take a look at the test bench for the DMA engine to remember what the correct process is for doing that. Okay, so we can create a memory region like this. So we can go out of the memory pool, we can allocate, whatever size region that we want. So I'm going to allocate a couple of different regions for both the packet and for stuff that we want to send. Okay. Oh, I guess there's more stuff that needs to be done here. All right. I'll deal with that in a second here. Let me just get this set up here. So we're going to create a RX buffer. We're going to make this, relatively small. How about we make this 4 kilobytes, right? We'll create an RX buffer. And we'll create a TX buffer as well, right? And then I'm also going to create a an RX ring and a TX ring. Actually, I'm going to call this RXQ and TXQ and RXCQ and TX. Oops. What happened? Okay, somehow I switched to a different file. All right, RxCQ, TxCQ. All right, so we can allocate a bunch of buffers like this. That's no problem. All right, then we need to start setting up the data structures inside of all of these. So what we can do is actually write into the packet buffer here in preparation for actually sending a packet. So let me take a look at the test design over here, so we can actually go ahead and write some data into this thing. So we can do test data, we do DMA RAM.write. Hang on, let me think about this here. We want this not to be in the DMA RAM, but in the memory region. So, okay, here we go. Yeah. I think we can also just write into this as well, but alloc region, and then we can write stuff into it. Okay, great. So let's go ahead and do this. PCIe address. Okay, that's fine. So we're going to go ahead then, and we're going to create a packet. Some fun test data, right? And we're going to go ahead and we're going to put that into the transmit buffer, right? And this is going to be make both of these 0, right? Okay. Actually, let's rearrange these. We'll do all the queues first, and then we'll get the buffer. Okay, so now we've put some data in the buffer. Now we need to send that and receive it. So what we're going to do is we're going to create some descriptors that sit in the TX and RX rings. So the completion queues, there's not much we need to do with those for the time being. Yeah, I'm not even going to bother trying to zero those for now, but for the TX and the RX queues, we need to go ahead and set those up with the appropriate descriptors. So I guess I should actually take a look at I have the Coco TBX PCIe. Do we have Coco TBX to AXI? Oh yeah, here we go. Coco TBX to AXI. I can take a look at the memory stuff that I have here. All right, so memory, yeah, we can read and write the memory. Yeah, okay, great. So that should be the case anyway. Okay, that's actually a good point. So I will do that write. I think that will work. Okay. RxQ.write and TXQ.write. Okay. Okay, so what are we going to write then? That is what we need to figure out next. And what I'm going to do is use Python's struct module. And let me see about this here. So L, that's going to be 32 bits here. Right? So if I do something like that, okay, that makes sense. But I need a 64-bit word, right? So it's going to be Q, and then I also need a length. So if I do that, I can then put like a length of like 32, for example. We can create a descriptor pretty easily like this here. Yeah, okay, so we can have the length, and then we can have the pointer, and these, I guess I need 4 X's, not 2. Or I can just do another L, and I can put a 0 in here. This is well, no, I'm gonna make this more clear about it being reserved. Actually, I'll make the first 4 bytes reserved. Okay, there we go. So this thing is 16 bytes in length. Yep, and it has the pointer over here. In fact, I can make this, let me do something. Make it a little bit more clear what's going on here. Yeah, okay, so we can see the length here and then the pointer here. So that's pretty straightforward. So we're going to do that here. Struct.pack, and then we're going to do what did I do? XXXX LQ, and then I need the length. And then I need base address here. I need to look up how to do the base address again here. All right, so for the RxQ, I'm going to set this to the size of the block, 4096. For the TXQ, this is going to be the size of the test data, right? And I guess I can actually rearrange this a little bit here. So TX, so RxBuff, TXBuff, TXQ.write. Okay, there we go. Let's see, struct.pack. Oops, this should be inside of that. Okay, now I need to go look up, so this is RxBuff, not TXBuff. I need to import struct, which I'll do in a second, and then I also need the base address of this, which is get absolute address. All right, cool. Okay, so this generates two descriptors and it puts them in the queues so they're ready to go. So now what I need to do is create the pointers, right? So the producer pointer will be 0, RxQ, we'll call this prod, and cons. That's also equal to 0. All right, cool. Actually, these should be done with each of the individual queues. So what I really should be doing here is, you know, making this thing a, objects, which would make things a lot easier to deal with going forward here. All right, CQ. So we have the producer and the consumer pointers for all these. All right, so at this point we can do RxCQ cons plus equals 1. And this one will be TX, oh sorry, it should be RxQ consumer, TXQ.cons plus equals 1. All right, great. So I can, oops, not dot. There we go. Okay, great. So we can do that. And then now the question is we need to poke that over to the hardware. So let me go ahead and do struct here. Okay, great. So we have struct. And now we should be able to run this. Now obviously this is not going to do much, but this is kind of the base stuff that we need for being able to actually test this. All right, so let me get rid of that. You got to have some way to test the functionality of the HDL. Oh, what happened? Trace malloc to get the object. Oh, coroutine was never memory interface dot write. Oh, hang on a second. I need to double check on something really quick here. Address space. So memory interface. Okay, so when this thing. Actually, I guess these are technically async. All right, well, whatever, that's fine. I will just do good old await. That's fine. Okay, so that's gone ahead and created those. Let me think here. I thought there was another way of accessing these. Oh, I guess these are coming out as windows instead of coming out as windows, or they're coming out as something else. Yeah, I can't remember exactly how that's set up. Yeah, I guess these are probably coming out as either memory regions or sparse memory regions, and these do not have. Okay, I see. So there is hex dump, so we can hex dump these things potentially. So let me actually do that. RxQ.hex dump. And then this is address and length. So 0 and 32 and RxQ. All right, and then we can do the same thing for the TXQ here. So if I run that, we should see hex dumps of both of these. Yeah, okay, there we go. So we can see this one is for the RxQ, right? We got the, I see. I should add a space to that or something. Yeah, okay. So there's the RxQ, and the length you can see is, well, it's hex 1000, which is 4096, and then for the packet data that you want to send, you can see the length is F, and here are the addresses that were allocated. Okay, great. So that was the easy part of getting that set up. The next step now is to push all of this information over to the hardware and actually bring the DMA engine online to transfer the data. All right, great. Let me think about this for a second here. So we got the core logic here, and we can perform writes over AXI Lite into this space. So let me think about how this is going to work here. Yeah, so I guess what I need to do then is to create an AXI Lite register interface. That's going to be able to accept the these pointers and whatnot, and then we can use that to perform the various operations, right? So we need to bring in base addresses for basically 4 different queues. We need producer and consumer pointers for 4 different queues as well. So that's 8 pointers. Yeah, okay. That's not too bad. I think probably the simplest way to do this for the time being is to keep things as simple as possible by having, instead of having, like the previous version of Corundum, it had a relatively complicated AXI Lite interconnect internally to provide register access to a bunch of different internal modules. So for this particular case, it doesn't make sense to do that yet. So what I'm going to do instead is to, let me think here. I'm going to have just one sort of temporary top-level register bank, which has all of the main options in it. And then that's going to push some of these base address settings and whatnot to a couple of other modules. So let me think here. I need to create a couple of different modules here. Let me see. So I need to create a module for, what's the best way to do this? So there's several different things that we need to do via DMA, right? We need to be able to read packet data, we need to be able to read descriptors, we need to be able to write packet data, and we need to be able to write completions. So we can do desc read, descriptor write, and then we can do Rx and TX. And what else do I need here? I think that's probably enough for a very basic setup. Yeah. All right, so we got the Rx and TX, and we got the desc read and write. Ah, shoot! This opened everything up on top again. All right, let me try that again. We got the descriptor read and write, and we got the transmit and receive modules. Okay, great. Okay, so for the, we'll start with a descriptor read, right? So for the descriptor read, we're going to have the clock and reset as inputs. We're going to have a control register interface. No, we're not. No, we are going to have DMA because we need to be able to issue reads. So for this, we need the read descriptor connections and the RAM write. And then we'll need another, for descriptor read, we're going to need I guess, two different AXI stream outputs. Let me think about this here. So when we want to both send and receive packets, we're going to have to go through the descriptor read function. So I think what we're going to do is have the transmit or receive logic issue a request to the descriptor read logic to fetch the next descriptor from the queue. And then the descriptor will be sent back to the corresponding logic. So we need AXI stream source for the descriptor. So tx desk and rx desk. And for now, I'm just going to have strobes for requesting the descriptors. Right. Okay, so we can do that. And then for the configuration, we're going to need a couple of things, right? First, I'm going to need the address, right? So that's going to be 63 to 0 TXQ base address here. And then we're going to have TXQ producer and consumer. Or do we need the consumer, right? So the producer is going to be updated periodically by the software. The consumer pointer is really just going to be handled internally. So I don't think I need to do anything with that. Okay, so RxQ, base address, and the producer pointer. Actually, I guess what I can do is make the pointer an output. Yeah, all right, so I'll do that. Output, and this will be the TXQ consumer pointer. And then same thing here, this will be the RxQ consumer pointer. So we'll start with that for now. Let's see, so the base addresses, I think those can be fixed. Do I even need like a load on these? I guess not. No, I think this is probably fine. Okay, so that looks reasonable. And for the, actually I call it desk write, but it really should be CPL write. So I'll do rename completion write. Oh hey, now it actually updated its hierarchy for once. Okay, well, great. Better late than never, I guess. Okay, this is going to be desk read here. And ports I don't need, so that goes away. Yeah, again, this is just a high level, you know, test design for now. It'll be reworked a bit later. So we'll take this, copy that. That is for descriptor reads. Now for completion writes, we got to do basically the same thing, except these are all CQs, base address. And then, do we need to interchange anything? No, I'm just going to have, yeah, I'm just going to call this, yeah, so this is just going to have the producer pointer as an output. And no consumer pointer, because we don't care about the consumer pointer here. Okay. So we have the completions here, that goes away. Okay, very nice. And these are going to be write and read. Okay, perfect, perfect. So there we go. That looks, I think, reasonable. This is going to be the CPL write logic. Okay, there we go. So we got the descriptor read, we got the completion write. Okay, now for the, well, obviously these modules are not implemented yet, but that's a starting point. All right. So let's try to figure this out then. For the descriptor read, what do we need to do then? We need to have a RAM and we need to have a DMA engine for actually doing the read. So let me go into the test bench for the RAM, and we can go ahead and create the actual RAM. Right, so here's the RAM. This is going to be used for the descriptor read. And the size, let's call this 1024. It doesn't need to be very big. Pipeline 2, why not? DMA RAM. Okay, DMA RAM write. This goes in here. So we have the read port there. All right, so clock and reset. That's pretty straightforward. All right, let me go take a look then at the RAM again here. Put that away. So the RAM I'm also going to need an internal bus here to handle the reading. Okay, cool. So that's that, and I can put this up here. DMA RAM read like so, and this is going to be now. Okay, so I transfer all that stuff through to make a copy of that, and so when we make a request to the DMA engine, right, it's going to be a read request against the host. DMA engine will fetch the descriptor. It'll write it into this internal RAM. Then what we need to do is read out of the internal RAM, and that is done with a different DMA engine that I have here, right? The DMA client access source. And this module will enable us to read that and then transfer it through. So I have several different components here that I need to deal with. So I'm going to go ahead and copy this over here. So the RAM, I already have that. That's the RAM read interface, right? DMA RAM read. That's going to go here. And then the EXI stream, okay, that works. The DMA descriptor, I need to figure that one out here for the internal DMA. Okay, but that's a good starting point anyway. The DMA RAM instance. And then this is a DMA. Okay, great. Enable. Perfect. Okay, so RAM read data. Okay. Okay, things are slowly coming together here. All right, so RAM address width, I guess. Well, I'm just going to be a little quick and dirty here. I don't think that's quite right, but we just need to read one descriptor out of the RAM, and we're only going to read it from one location in the RAM, so that keeps it very, very simple. The length, well, it's a fixed 16 bytes, so I'll set it to 5. Tag width, I mean, we don't really need tags, I'll set it to 1. ID width, I don't think we're using any of the ID functions. I'm probably going to use the user, so turn that one on. That off, although actually I think I do need dest actually, width of 1, ID width, not using that right now. User width, that's also going to be 1. Okay, cool. Data width, I'm going to follow the TX descriptor here. Okay, except this one, dest en is 1, dest width is 1. Okay, so I have that. Now I'm going to use some AXI stream logic that I have here. I should have a demux that I can use, right? Demux. So the demux will be able to send the request to the appropriate module, right? So this one here, I can make a copy of this. Run to micro descriptor read, right? So I can take this, here's the descriptor read, demux. All right, and then this is to the tdest route of, yeah, turn that on. AXI stream in, so I have the data coming in, and then out, I gotta figure that out. Turn it on, drop is 0, select is just tied to 0. Right, and what I need to do now is create the outputs here. So this is slightly annoying because it would be great if I could just concatenate those things together, but I can't. So this needs to be set up like this. This is all going to come from tx desk. All right, tx desk, dest en, and dest width. All right, great. And this one I will connect here. So the idea with this setup is I'm just trying to be as expedient as possible. Ultimately, this module would probably have like a custom DMA interface in it, but you know, for the time being, this is going to make the most sense. The other thing I need is the access I module, and this is how I do the unpacking without, you know, eating up a lot of lines of code here. So descriptor read module. Whoops. Annoyance about bed. All right, so we'll just call this tie 1, and this one is going to be coming from desk 0, and then this one is going to be supplying TX desk. Actually, now that I think about it, let me save some annoyance here and just make this make these arrays to begin with. Okay, that might actually make things a lot easier, because now I don't need to bother with this here, right? So I don't need that, I don't need the demux, I can get rid of all this. Okay, all that goes away, and then I can just put a oh wait, shoot, no, I do still need this actually, yeah, but I can put this here. Okay, great. That, don't need that anymore. Okay, access tie, I don't need that. All right, that simplifies things quite a bit. All right. Okay, great, so that simplifies things. So the request comes in, we can request for one or the other, then the descriptor port here will carry the descriptor on the way out. Okay, great, that's pretty straightforward. So we got the demux set up here, tdesk route. Okay, we got the read data coming in, read data going out, coming in here. Okay, that's perfect. This descriptor output feeds the top. Okay, great. Okay, so now I need to write a little bit of logic which can actually keep track of these pointers and issue the requests both to the top level DMA engine and to the internal DMA engine. And then once that works, we're going to have a very similar setup going in the other direction for handling the completions. So I think I'm going to do the same thing actually here and make this EPL2, right? And then I can go ahead and bring in the arbitrated mux and such. So a lot of this is stuff that I think will be kind of reworked going forward. Oops, I don't want the actual mux code. I actually want to pull the test bench code for that. All right, so I will do that. For completion right, I have the mux instance. I can have the completion input here, and then the output here. This is all going to be coming from see here, 0.that, and then ID en is 1, ID width will be 1. That's fine. All right, so scount 2, update TID 1, round robin. Okay, that looks good. So this will go ahead and merge that together, and then I will have the combined path here. Okay, so we'll get a completion, it'll come in, and then we need to transfer it into the internal RAM and also pick it back to the host. All right, so we have that. Now I need the other infrastructure for this, including the actual RAM here, and also the DMA client, although this will be the other DMA client, so I will grab that in a minute. All right, so we have the RAM right here. We have RAM write, we have RAM read, that looks good. Yep, RAM read, RAM write, okay, perfect. And then I need one more copy of the DMA engine, except in this case, it is the other one. It's the sync. Okay, so here's the sync instance, and then I also need the DMA descriptor for internal and such. All right, so we have the write module here. Here's the DMA descriptor, the DMA RAM. I already took care of that. The write data. Let's see. I think there's a lot of this I can copy over from this one as well, right? So the descriptor interface. Most of this I think can be done the same way. Yeah. See here, immediate enable 0, length width 5, tag width. I'll just set that to, I do 1. Okay, yeah, that's fine. Access ID EN. Actually, I don't need any of these, right? Oops. I think anyway. Well, I guess maybe I do need the ID, right? So when it pops out of here, then, well, I don't know if I need that or not. But I definitely don't need that, and I don't need that. Okay, great. And then for this one, this is all going to be based on, or wait a second here. Okay, I don't need that one. CPL combined, I already have that, so I just paste this in here. So that one is right there. DMA RAM write, and then the internal DMA descriptor, that looks good. Okay, great. Enable and abort, that goes away. Enable 1, abort 0. Okay, perfect. Okay, and then this is the DMA instance here. Okay, great. A lot of boilerplate that needs to go together for doing all this data path stuff. All right. Now what about for the actual packets? I think actually for the actual packets it's going to be quite similar. So for the descriptor read, this in some sense is going to be quite similar to the transmit path. So I'll go ahead and copy this and paste it in here. And for the completion write, that's very similar to the receive path. All right, so let's go ahead and simplify this now. This is going to be for the TX, and this here is going to be for the RX. Okay. All right, so we have that, and then this is going to be for the, well, let me think for a second here. So for the RX path, we're going to need a, well, we're going to need a completion out. We're going to need a sync for the descriptor in. Actually, one more thing to take a look at here. So this one, how did I name that? Okay, I did put that axis, whatever. All right. Axis CPL, just for slightly better naming here. Okay. So for TX, we need all the same stuff in the transmit direction. So I have the internal RAM, right? And I'm going to make this a little bigger. I'm going to make this 4096. We have the RAM write, RAM read. RAM write comes from there. RAM read is over there. We have the DMA descriptor for the internal. The width for this, I'm going to make that 16 bits. Tag width, that's fine. Everything else I think is okay. I'll get rid of the destination because that's fine. Axis IF here, M-axis RD data. I guess this can just be sent directly out the top of this thing, right? So if we're talking about TX, then this is going to be SRC for the TX data. And descriptor request, there's 1 bit there. And the descriptor is again, okay, there's a descriptor coming in. We got the completion going out. Okay, great. So, okay. Oh, descriptor, this is going to be sync. Okay, right. Descriptor request. Okay, great. And then I can copy all of this, bring it over here. In this case, the RX data, it's going to be a sync. Okay, so desk request, access desk, access CPL, that all looks reasonable. I don't need any of this. I do need that. Okay, and same thing here. Okay. Oh, all right. This is a bit of a slog to get all this implemented, isn't it? Okay, so again, we have the RAM, we have the DMA descriptor here, we have the read data here. Actually, right, I can get rid of that. I don't need that. The access source, read data is going to be axis TX. RAM read, DMA descriptor, that looks good. Get rid of the debugs. Okay, perfect. And then for RX, I have the axis IF. This is for the combined. I don't need that. That goes away. ARBMUX, I don't need that. I have the RAM. I'm going to again make this 4096, a little bit bigger. I have the write, read is going over here. This is going to be RX, axis RX, there we go. DMA descriptor, okay. That looks pretty good. So the data comes in, it gets written out into the RAM, so on and so forth. Okay, len width, that's going to be like 16 bits. Tag width, I'll leave that as 1. Turn that off, turn the other stuff off. Actually, well, user enable should probably be 1, but I'm going to call that like that for now. All right, cool. Okay. Progress, little by little. Do we need anything with select lines? No. Oh no, this is fine, All right, Houston. I see. You want some pets? All right, cat cam. There we go. Perfect. Okay. So at this point, we have kind of the core data movement portion, I think, sort of put together. So what I need to do now is make some of the connections between these modules and implement that. Now I need to implement all the control logic, basically. So we have the core. I'll just leave that RAM here for now, but that will need to go away soon-ish. So let's go ahead and start plopping these things down here. Right, so we got the descriptor read, we got the completion write. All right, got the read, we got the write. Now I need the TX path and the RX path. Okay, so TX and RX. All right, great. Okay. Lots of stuff to wire up here. So let's go ahead and start cranking through it, shall we? There's the clock and reset for this, and for that, and for this, and for that. Gotta add the names, RX instance. And let's see here. Okay, completion write and the descriptor read. Okay, great. Now, oh, I need some other stuff too, don't I? Right? Because I've got two different things that want to read and two different things that want to write. So this means I need a bunch of additional logic that's going to sit between here and the DMA engine. So need to do a little bit of planning for how all this is going to come together, right? Okay. There's also a bunch of control signals that need to be hooked up. So let's start out with just getting those laid out here. These are all just going to be wires for now. Okay, so there's that. There's that. And similar story with the TX completion queue information. Okay, I guess these don't actually need to be logic. Wire's fine. And then I have these guys. All right, great. Okay, perfect. And right, so I have descriptor request signals as well from TX and RX, as well as the actual descriptors. All right, so the descriptors and the completions. Okay. I'm going to go and wire up the descriptors and the completions because that's pretty straightforward, I think. Start with that one. So let's do wire. Oh, descriptor request 2. Tobias is saying, don't let the stream extend beyond 12 hours. Well, what are we at right now? 5.5 hours? Giving me 2 different numbers here. It says 5:30 and it also says 6:30. I don't actually know how long it is, but I've got a hard stop in a couple of hours anyway, so that's not going to be a problem. As long as I don't forget to hit the end screen button or something. Yeah. Anyway, let me go ahead and get this figured out here. All right, so the data width, I'm going to transfer the whole descriptor in one shot. So 16 times 8, keep enable. I guess that's normal. I'll keep the standard value for that. Last enable, I think that needs to be turned on for most cases. ID enable 0, enable 1. Yeah, ID enable 0, ID width 0, dest enable 0, dest width, don't need that. For the descriptors, I think I do need that. All right, so there's your descriptor. All right, and then we do this again for the completion. So CPL, do those, same thing. Okay, except in this case, do I need user for that? No, I'll turn the user off. I don't need that. All right, great. So access desk. This I think is fine. Okay, and then the completion over here, that looks pretty good. Okay, great. Now I can go ahead and set up some of the connections here, right? So we've got the descriptor request connection here, so that's going to be on channel 0, and the completion here, same deal, right? This is going to be on channel 0 as well. Yes, and then these guys, I will transfer that down here, and similarly I will put this over here as well, and these are all going to be on channel 1 effectively. All right, and then for the Mac, okay, so now I need some FIFOs for the Mac because these are in different clock domains. So for the TX and the RX instances, I need to pull in a couple of FIFOs here. And I need some associated connections with that too. Let me see. Simplest way to do that. Well, I had something in the example design, but I will go over to the Ethernet example design again and yank that FIFO. Okay, so RTL, FPGA core, FIFO is down here. I guess I need the FIFO and I need a couple of intermediate connections as well here, right? So I need that. Now I'm only going to connect one of the ports. So yeah. All right, so we'll start with the TX direction here. I have the TX. The internal TX connection here. And I'm going to call this, and make it 64 on the data width for now. ID width. Am I using the ID for anything? I'm not using the ID for anything. So I'll clear that out of here for now. That's max TX int, and then that's going to be, that'll be on TX data over here. Okay, great. Okay, and then we got to do this one more time for RX. I also need the FIFO, which I'll grab that in a second, but one step at a time. Actually, I guess what I should do instead is do Mac access TX dot data width. Okay, there we go. Mac access RX dot data width. Okay, cool. This will be Mac RX inst. Great. And same kind of thing here, right? This will be the Mac RX inst here. Okay, that looks pretty good. So I still have the control logic and the DMA connections to make here. Well, okay, and the FIFOs. Let me finish that up real quick here. So the FIFO was all the way at the bottom. All right. Nice. Up here. Okay. Houston, you're being a very funny kitty here. Okay, so I have that. Let me go back to the core logic here and I'll get the FIFOs in place. So this guy on the RX path here is the Mac RX clock. And the Mac, I guess I can just make this Mac here, right? Mac. Well, all right. Mac axis RX, right? So that comes in and then this drives out. So I have clock, no N. Oh, I don't even need an N here, do I? This is just going to be all zeros. Zeros. All right, there we go. 16K RAM FIFO, RAM pipeline. RAM pipeline 2, frame FIFO 1, everything else looks good. Right, okay. Cool. So there's clock, and here's reset, and here is the, what was this one? Mac RX int, and there's no N associated with that. Okay, perfect. So we have that, and I'm going to go ahead. This is going to be the RX FIFO, right? And then I need to make copy of that again for the TX. So I do that. Okay, here's the TX FIFO. TX FIFO. All right, so we got, these are all TX here, and I need to make this M. This goes down. This comes up. They're all S. And this is Mac TX int. Oops, that was a typo. There we go. All right. Ugh. Slowly coming together here. Okay, let me make sure I have some of this stuff fully up to date. So I have that in here. I also need to add the let's see, this would be the axis async FIFO.f. That's one thing, and then I also need Corundum micro RX EX. Let's see, this is desk read and CPL write, all of those modules, and there's a bunch of other stuff I need too, right? So I need a bunch of DMA related stuff. Let's see, this would be DMA. What are these modules here under DMA? I need several different things, so I need the, put that away for now. RTL. I have the DMA client access source and sync. Let's see, it's a DMA client access source, access sync. Let me see here. I'm gonna need DMA. I'm gonna need the DMA IF mux rd.f and write, right? So the read and the write versions of that. I need all right, I need the RAM, TX DMA PSDP RAM. Okay, is that an F? No, that's an SV. All right, cool. Probably more than just that, but you know. Okay, Houston is running off. See you later, Houston. Okay. Okay, great. Great. Where was I? Got the core, I've got most of the data path stuff connected. Now I need to figure out all of the somewhat more middling DMA related connections. So this will take a couple of minutes here to get this figured out. I need to create 2 copies of the DMA interface mux modules. So there is a DMA IF mux, and then I have separate read and write modules. So I'm actually just going to pull out of the DMA IF mux module here. I could use the top level one, but I think it's a little bit more straightforward to keep them separate. All right, so DMA desk IF. Oh, I think that one's already pulled in. Maybe? We'll see. If not, I can always add it. All right, so going back to the core, I need to create. Where am I going to do this? I guess I will do this. Underneath these initial control signals here. All right. Okay, so ports, it's going to be 2. It's going to be yep and yep. Ports 2, yep and yep. Okay. So this is going to be DMA mux and write DMA mux. All right. A lot of stuff that needs to be strung together for this to work here. All right, so the DMA descriptors to the DMA engines. So I just need to add desk. Yep, okay. And desk here as well. Okay. And then I need DMA RAM read and write. So that looks fine. DMA RAM read, DMA RAM write. Okay, great. So I need to create these client interfaces then. Okay, cool. So let's see. We go to the PCIe wrapper, and I'll just make a copy of everything here. So there's a read desk, write desk, and the DMA RAM. Okay. Copy all of that. I will go back to the core module here. So this is going to be the write, and I'll call it int, and it's going to have 2 channels here. Write desk 2 int. Okay. That looks good. This looks good. And I will go ahead and I'll make a copy of this. I will delete that. Go down here. All right. So that is looking more reasonable here. It's going to be rd int DMA RAM rd int. All right. Now where does this go? DMA RAM read. So this is 0, right, for the completion write, and then for the right, yeah, okay, yeah. So that's RAM read for the completion write, and then I need to do one more for the receive data path. Yep, okay, this will be on port 1. Okay, great. Okay. This really starts blowing up pretty quick. Okay, DMA read descriptor. So this is going to be, I'm just going to transfer through all of this effectively. Okay. I think that's right. I will need to make one minor adjustment, I think, and that is that the tag width is going to be reduced by 1. And select signals. So for read, how is this going to work? So for read, we're going to have to reduce, well, I think I'll just reduce all the select signals by 1, just to make sure everything is happy. All right. And then I will go ahead and paste this down here. This is all. What happened? Why do I have a different number of signals here? Oh, I see. There's a ASID EN that's not connected here. Is that what it is? Guess so. Address cell. All right. So, okay. So there is no ASID on the source, right, but there's another difference as well. Oh, there's also no immediate. I think that's right. Yeah, okay. Well, all right, whatever. I'm just going to transfer these things through as they are. All right, DMA, oops, DMA write disk. Okay, great. Oh. Request side. Okay, perfect. All right. So that passes all that through. I need to do the same thing. I need to reduce this by 1 and reduce select signals by 1 as well. Oops. Select width, not select enable. Okay, reduce that by 1. Yeah, okay, so I messed that up. This should be -1 here. Okay, great. There we go. Okay. I may need to make some other cleanup steps here, but you know, one step at a time. Yeah, I guess I didn't have this select width on the other side. Anyway. Okay, so that's that for the descriptors. Now let me get those hooked up, right? So the right descriptor gets hooked up here, right? Okay. And then similarly, the right descriptors need to get hooked up down here. So there is right descriptor, so this is going to get channel 0. Okay, and there's another right descriptor down here. Oops, this should be channel 1. Okay, there we go. And then this is going to be getting read descriptors. Actually, I guess I can just do it like this. This 1, right? Yes. Okay. Oops, what happened? There we go. All right, so I can get rid of these. There we go. And then I need to do one more of these here. Okay. And this is 0. Okay. And all of these get ints. Int 0, and I need to remove that. Okay. Okay. How are we looking at this point? I'm thinking it's good enough to do a test build and see how badly it blows up. Not a test build, but, you know, test run of the synthesis, not synthesis, test run of the simulation and see what happens. Yeah, that would be, I think, pretty reasonable at this point. My guess is that this is going to blow up in a really bad way in many different ways, but we'll see. Yeah, okay. Duplicate. Okay, well, we can fix that. That's easy. Here's the RX FIFO, and I think it was a TX FIFO that was on top. Where was the TX FIFO? Maybe the TX FIFO was at the bottom. I can't remember. Oh, well, this was RX. All right. Okay, that's TX. Cool. That's TX FIFO. That solves first problem. Okay, then. So now I have a bunch of stuff in the completion right, because I renamed that. Okay, great. So that... Okay. What next? Can't find definition of access data width in descriptor read. Yeah, that's a good question. Why are these all access whatever? That's not correct. Corundum Micro TX, we have access TX line 94. Doesn't make sense. That TX data, okay. And similarly on the RX, that's RX data. This should be again RX data. Okay, great. Um, 389 in the core. we have another typo, 389. 389 here. Okay, that should just be int, not inst. Okay. Okay, so we have another couple of complaints here. 119. 119. Okay, so this is going to be DMA int. And this is again DMA RAM int. Alright, great. That fixes most of those, I think. And now we have a few other complaints here. Oh. Okay. Okay, great. So, some more signals not quite found yet. 101, okay. Let me think here. Okay, yeah, I guess all of these just need to come from the higher level parameters here that are getting fed in from the DMA engine. All right, so these are all going to be okay. This is going to be equal to I will do DMA RAM write dot okay, great. So that should take care of that, I think. Now I actually think I may have a minor issue with some widths here. Oh boy. All right. Update TID requires IDEN set. So this is coming from. Yeah, all right. So this is an annoying verilator bug where it's actually not telling me what instance this is. But okay, update TID. I think this is coming from. All right, this is going to be. What is this going to be exactly? I guess that maybe if I need to set some of these things, I need to set some of these here. Okay, so this is looking at the descriptor. Is it the descriptor or the completion? Right, so I got update TID times 2. Oh, these are the same line here. Same line, same instance, different complaint. So this is going to be update TID. I'm using the TID, I think, in the RX, right? Or not RX, in the completion, right? Yeah, update TID. Yeah, okay. I guess I just need to, the simplest thing to do is probably just to make sure that the ID signal is enabled one level up. I need to look into that, because that should not be necessary. Okay, I am looking for where that interface is defined with CPL. All right, so I'll turn on ID here. See what that does. Descriptor address width is not sufficient. So this is coming from the sync, client access sync. Right, but is this coming from the one in the transmit or the receive, or this is one annoying thing about Verilator, right? They ostensibly this %m is supposed to be expanded to the instance name, but Verilator is complaining about this. Well, okay, so here's a complaint about that, but it also complains about, oh, here we go, expecting the expression to be constant, but it can't convert a scope name to a constant. Like, how does that work exactly? How are you supposed to actually use this %m thing if literally using it is an error? So that's a problem. Anyway, so this one is coming from, I'm assuming this is the RX, and the width of this thing, I guess, is not enough. RAM address width here. Okay, yeah, I guess so. All right, fine. Let me make that 16. Okay, great. So that looks better. Okay, I need to fix some of these, but or do I? Well, I can just turn off some of these with complaints. All right, I'm going to ignore those for now. Address width is not sufficient for the, right, that'll be the TX. Again, same problem. Yeah, I made the RAM bigger here, so with the bigger RAM, it's it needs a wider bus. So this is one of the advantages of System Verilog, right? It can actually check and complain about stuff like this. Descriptor address width is not sufficient. More complaints for both the source and the sink. I'm not sure where these complaints are coming from now because it's not telling me the instance. So anyway, I'll just make this bigger and we'll see what happens. All right, mod missing. Cannot find file containing taxi access demux. All right, I need to add that. Let's see. Corundum micro core here. All right, so taxi access. I think I have the arb mux and the demux. And I think this one is an SV. The other one is an F. But we'll find out here. Okay, we got some more complaints here. Port connection RAM read expects read SLV, but it got write master. That's not correct, obviously. RX. Let's see here. All right, that's RX TX. Station write. Okay, this is RDSLV. It's working quickly. You can make lots of little mistakes like this, but at least we can grind through these without too much difficulty here. Port connection. All right, so this one is in the TX instance. Oh, that should be, yeah, okay, I see. Gotta make sure all the ports are correct. But it's a heck of a lot easier than managing all of these directions separately. Okay. DMA request, DMA status, so a bunch of these are still backwards. Request, oh, right, so this should be SRC. And sync. Alright, so I think I got all these backwards. Alright, and then finally here is we're issuing requests and accepting the status. So you got to get the sources and syncs the right way around. Otherwise, it's not really going to work, is it? Okay. Right, and they're all wrong here too. src sync. Okay, I copied it from the DMA engine, so actually I guess that makes sense why they're all wrong. Oh, and then these should be, yeah, all backwards. All right, I think we're finally good here. Okay, so we got the width, trunk, width, expand. All right, so we got another tdest route requires dest en set. Yeah, a couple of these I guess I just need to fix somewhere else. Okay, so this is for the descriptor read, and I need to make sure, oh, actually, not for the descriptor read, it is, so that one is a to-do, and then dest en here is also a to-do, because those, it shouldn't need to be activated. So anyway, all right. Okay then. So now I have a bunch of select with complaints. All right. Okay. So I think I know what's going on here. The issue has to do with the select signals from the top level. Actually, let me take a look at. Okay, so I think this may be coming down from the top level PCIe US level, where these are being defined in the first place. Yeah, RAM cell width. Okay, so first I need to do that. And then what I need to do is take this in the core logic, and I need to shave off a bit. Where are we here? So somewhere we create the RAM instances here, and this is going to be RAM cell width -1. And there should be another one, right? RD int, RAM WR int. Okay, there we go. All right, so cell width for both of them, and then okay, great. Okay. DMA source cell, DMA dest cell. Okay, so we got a couple of other locations where we have an issue with the select width. Let me think about this here. All right, let me just make sure these are all connected here. That solve anything? That was 2 errors, 6 warnings. 1 error, 5 warnings. All right, yeah. So I think I need to fix that as well somewhere else, but I will deal with that later. Okay, so there's that, and then I need to do one more cell width here. Okay. As the idea with all this stuff is you have to winnow down the ID signals and the select signals as you progress through the hierarchy. Okay, let me see here. So we got a couple of things going on here. All right, let me see if I can figure out where some of these issues are coming from. So the first one here is for the DMA client access sync. We have a difference in ID values here between, why would that be the case? It expects 1 bit, but it generates 8 bits. Oh, I see. That's the ID here, and that's the dest here. Okay, yeah. All right. Gotcha. All right. So this is in both of the DMA modules here. For the sync module, it's line 182. Okay, let me here. Line 182. So this is something where. Okay, I see. So this is going to be actually probably the simplest thing to do. Yeah, there's a few width-related things that I don't necessarily know the best way to handle this. So actually what I'm going to do is I'm going to kick the can on this by just temporarily disabling the lint message on this line. Alright, we'll do that. Obviously I need to go deal with this properly at some point, but this is how it's going to have to work for the time being. Wait, where was that one then? This is the... Oh, also in the sync. Oh, okay. Literally just the next line. Great. Okay, and then there's another issue with the sync at some point. Where the address is truncated. I see. Yeah, I think that's probably fine. Yeah, okay. So 250. ADDR mask. Is there an ADDR width? Okay, so ADDR next is what? How wide is that register? Yeah, this is RAM ADDR width here. Okay, cool. Alright, so everything's looking good except for this one weird message coming from here where I seem to have doesn't make much sense, does it? Alright, I'm wondering if we have some sort of a disagreement between the configuration here. So if segs is not equal to DMA RAM rd.segs, configuration mismatch here. So segs, and then also this is looking at the data width. Yeah. The address width being different is fine, but the data width and the segment width, if those are different, that's a big problem here. Oops. Okay. Yeah, interface configuration mismatch. Bunch of stuff that doesn't match. So what happened there? All right, let me see here. Doesn't really give much actionable information about what happened, but it's got to be one of these guys where this has been redeclared somewhere. So this is coming from the RAM right. I mean, this
guaranteed to match because it's being generated direct from there. There's a RAM read. Okay, but this one, this is again, it's pulling direct from there. This is pulling direct from there. This is pulling direct from there. So what the heck? Why would we be getting any kind of a mismatch at all if all of these match? From RAM segments, RAM right. I don't know if this is actually multiple modules that are complaining or if it's just one. I guess there's 3 different complaints about this. So this could be 3 different modules that it's complaining about. Another annoyance about Verilator is that, again, it's not telling me what instance this is, so it's kind of hard to track down exactly where the problem is coming from. Okay. Mismatch, obviously, but which one is it? And this one is interesting. It expects 256, but the array cell generates 128. So, yeah. Well, it's a read response data. Why would that be a problem? Alright, so this one, DMA RAM, I just have one DMA RAM here, right? And this is coming from, where is this specified here? RAM segs is set to 2. So this is DMA RAM, and then this should get passed down to here, and it gets passed down to here. Okay, that's reasonable. And then over here we have the RAM read and the RAM write coming in. They get passed in from the same component, so this shouldn't be a problem, I don't think. We get RAM segments here, that gets passed over here. That looks fine, so that's the RAM write int, and it's also going to be used down here, RAM read int. We don't have any complaints anywhere else. Alright, I've noticed one weird issue with Verilator. Alright, so this is DMA RAM write, DMA RAM write, okay. This one is DMA write. This is DMA RAM read. Descriptor read. So that's write and write. Okay. That's read. And yeah, okay, there we go. This is a Verilator bug. That should be a totally red flag error if that name doesn't even exist. Okay. Doing something different this time. Hey, it built that time. Okay, excellent. Well, this is not going to run, but that is a huge step. Okay. Well, by building, I mean the Verilation process completed. Okay, right. So next step, control logic. What we need to do now is write a bunch of control logic to make all this stuff work, and I'm trying to think of the most expedient way to do this. I guess what I should start out with is actually just going ahead and implementing the register space for AXI Lite, and then we'll roll with that, right? So, oops, I need to make a bunch of these registers. Okay. Okay, I guess that's the starting point here. Okay, let me think about something actually. So
Actually, I need to add a couple of additional signals here. So I'm going to go ahead and do a couple things here. First is I'm going to rename all of these, or I'm going to change the types properly to logic, right? And then the next thing I'm going to do is I need to add some reset signals, some pointer reset signals here. All right, so the idea with these pointer reset signals is they can be used to reset the state of the queue, so you're always coming out from the get-go in a consistent state. Okay, so we defined all that. All the reg values here need to be initialized to 0. Okay, great. Oh, and the pointer reset, that does not need to be 16 bits, that's just 1 bit. Okay, great. Okay, so the test bench actually ran to completion, although we're not using any of this this new data path, so it doesn't really make that much difference. All right. What I'm going to do now is go over to the completion write and add inputs for the pointer reset here. And again, RxCQ pointer reset. All right, cool. Save that, and then we'll go to desk read exq and RxQ. Cool. All right, let me go ahead and make those connections here. Rx instance. Oh no, this is only in terms of the descriptor and completion handling. Yes. All right. Okay, so there's that, and then again, same thing over here. Yeah, so this is a very simple design, very limited number of queues, but the idea is that this can be improved on incrementally going forward. All right, so now I need a very basic AXI Lite register space implementation. So let me think here. All right. So for AXI Lite, let me go take a look at the interface for that. AXI Lite IF. There we go. All right. So here are quite a few signals associated with this, right? Yeah. Okay. All right. So what do I need here? AW ready? W ready? D channel. AR ready. Okay, and then everything but R ready. All right, cool. So this is now AXIL. AXIL. All right. I don't need the user signals at all. All right, let me go take a look at the AXI Lite interface again. I need to make sure I'm doing things correctly. So for the well, all right, I'll figure this out. Okay, so take all those signals, and one more time over here. All right, so I need to do all of the, I guess I need to do what I just did here. Actually, let me, yeah, I'll leave those in. All right, let me just duplicate this. Okay, great. Okay, so this is going to be, these are all going to be WR. All right, so resp is 0, user is 0, resp is 0, user is 0. All right, so then the resp and user can go way up here. All right, excellent. So let me go ahead and add a couple of additional local params here. All right, great. So we have both of those now. This is AXIL data width, and these are all going to be regs. Well, actually, for the most part, these are all 1 prime B0. All right, great. So that's that. Okay, great. Now I take all of these and I go over here, and let me think for a second here. Well, I need if reset at the bottom. If reset. Okay. So the reset, I don't care about our data. But the rest of these all get set to, zero like that. Okay, great. All right, and then what happens here? So there's if saxil wr dot b, sorry, aw valid, and saxil wr dot aw or dot w valid. Okay, then we can do a write. Similarly, if saxil rd dot ar valid, then we can do a read. Okay, cool. AR valid. Let me see here. So EW ready, W ready. These are going to be set to 0 by default. Same with AR ready. That'll be set to 0 by default. For reads, we'll set saxil data reg to 0. Okay. R valid. Again, that also needs to be set to 0 by default here. Okay. Well, oh no, actually no. That's a different story. All right. So these guys need to be done differently because we're looking at valid and not saxil wr dot be ready. And similarly, this is going to be the same kind of thing here. rd are valid. Okay, great. So if, all right, and then in this case we set both of these high, and in this case similarly we set this high. Okay, cool. Is that right? I think that's correct. I gotta double check just to make sure, but how have I handled this kind of thing in the past? Let me just take a quick peek at something and make sure I'm not doing something totally stupid. Where would I have one of these to look at quickly? I wouldn't be there. Oh no, I guess I do have all right, I think in the sample design here for PCIe, that's how it's built, right? Got it. Okay, got it. And not B valid reg, and not R valid reg. Okay, perfect. Okay, very, very, very nice. And then what I do here is I'm going to go ahead and add some case statements here for both of these. How do I usually do this? I do write and then read. Okay, great. All right, so this is going to be 16H0. All right, so this is going to be S AXIL RD dot ARADDR. Goes 15 down to 2, and then just to make sure these work out nicely. Okay. So that, I think, will work there, and then I need to do the same thing for writing on the other side. Okay, great. So as you can see, making an AXI Lite register interface is not particularly complicated. Okay. Oh, this is a WADDR. All right. So these are all the registers that I need to poke here. And let's see, how is this going to work? So first I'm going to go down for reading registers. And then also, whoops, so I'll do that, and then that, and these guys, same kind of thing here. There we go. Okay. So for all of these, the way this is going to work, I got to set this high as well. Yeah, and then I got to do that as well here. So I accept that and I generate that. Okay, same kind of thing here. It's going to be valid. Okay, great. All right, so for all of these, we want to be able to read. So let me just make this as simple as possible. And we also want to be able to write to a bunch of these. So let me go ahead and paste that. Bam. All right, I'll leave it as is for now. Okay. So, reading here, this is going to be SAXIL R data reg. It's set to all of these here, but the base address ones, we need to do these in two pieces, right? Because we have the 31 to 0. And then we have the 63 to 32. Right, excellent. And the reset registers, I don't need those. Those will be handled differently. Okay, there we go. And let's go ahead and space this out. So the TXQ, I will put this, the TXQ, I'll put it at 100, RXQ at 200, TXEQ at 300, and this one at 400. Okay, so this is 404, 408, 304, 308, 48, C. Okay, 48, C. All right, great. And now the idea is when we write particular registers, it will trigger that. Why is this highlighting this incorrectly? If I messed up the syntax somewhere, I don't know. It doesn't look wrong to me. That's weird. Oh, it's because this case is up here is wrong. Yeah, okay, great. Okay, perfect. All right. Okay, let me go ahead and I will fix that, and then I need to go through all of these here. All right, so this is then going to be W data reg. Yeah, okay.
Okay. Actually, so is there anything else I need to do here? I guess this is fine. Okay, so if I write to this, then I need to do a pointer reset here. So this is going to be right. So I write that to 1. Okay. Do this here as well. In fact, I should have added an enable signal, but oh wait, no. PTR reset reg. Okay, this is set to 1. Yeah, and then the same kind of thing here. And again, here we go. So this is again PTR reset reg. Okay, and I also need to make sure that all of these reset regs get cleared properly. Do I need to change anything else? I don't think so. Okay, great. So I got that. That goes here. All of these get set to 0. Okay. Great. So this is actually starting to look pretty reasonable. So I've got all of this in place for setting all of these pointers. Now what we can do is go to the Python test bench code, and let's see if we can actually trigger to this to do something useful. All right, so we've gone ahead and we've set up all of these things here. So for each of these rings, I need to go through and perform several operations against the bar space. So what we're going to do is we're going to write to each one of these in sequence. So let's see here. We got to write the base address for this thing, right? So this is, how did I do it? Was it RxQ first? TXQ first? I can't remember. Let me take a look at exactly what that register layout is. Okay, so TXQ, RxQ, CQ for TX and RX. So TX is first over here. Okay, great. So I write here, and I'm going to write, I need to get the base address again of the RxQ. How am I doing this here? Right D word here. RxQ. Right, so we do that, and then we do this again for 104, where we do this shifted by 32 bits, right? And then we're going to write 8, 0, and we're going to write C, 0. All right, cool. So we do that. I mean, this is really just the producer pointer and the consumer pointer. Well, actually, all right. So with this one, we're resetting the rings consumer pointer. All right, so we paste this down here. We need the address again, right? Address for the all right, hang on a second. I need the TX. Sorry, this is going to be for the TXQ here. I got to do this and I got to do this. All right, so this is for the TXQ, and these are all. Oh, RxQ is 200, 200, and then this is 400, and then yeah, okay, cool. This is TXQ producer pointer. Well, we can't even access that for this, so that's fine. Okay, great. And this is RxCQ, right? And then finally, I got to do this one more time here for the TXCQ, and these are 3. All right. Let's see if that works and if these actually get set properly. Oh wait, I don't. Why am I incrementing cons? I'm going to implement prod.
Okay. Okay, great. So with all of these, now we can actually start updating the pointers. So when I update this, I can then update the RxQ producer pointer. With this one, I can do the same thing and update the, well, sorry, that one was a TXQ. This one is the RxQ. There we go. Okay, I need to fix a couple of signals here. Let's see. So I got to go back to the core. And we're looking at line 103. Oh, these should all just be regs. Okay. Okay, 134, something is also unhappy. Oh, yeah, because this should not be wdata reg. This should be, there we go. Okay, so it's complaining about a bunch of stuff, which makes sense. Let's see, so 100. What is this here? Okay, that's 0. That's right. Okay, this is 16 prime that. Well, actually, yeah. Broad reg 16 prime. There we go. Okay, so prod reg. Okay, let me just see here. Oh, I know. This will just be 15 to 0. Okay, and then again here. Ah. Okay, I think this will work. I mean, it's definitely far from optimal, but it's a question of, is this going to work well enough for just something really simple? Oh. Yeah, okay, so I can't even write that, and I can't even write that. Okay, great. Okay. This is my kind of stream. How's the dev going? Actually, reasonably well at this point. I still have a lot of control logic that I need to put together, but for the most part, this is, well, it's coming together. Yeah. What am I looking at here? Case values. Oh, all right. Yeah, I think there's a good chance I'll actually have the HDL for the just very high level, not really very high, very stripped down implementation of the core data path working tonight, or at least mostly working tonight. I don't know if I'll have time to actually write the network device driver. We'll see. Currently 5:30. I got a hard stop in like an hour and a half or so. So that's not that much time, but a lot has been accomplished. So yeah, so like my goal was to get to the point of having ping working, but I suspect I might not be able to get all of that operational today. We'll see. It's taken a little bit longer than expected to put all this logic together. But I mean, look at this. This is like the 500 lines in the core logic here, and then I have, well, all right. So I need to do a bunch of work on these modules in terms of putting together a basic state machine in each one of these for, you know, managing the sequencing of stuff. But yeah, one step at a time. Oh, I guess what I need to do here is wait for a while. Working on a digital PLL. Digital PLL to do what? Be interesting to hear some more details on that. I'm waiting for Verilator to finish building this so we can see what it does. Make sure my little AXI register interface works. All right. Looks like that built, so now it runs. No, okay, something failed. What happened? Oh, yeah, write D word instead of write DW. Okay, good. So I can go ahead and make that modification across all these lines here. Need to await all of those as well, otherwise it's not going to do much. But yeah, this is the exact sequence I was talking about earlier, right? Where we program the base address into each one of these registers for each one of the regions. And then we initialize the producer pointers from the software end. And then when we want to set up the queue for receive, we increment the producer. Well, okay, we allocate the memory, we write out a descriptor, we increment the producer pointer, and we write that to the register. And same thing for transmit, except we actually write some data into the buffer first. So it looks like this has done something. I need to take a look at the waveforms, hopefully, to see what happened. So this should be writing all of the addresses and initializing everything, including we have the two increments of the pointer value here. So that all is looking pretty reasonable so far, and you can see the addresses stacking up here. So the question is now, did all those registers get set correctly? Let's see. So I think this is the dump file that I was looking at. Let's take a look. If I go in here, where are we? Something is called UUT. I need to rename that probably. That's not optimal. Okay, where are we then? So this is the Corundum module. Oh, I guess. Okay, yeah, I guess maybe it is. Maybe it is called UUT. No, it isn't. Okay, that's not the right thing. PCIe AXI Lightmaster. Okay, core instance. That's what I want. That might be the DMA engine that I have named incorrectly. Okay, so if I hit that, okay, we have a bunch of operations taking place right here. So if I zoom in, there are some things that I do not like about some of these tools. Okay, so we can see this starting to load stuff, right? So this set the RxQ base address, the CQ base address for RxTXQ and TXCQ. So all of the base addresses are getting set. and then we can see the pointers get incremented, right? Here's the RX producer pointer gets incremented, and then TX producer pointer gets incremented. Okay, so now we need to write the control logic to actually transmit a packet. Let me take a look at the comments for a minute here. Okay, always wanted a configurable I/O controller that can manage SPI, I2C, UART, CAN, etc. Anything 50 megahertz and slower. You can just drive a configuration handshake and it'll work with whatever. I mean, so is this like some sort of configurable state machine, effectively? Similar to the PIO controllers on the Raspberry Pi? Or am I misunderstanding what it is you're talking about there? Anyway, for this particular project that I'm working on here, the kind of high-level goal is to support, both research in data center networking, but, the code is also pretty general that can be used for all sorts of stuff that relate to networking. Anything kind of related to the NIC, and also it could potentially be extended to do more general, DMA transfers for, related applications. Anything you got to shuffle around large amounts of data. And then the hope is that I'll be able to set this up in such a way that companies will actually be interested in licensing it. So yeah, we'll see. What I'm working on now is just kind of a first pass implementation of the core of the project. And then the next step will be to continue refining that effectively until we get to a point where it's actually reasonably useful. Anyway, looking at this here, this code ran and all of the registers were initialized. So like I said, the next step is to work on the control logic. All right, so let me think about this for a minute here. I guess we'll have to start with the transmit logic. Otherwise, there's not really much to look at here. So, okay, what do I need to do on the transmit side here? Now let's see here. Go ahead and create a create a new always block. Oh, wait a second, I did that wrong. There we go. All right. Actually, let me make sure I did that correctly on this other module here. I think yep. They say old habits die hard, right? Okay. So in the transmit engine, what are we going to do here? Well, first, we need a state register. Okay, so we have the idle state first, and then I need a state reg. All right, so well, I guess I'm not, well, I'm going to start doing this in the fully synchronous mode for now, but if I have to rewrite it, then I got to rewrite it. Actually, I guess I don't really want this. Okay. Okay, so let me think about how this module is going to work.
basically the idea is that we're going to continuously request descriptors until we get something. And when we get a descriptor, then we will go ahead and perform the transmit operation. So what I need now is another register here. Logic. Descriptor request reg. Okay. Oh, desk request reg. Okay, so for idle, then we will do desk request reg 1. Okay, and I'm also going to reset that back to 0 over here. Okay. Oh, reset it back to 0. Okay, there we go. And then I'm going to do alright, so I need another state now. This is going to be... Oh, how do I usually... What's the usual syntax I use for this here? Okay, I guess that should be correct then. Okay, alright, so I do that. Okay, state idle, and then I do state. Alright, so go to state read desk, and state read desk. Come on. This editor can be annoying at times here. Yeah, I guess I don't really understand the point of making like a super flexible I/O module like that for an FPGA, because it's an FPGA. So, but I guess maybe I don't fully understand or appreciate what it is that you're trying to do with it. Seems like you could just code it in Verilog or whatever for whatever protocol, and then drop it in. But I guess under certain circumstances, it could make sense to make something more configurable. I don't know. All right, let's see here. All right, so the idea with this state machine is that we're going to try to request a descriptor. The descriptor fetch module may or may not be able to fetch a descriptor. If it does fetch a descriptor, then we will go ahead and consume that descriptor and issue the read operation for that packet. So we got state read descriptor. If we get the descriptor, then we got to check to see if the T user was set. If yes, then it was bad and it failed to read it. Otherwise, then we can go ahead and use the descriptor. All right, so how are we going to use the descriptor then? In this case, we need to have the DMA descriptor block here ready to go. I'm actually going to go ahead and move this up higher. We're just going to see how this works if I'm directly poking at stuff in the DMA descriptor. So let's see here. That's set to 0. Desk.tuser. Let's see here. So in this case, we're going to set tReady to 1. If it's valid and ready, then we check tuser. That's a failure to read the descriptor, so we will go back to idle in that case. Otherwise, what are we going to do? Otherwise, what we need to do is queue up the, well, I guess a couple of different aspects of the
transfer operation here, right? So I need to take a look at the DMA read descriptor request. Actually, I'll go ahead and put this over here. There's a bunch of signals inside of this thing, right? So DMA interface, DMA descriptor interface. There we go. All right, so here's all the signals. And we are going to perform a DMA transfer from the host, right? So the source address, that's going to come out of the descriptor. Source cell is not used, I think, anyway. Actually, here's what I'm going to do. I'm going to do this. Okay. So the address, oh, these all need to be set correctly as well. It's all that. Okay. Get rid of this for now. Okay, so the address is going to be 127 to 64. The length is going to be, oh, not T-ready, T-data. T-data, all right, and then the T-ready, we're going to pull this from, let's see, that's going to be around, yeah, the length of this is going to be where, oh, actually, hang on a second, let me look at, did I do this correctly? I think I may have the endianness wrong on these things, perhaps. Maybe not. Right, okay, yeah, no, I think I do have that backwards. All right, this should be going the other way, right? Yeah, okay. That I think is correct. Okay, okay, so where's the length going to be then? This is going to be, I'll take 16 bits starting at 32. 32, so that would be 47. Okay, I think that's right. I think that is correct anyway. Okay, we'll see. If it's not right, then I can fix it. Tag 0, that's fine. ID 0, all this other stuff is 0. Valid. Well, I'll set it to 0 here, and then when we do succeed in reading that, I will set that to set it high for, okay, that's an input. Okay, now I need to adjust this value based on valid and not ready. Okay, great. A lot of these other ones I think are just going to be fixed at 0, so that makes things simple. Okay, so that's that. And then I'm going to do, that's going to go into state read data. I got state idle, I got state read data. And then finally tx data. Oops, tx data. Okay, 2, 3. All right, so read desk, and then read data, and then tx data. All right, so in this case, so I'm looking at, in this case, the, there's a source address, the dest address, that's also going to be set to 0. Okay. Let's see, so in this case, I'm not waiting for any data to come in. I'm just looking for the completion of the DMA operation. So I'm looking for status. Okay, so at that point, then we can move on to the transmit data.
Yeah, I don't really hang out on Discord at all. I have my own, Corundum Zulip for this project and related stuff. I don't have a massive amount of bandwidth, so that works well enough for me. If people are interested in the stuff that I do, they'll join the Zulip. Otherwise, they'll do other stuff. There's like a billion Discords, I think, that you could potentially join. So that's not something I've looked into, really. All right, let me take a look here. So read desk, we get through here, we go into read data, we look at the status signal coming back from the main DMA engine. And based on that, we then need to move to the TX data, and we also need to trigger the internal DMA transfer, which is going to be to this internal DMA descriptor signal here. So let me go ahead and get that set up. Oh boy, all right, DMA descriptor. All right, great. Okay, so with this one, this is going to be DMA descriptor. Source address is 0. Dest address is, pointless, because that's not used here. Okay, and then the length is going to be set to be the same thing. So all I do actually is I go ahead and I set that valid signal to true, trigger the transmit operation. Okay, that's simple enough. Okay, and then at this point in TX data, I go back to state idle. And this is the DMA desk there. Okay. I think that makes sense anyway. All right, well, let's see. This is obviously not going to work yet, but it's a question of does it build? Okay. This is looking promising-ish. Oops. Something was unhappy about something. Assign desk request 46 here. Was that 46? Oh, yeah, that should be output. Hehe. That's and I guess same thing for RX here. Yep. Output. Okay, very cool. Alright, so that's again complaining about the width, but that's fine. This is stuff that will have to be cleaned up a little bit later. This is line 104, right? Okay, that's just set to 20 bits for right now, but great. We'll just do that for the time being. Okay, so that is doing something, perhaps, at this point. Let me see if I can do the same sort of setup in the receive direction. Let's see here. I'll actually move all this down, keep all this together. I can go ahead and copy this, and we'll take that over to the receive path here. Paste that in here. I also need to go ahead and grab the DMA descriptor here. All right, so for this, how is this going to work now?
asking what level of experience do I have before this? I mean, let's see, what is the position that I'm in right now? It's technically research and development engineer at UC San Diego, but you know, the previous version of this was my PhD and postdoc work, so I've been working on the precursor to this for about 5 years or so. Yeah, it's at least been publicly available for like about 5 years, so I guess I've been working on it a few years longer than that. All right, what was I going to do? So for the receive logic, what do we need to do? We need to sort of shuffle some things around here, because the first thing we're going to do is turn on the internal DMA engine. Yeah, I guess that's one thing I don't have set up right now, is a register to configure the receive length. So this is just going to have to, yeah, this will just have to work for the time being. Okay, so we start out idle. What do? We go ahead and we set the internal DMA request to valid, right? I'm going to do that. And let me think here, actually. I'm going to take TX data, I'm going to move that up to here. Oh, I also need something to write the completion. Yeah, okay, one step at a time. So state idle. When this is completed, then we move to state read descriptor. Okay, great. All right. So we need now is for this to trigger the external DMA transfer there. Okay, perfect. And then what I need to do is length and the source address here. Source address is 0. That's fine. Length is down here somewhere. I'm going to call this 4096. That should be fine. All right, so we trigger that. We wait for it to complete. We move to read desk. And as part of this, I also need to set the what was that signal? Descriptor request pulse here. That needs to be set high. So I go to read desk, I set that pulse high, I wait for the descriptor to show up. And then I get this is going to go into the destination here, yes. So that is, oops. Okay, that goes there, perfect. And then the length is to do at this point. That needs to be fixed, but that'll work well enough. Let's see, so this is looking for that. If it failed to read the descriptor, go back to idle. Otherwise, I move over to write data. State. Oh, I did not copy over the states. So I need this, so I can put all this here. State read data, this will be state write data. RX is actually, that'll be RX, not TX. Okay, cool. Okay, that's 1, that's 2, that's 3, I think. Oh, I also need the completion, right. Slowly coming together, All right. So we read the descriptor. If we fail to read it, we go back to idle. Otherwise, we go to write data. Write data is going to trigger the DMA transfer. Okay, great. When it's done, then we go to idle. Okay. Okay. Obviously, there's still a few more things to do, but this is, again, start. Now I need to get the descriptor read logic working. So the descriptor read logic, I think, is going to be very similar to the transmit logic. Whoops. All right. Complaining about a lot of stuff. Oh, all right. So then that's because there should be descriptor write request instead of read. Okay. Oh, there should be RX. again be write descriptor. Okay, great. Okay. All right. So what I need to do now is to get the descriptor read module working, which is going to be very similar, I think, to what, the transmit module? Yeah, because I need to read the data. Or I need to read the descriptor rather. Okay. So this is going to be relatively similar in terms of the setup. Let me see here. It's going to be the descriptor read logic. Take a look at this here. Okay. Then I also need to move over the internal DMA transfer component up to the top here so we can actually issue that internal transfer. Do not have a descriptor request connection here. So that goes away. That's fine. Okay, access desk. All right, so that needs to be handled differently. All right. So I got to rewrite all this, but you know, one step at a time. Okay, so this is going to be working with the DMA read. Okay, there we go. Yes. All right, so state idle. All right, so this is TX desk. I guess do I need? Let me think about this for a second here. Yeah, so this one, it'll go ahead and start main DMA transfer here, assuming that there is something to read. Right, that makes sense. Okay, so this one. Okay, this looks better, right? So we have the least significant bits, and then we're going up that way. Okay, that looks good. All right, I don't think Surfer has really done much, so I can refresh this. Well, it is refreshed, but that's not particularly helpful. All right, so we were looking at, I need to look at for example, the TX instance. Actually not much here. All right, which makes sense. Yeah, okay, so it's just in state 1 the whole time because I don't have anything else implemented yet. So it issues the descriptor request by setting that bit high, but then basically goes to sleep because there's nothing going on. All right, so now I need to get this descriptor read code working here. So what happens? We're going to get pulses requesting descriptors. We have to latch those pulses. And then we're going to go ahead and do stuff based on what pulses we see, right? So let me go ahead then, and I'm going to create a descriptor request reg here. Reg, and that will be set equal to, yeah, okay, something like that. And then what we're going to do, see, what is the best way to handle this here, right? So I have the requests come in. Now we're going to set this descriptor request reg. Can I do... Oh, let me think here. Descriptor request reg. Set that equal to descriptor request reg. Or descriptor request. Is that gonna work? Oh, whoops. I don't know if I can do that. I may just need to go change the dimensions of that signal. Yeah. Can't do that with an unpacked array. All right, but that's fine, because while the descriptor portion needs to be unpacked, this can be packed. That's fine. All right, descriptor request there. And same. Oh, this is fine actually. Yes. So it's just here, and then I go to core, and where was that descriptor request connection here? Descriptor request. Yes, that can be made just a 1 to 0 descriptor request. Okay, great. So we come in, descriptor request, set that high, we latch it in. Oh, I'll set that to 0. All right, cool. So that gets set. And then what we need to do is determine which one we're going to pull in here. So if one of these bits is set, we need maybe to have some mechanism to figure out which bit we're going to use. We then need to latch in the corresponding values, right? So we have the producer and consumer pointers for the queues here, so we'll have to compute the correct address and based on the base address and the producer pointer and read the queue. Right, that makes sense. You think about the best way to do about that. Okay, well anyway, so this is going to go ahead and set up the DMA engine to read the descriptor. Once the descriptor has been read, then we'll see the status here. And then we can activate the internal DMA engine to transfer the descriptor here. All right, so that is TX descriptor. All right, cool. And at this point, we can return to idle. Read desk. Yeah, so once this is done, we have the status valid. We set this to 1, and then we go to TX desk and then back to idle. Okay, great. That is pretty reasonable. So what do I need to do next here? Right, I need to finish connecting these pieces together to make this actually work. All right. So based on the descriptor request reg here, I need to favor RX over TX, otherwise this is not going to work very well. So I think I have... Come here, kitty. Come on. Come on, Houston. There we go. There we go. Okay. All right. My cat decided to show up, so cat cam. There we go. Perfect. Okay. Where was I? I'm starting to run out of steam here. Why, I should not be surprised by that. Okay, let me think here. So I don't need any of this, I don't think, because I'm not waiting for the external descriptor read to come in. But I do need to plug in a few other things here. All right, so DMA descriptor, that's all fine. The addresses are going to be 0. The length is going to be fixed, right? That's going to be fixed at 16 bytes. So that's fine. And similarly, the length over here is also going to be fixed at 16 bytes because, you know, it's a descriptor. So the only thing I need to do is figure out the address. Okay. Right. Let me go ahead and comment out the rest of this just to make sure that's not causing a problem. All right, so what I'm going to do now is take a look at if bit 1 is set, then we'll do something. Otherwise, if bit 0 is set, then we'll do something else. And this is just going to be a very simple mechanism until I have a more complete implementation of this whole thing. So let's see here. The read descriptor request, if it's set to 1, right, what am I going to do here? If it's set to 1, I need to use the RxQ base address, right? And I'm going to add, what is that? The RxQ prod pointer times 16. Okay, great. And then I do this again. And this is going to be the TXQ. Okay, great. So we can compute the address and we can issue the read operation. All right. And then the other thing that I need to do as well is set the, I think it was a destination here, right? Destination. So I need to set the destination equal to either 1 or 0 depending. Okay, great. So I can remove that. That looks maybe reasonable. All right. Let's give that a shot, I guess. See what happens. All right, Houston, we'll turn you around here. How about that? That's better. All right, so this looks like maybe it will work, at least partially. Yeah, because in this case, I don't need to do anything with the AXI stream interface. That'll be handled by the other DMA engine. So it's just on the start. I need to accept that that pulse. Oh, actually, I need to do one other thing. Yeah, that's kind of important. I need to clear that bit. Okay, let's try that. Okay, so if the bit's set, I'm going to clear it, and I'm going to set the destination field for the AXI stream, and I'm also going to do that. Okay, great. So this looks good. This looks good. I think everything else here is correct. Okay, great. And then for read descriptor, I'm looking at status valid. When that happens, then I go ahead and fire off the internal transfer, and then, yeah, okay. All right, that is actually looking pretty reasonable at this point. Now I guess the last thing that I need to do like 2 or 3 more things, but one step at a time, right? So this one is looking like it's possibly going to work. Then I need to implement the completion write, which is going to be very similar to the receive logic. Yeah, except I guess there's a couple of minor wrinkles associated with that. Are there? Maybe not, actually. Yeah, actually, this might be pretty straightforward. Okay, because this logic, I mean, it's basically doing the same kind of thing where it accepts one of the completions. I already have the code to multiplex it. Let me go ahead and pull that DMA descriptor block up to the top. Right, there it is. Okay, so there we go. This thing will pull in the descriptor, and then we need to do something very similar here. I'm not doing RX data, I'm doing RX desk. So I receive the descriptor, right? I see the status valid here. And then, what do I need to do next? What I need to do next is, oops, all right. See you later, Houston. Let me turn off the cat cam. Okay, there we go. What do I need to do next here? Right, so I've received the descriptor. I got the status indication that it was in fact transferred. So at this point, what I need to do is to set up the DMA engine to write this, and the request length for all of these is all going to be the same, right? Request length is 16, and request length is 16, right? That looks pretty good. Get the descriptor, it gets transferred into the DMA engine internally. The DMA engine internally writes it out into the RAM. We get the status from that. This is then going to trigger the the internal DMA. Yeah, so, or not the internal DMA, but the DMA back to the host. So need to do that, and then I can do that. All right, and then this is going to get rolled together here, kinda. Well, this I can move up. This goes here, that goes away, and yeah, okay. I need to get rid of the descriptor request logic here. That goes away. That goes away. Okay. All right, this, let me take a look at the latest output from Surfer. See if anything happened. I don't know if anything happened. Okay, hang on a second. So, all right, I need to look at the descriptor read module here, right? Where is that? Descriptor read instance. Yeah. So state reg is 1. Okay, let me take a look at this actually. So the descriptor read instance, the state reg advanced to 1, but oh, so I set the source address, but I never actually triggered the request. Oops. All right. Okay, we do that again over here. Actually, I guess there's one other thing I need to do, right? Because we're not necessarily going to be reading the descriptor. If the queue is empty, then the queue is empty, right? So what I need to do here, okay, I am screwing a couple of things up here. There should be cons. All right, so this should be cons pointer reg here. All right. All right, so 15 to 0. This is going to be, let's see, txq cons pointer reg. That's set to 0, and again on rxq, same thing. Okay, so that's that. Now what I need to do is if txq pointer reset, then we do txq cons pointer, cons pointer reg, we set that to 0, and same thing for the rxq. All right. Okay, that looks good. Now we have the cons pointer reg here. All right, so now what we need to do is we need to figure out whether or not there is anything in the queue. So if rxq cons pointer reg equals rxq prod, then we do nothing. Otherwise, we do that. Okay, well, we don't exactly do nothing, but okay. What are we doing here then? So DMA descriptor. Okay, so user is either set to 0 or it's set to 1 here. So I set to 0 here, I set to 1 here. Okay, perfect. And then the next thing I need to do is, yeah, all right. So the idea with this is depending on the amount of, depending on whether or not there's something in the queue, we are either going to trigger the descriptor read operation, or we're going to return a null descriptor with the user signal set. So this indicates that the read failed. This indicates that the read succeeded. Yeah, okay. That, I think, is probably going to work. Well, maybe. We'll see. All right. And then for the completion write, this is very similar to the... Okay, is this going to blow up in my face, or is this going to work? Okay, that actually built. Okay, great. All right, so I can get rid of this request link here. Okay, let me think about this for a minute here. For the completion write, okay, we set this, and then we look at the RX descriptor. Okay, great. So the source address, that's always going to be 0. Yeah. And then the destination address, this is going to be based on the TID value. Yeah, all right. So this is going to be the DMA desk.sts ID, and if this is 0, then we do one thing, else then we do something else. All right, great. And then this is going to be coming from somewhere, and I need to go ahead and copy over these pointers, right? Because this is going to be using its own internal, in this case, producer pointers. All right. And then I also need to copy over the pointer resets, right? So this one will enable the driver to reset everything. And these are the producer pointers, not the consumer pointers. All right, so if this is 0, then the dest address, it comes from the TXCQ base address plus the TXCQ prod pointer reg times 16. Okay, great. And I also need to assign TXQ prod pointer reg equals, oh, TXQ prod equals TXQ prod pointer reg. Because we want to be able to look at these if we need to. And we get the, oops, for the RX CQ. All right, there we go. TX and RX CQ. All right, I will do that as well for the consumer pointers. Okay, there we go. So we're getting things set up here. Like, where do these pointers need to leave for all this logic, or need to live for all this logic to work, right? That's the trick. Okay, so this is RX and RX, and then we also need to increment this here, right? So, oh, I think I might have forgotten that on the other side. Let me see here. Well, this did something. I don't think it did what I wanted it to do, but it did something. All right, and I think I might know what happened, because I think I forgot to update this pointer afterwards here, right? So once I read the descriptor, I then need to increment that, and again, okay, great. Whew. Yeah, and I guess I still am not even generating completions right now, so I'll need to do that. But I think that would be a pretty simple thing to do. Okay, great. Oops. What happened? Oh. Ah. Typo. Yeah, that's not helpful. All right. Well, actually not a typo. I guess that was a copy and paste error, but whatever. Okay, so in this case, we have the completion that needs to be set up here. Data, keep, that's the user, valid equals, valid and not t-ready. Okay, great. And I can go ahead and do that. Okay. All right, great. So I can go ahead and paste this as well into the RX code, just like that. Okay, very nice. So at this point, when we get down here, then we go ahead and we set this set to 1 here, right? So go back to idle. There we go. All right, TX, go back to idle. We do that. Okay, excellent. Okay, what happened? What is this complaining about? CPL write. Okay. Oh, I get rid of that. Okay. Oof. I think we may be getting to a point. Interrupts are not working, but we may have the core data path working. So I don't think we're going to be able to get ping working today, because I think I'm going to have to clear out of here soon. But we can pick up where we left off with the driver in, I guess we'll see about the rest of the data path here, but we'll pick up where we left off in a day or two, maybe on Tuesday, maybe same time on Tuesday. We'll see. I got some stuff going on Monday, but on Tuesday we might be able to pick this up and take a few more cracks at it. All right. Well, we'll have to see what this does. Barrel hasn't complained about it yet, but we'll see. Might as well do some minor cleanup work while I'm waiting for this. Yeah, Verilator is taking its time to build everything. That's just kind of a characteristic of Verilator, I guess. It's the amount of time it takes to actually build all of the C code. Verilator tends to generate just a crazy amount of code, like hundreds of megabytes. So yeah, it takes a little while to compile all that. And it takes up a lot of disk space too, which is can be annoying. We can check on that real quick. What is it looking at here? 257 megabytes. Yeah. That's quite a bit. Wait a second. Hey, look at that. It worked. See? That's the data that we wanted to send right there, right? So yeah, the transmit path is working. Look at that. Bam. Okay. That's very encouraging. That is extremely encouraging. I thought for sure I was going to have like 10 other bugs in there I'd have to fix, but yeah, okay. That's pretty cool. Okay, now what I need to do is see if I can get the receive path working as well. And I think the main thing to do here is basically to turn the packet back around. So we're going to do, we're going to wait for the sync, and then we're going to turn it back around and send it out of the source. So that's pretty simple idea here, right? Yeah, okay. So we're going to do that. Oops. Right, so there's the RX frame, right? And then we're going to be turning around and sending that here, right? Okay, so from payload RX frame. Let me see here. RX frame dot get, oh, get payload. There we go. Okay. Well, and now I just saved all those files, so it's gonna have to rebuild it again. But that was actually pretty cool to see that we actually have some semblance of life out of this. So we can actually take a look at exactly what happened leading up to this, right? So we can see when, let me think about this here. We updated the pointers here, right? So then what happens, so we updated this pointer. This pointer is on the read side, because we enqueued a descriptor for read first. Then we enqueued another descriptor for transmit, right? Right, sorry, we enqueued a descriptor for receive. Then we enqueued a descriptor for transmit. And we can see right here, this this frame, right? Well, actually, sorry. So this is an RQ request coming from the hardware, right? And this is for this address, length 4. In this case, 4 is in terms of D words, so it reads 4 D words, and we see 1, 2, 3, 4, right? Boom, 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 boom. And we can see here's the length, and here's the address, right? So it reads that. And then we have 2 more of these come in, right? 2 more read requests. What are these in relation to? Why do we have 2 read requests? I'm trying to figure that out right now. This first read request seems to be the read request for another frame. Doesn't make sense because this is matching that. So I don't know. Okay, this could be a bug, but all right, we'll have to take a look at that. But this one, this read request is, well, we can see them down here, right? Oh, this again is for the same. Why is all length 4? Oh, because the packet's pretty short. Yeah, okay. So this read request, we can see that the byte enables are set differently, right? So it's actually for 15 bytes, not 16. Yeah. And then that data gets sent back. This one is reading all zeros. Yeah, so that, okay, that's got to be a bug of some sort. And then we have this one, boom, 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 boom. Okay, that is the packet data that we wanted to send, right? Corundum rocks. And then we get 2 more requests here. What are these? Oh, this is like another one for the same queue. All right, so I don't know what's going on here. Somehow this is incremented multiple times. And this one, RxRQ frame, I'm not sure what this is. This one is like reading of address 0 for some reason, length 1. All right, so there's some funny business going on. I'm not sure what's going on here, but bottom line is at the end, we have, you know, the data that we wanted to send showing up. So that's pretty cool. Now let's see what happens if we run it again. we ran it again. We get the packet twice. So why did that happen? Oh, RX frame and then TX frame. I see. Actually, so I think we need to wait a little bit longer before doing this init operation here, because if the links are not ready, then it may not actually send it. So I gotta move this wait for block lock up, and we gotta do the wait for block lock before we do the rest of this stuff. Actually, I guess I can do the wait for block lock here. Right, we initialize everything, and then we wait for the block lock. Okay. Something still seems to be a little bit funky, but we'll see. Oh, actually, what I need to do is move this down here. That's actually not a problem, but... Okay, so this one ran. Okay, so here we go. Here's the RX frame, here's a TX frame. Then we do, what is this memory read of address 0? Yeah, there's some stuff here that's not quite working right. Okay. So we need to take a look at a few things, but what I can do, at least, is print out or do a hex dump of the receive buffer. Or not the receive buffer here, but the yeah, RX buffer. Okay. Alright, so it didn't actually get written into the RX buffer. So there's definitely still some issues, but we are seeing some pretty significant signs of life. So can't argue with that. Yeah, and we can see here, buff pointer reset. Ah, okay. Okay, there we go. Wait, so what is going on here? Yeah, the TX producer got incremented to 1, but then somehow this went 1, 2, 3. So, okay, that is a problem. Let me see if I can figure out what happened there. Descriptor read. Okay. Oh. Okay, so this should be TXQ and TXQ. All right, cool. Yeah, that was stupid. Okay. But I'm not sure what's going on in the receive direction, so I need to take a look at that. We'll delete that. Now we'll take a look at the RX path here. Mac RX instance, no, RX inst. There we go. Add that. Okay, so we've been in 1 all this time. And then something happened, and now we end up in 2. Alright, so I guess this means that the packet was received. We issue a descriptor request, and we don't see anything after that. Alright, that's interesting. Alright, so there's something wrong with the descriptor read module then. Let's see here. So descriptor read instance. Okay, cool. Delete that and okay. Well, so this seems to indicate, or the RxQ consumer pointer seems to have gotten incremented, but then after that we don't see any response. So I guess descriptor request. It goes to 2 momentarily, and then we're going to issue a DMA read request, right? So there's your DMA read request, and there's the status coming back. So when it goes out, it has, let's see, there should be a tag associated with this, right? So request tag has a tag of 0. That's not right, I don't think. Okay, I need to figure out what happened here. So this is the descriptor read, and or wait, but why would it have a tag other than no? All right, so that should be fine actually. All right, I'm forgetting how the module that I just wrote works. Great. Yeah, desk read instance here. All right. This goes 130. Well, that did something very different. So we write, we read, okay, that's that. We do another read. Okay, we loop the packet back. Okay, that seems reasonable. But then we have a whole bunch of writes. Oh wait, no, it worked. Hey, there you go. We've successfully received a packet. All right, there we go. Look at that. Yeah, so I guess all of these reads, I'm not sure why it issued so many reads necessarily, but at the end of it, there you go. We received the packet, it got written out into that buffer. So yeah, you know, the next step with this thing is probably to do a test build with Vivado and to see what things are looking like in terms of just the performance on the chip. Yeah, okay, so here we go. We can see now we get the producer pointer updated and then the consumer pointer updates. Over here is when the other request takes place. So, and it's continuously trying to read the transmit pointer, the transmit descriptor rather. So that's what's continuously going on here. It's always trying to read that to start the transmit operation. But then yeah, at this point it's so this is where it reads the descriptor for read, and then it goes back to the same transmit operation. Now the interesting thing is there seems to be, is the timing different over here? Maybe it's fine, I don't know. Something seems a little bit funny about that. Anyway, it issues that operation and then it goes straight back to normal operation afterwards. So that's pretty slick actually. Yeah, I guess there must be some relative timing thing going on. Yeah, I'm not sure what's up with this. That's interesting. Anyway, this seems to be doing something useful, right? We get this return. What is, I need to figure out what's going on here. This seems weird. Anyway, whatever. Progress is being made, right? So we've successfully transmitted and received a packet. There's some more cleanup that needs to be done, I think, before we can get to a point where we can actually write the driver. But, you know, oh, and the other thing too is that I need to set the length right. Let me just do that real quick. Why not? Let me go to, where is this handled? This is Corundum Micro RX. Yeah, okay, so when this thing comes in, we are going to, what are we going to do? Okay, we're going to go ahead and get this from the DMA scripter.sts_len. Okay, and then we're going to set this to if that is less than this, or if this is okay, greater than or equal to, I'll just do greater than that, then yeah, okay, there we go. Okay. Yeah, because we have to limit the transfer length to the packet size, basically. Oh, and then ostensibly that should also go in the completion record somewhere. So what we can do is we can say access cpl.tdata. I'll just put it in the same place, right? So 47 to 32. We'll set that equal to this, right? Okay. I need to fix all the lengths and stuff, but that's a good starting point anyway. All right, so if we do that, then we should be able to get the length in there, and that would be pretty slick. So what do I need to do to actually make this thing work? I need to get interrupts working, so we can actually interrupt the driver and tell it that, hey, something happened, and then I need to write the driver. Is that it? Probably a few more things I need to do, but that's pretty darn good starting point. Yeah, I'm actually surprised at how well that worked. I thought I was going to have to do a massive amount of debugging, but actually this worked out quite nicely, right? You see, look at the bottom, right? Right here, bam. Actually, I should go post about that real quick. Yeah, Houston, what do you want? Come here, Houston. What do you have to say? Want to say something, Houston? No? Okay. Let me see about this here. All right, cat cam time. Houston, there you go. All right, close that. And I will go ahead and create a screenshot here. GIMP is being slow. Incredibly slow, what the heck? All right, and it looks like I also have a hard stop here, so I am going to get this closed down in a few minutes here, and then we will go from there. Go ahead and make one more announcements here. I gotta post about this, right? This thing is actually working. Let me go ahead and, well, partially working. You know, still got work to do, but yeah. Let me go ahead and create from screenshot. All right, cool. So I can do that. All right, I'm going to temporarily switch angles here.
All right. Go ahead. Oh, yeah, all right. Let's go ahead and
Get this thing closed down here. All right, Houston, how you doing? Well, this I think has been quite successful because I at least got to the point where it has been able to write and then read back the packet length. Oh, and here we go. Yeah, we sent and received the packet, right? Yep, there we go. Sent the packet, received the packet, and we wrote it out. Yeah, perfect. Well, except something still seems a little bit funky. I would expect it to make a larger write than that, but one step at a time. That's at least a pretty good starting point. I'm gonna have to take a look at the debug information and make sure that that's doing what it's supposed to do. But we did end up with the data as expected in the received buffer. So this is definitely doing a write. Yeah, memory write 1004,000, and the initial read for the initial packet was 1005,000. Yeah, so it's definitely gone ahead and transferred it to the received buffer. So hey, that's pretty good. That's about probably as much as we can hope for today. So I'll probably pick it up on Tuesday to do some more work. Oops, I can turn this off. So I'll probably pick this up on Tuesday to do some additional work and see if I can get the driver to do something useful. So yeah, thanks to everyone who tuned in for this, rather marathon of a stream. But and also feel free to drop by on Zulip if you have any other questions or comments or anything about what I've been working on here. So yeah, I guess I'll sign off for today and see you all guys in the near future.